All right. So good morning, everyone, to NEWSDR 2020. So, woo! For the other folks that are logged into the Zoom, can you all hear me? Like thumbs up. Okay, excellent. I just want to make sure, like mic check, 1, 2, 3. Woo! All right. So thank you all for joining us here for the 10th annual New England Workshop on Software-Defined Radio, Big 10-0, right? So my name is Alex Wiglinski. I am one of the sort of co-founders and co-organizers of this great event that we host annually here in New England. It's a great forum for all folks interested in software-defined radio technology to get together and to talk about how you implement, let's say, SDRs in cool and fancy new ways, as well as sort of like seeing what the current state of the art is in this technology, applications, and everything in between. This year, we have a very exciting program. And more importantly, we're trying out something new. Unfortunately, due to the current pandemic that's affecting the world, we have gone into cyberspace. We are now in like in this case, a Zoom session that our speakers and panelists can all converse and record, and then it's live streamed to YouTube out there into the wilderness for everybody to watch, right? But that doesn't mean there's no closed loop feedback. All of you are out there in YouTube land can easily provide questions and feedback back to us through our SDR Boston Slack channel. And there will be more instructions about that in a few minutes. So let me change slides. There we go. So what is NEWSDR? What is SDR Boston? Okay. So I think I've already taken the jelly out of this donut. SDR Boston, okay, is a user group that focuses on SDR technology, and it ranges from novices to SDR all the way to experts, right, and everything in between. And again, it's supposed to be fun, it's supposed to be informative, great opportunities to network, get to know people, maybe have collaborations and the like. But overall, it's just a way of bringing people in this community here in New England, which has a very high concentration of SDR people interested in SDR across all walks of life to get together to really meet up and talk and exchange ideas, right? The New England Workshop on Software-Defined Radio, NEWSDR, is kind of our flagship event that is kind of like our rallying point where everybody every year gets together. The first NEWSDR was held at Boston University in 2011. It was held on a Saturday. As we found out, holding events on Saturday is not really a very productive use of our time. We got a lot of flack from a lot of people, all of us. So we said, oh, okay, let's rehost this on a weekday. And so in 2012, we hosted this at Northeastern University. And it was a pretty good turnout. Like we progressively got more and more people from the SDR community around us to join in. At BU, it was about 45 attendees. Northeastern was about 80. At WPI, it was like about 85 or 90. And then as we progressively go throughout the years, in 2014, we're back to BU, 2015, WPI, Northeastern. 2017, we were at Tufts. Then back to WPI. And now UMass Boston. That was the first time we were at UMass Boston last year. And this year, was supposed to be a surprise. We were supposed to be at WPI, but instead we said, you know what? What was going on with respect to like the pandemic, we gotta come together. Even if we cannot physically meet, let's meet in cyberspace. And so the decision was made to go virtual. So that's where we are here today. For a complete listing of all the programs from these past NEWSDRs, we have PDFs, we have video recordings and everything. Check them out at the link below at https://newsdr.org workshops. Okay. So again, 10th anniversary. I would give each of you a cyber slice of cake with a candle on it, but that's somewhat a little bit difficult. I don't have that type of budget. But you know, just think about it. This is kind of a milestone event today that you're attending. So it's the 10th anniversary gathering of us SDR interested people together to talk shop, right? And it's going to be really cool. So this program is not going to be any different. It's going to always get better compared to past years, right? And these are some of the photographs from those past years. To the left, this left circle is Northeastern, beautiful venue, absolutely beautiful. It's always great to be at Northeastern. The middle bubble here, it's at the top floor of the Photonics Center at Boston University. And then lastly, here on the right is one of the meeting places that we had at WPI, like at the Odeum. And oh, that was just spectacular. In the background, it doesn't do it justice, but that was Tufts. It was like it was a renovated church that was turned into a conference hall. Absolutely spectacular venue. So we've had always a lot of fun at all these NEWSDR events. Okay. And I mean fun. I know some of the photographs here are a lot of with me. I think here is with me without goatee. So now you know how I look when I'm shaved. And the rest, you know, there's like whimsical antics to be had by all. And it was not just the organizers, but also everyone around. It was really a great way of bringing together not just strangers who are interested in SDR, but a community. So again, really awesome that we have such a great turnout today. So in terms of registration numbers, last I checked, I think ballpark wise, we have about 350 people who signed up as of Sunday. That's like phenomenally humongous. Like in the past, we would get about 110, 120. This is 3 times as much. And people who've registered hail from all parts of the globe. So to all of you from outside the New England region, welcome. Welcome to NEWSDR. Okay. So again, super duper exciting that we went virtual, but it's also without its kind of like, you know, like a sort of stress. So this is the first time we're offering a virtual format. And so we're going to make mistakes. We're going to be testing out this communications technology. So bear with us if we have like a glitch, if all of a sudden I'm stop talking like that. You know, like the thing is, that means we need to do more work in SDR and related communications technology, which means we're all going to be employed for a while. So excellent. But, you know, we really felt that even with the pandemic, we need to get together as a community. And hence we went virtual, but there's going to be a lot of little bugs along the way. So really bear with us. Again, if there are any problems like that come along the way, communicate over Slack. Don't send me an email. Don't send me a message in LinkedIn or anything like that. Send a message through our Slack channel to NEWSDR-2020. Like my co-organizers and I, we're monitoring that. We'll try and respond to the questions that come in, both to our speakers, as well as if there's any glitches, like, hey, your screen suddenly went like inverted, like this is kind of weird. And we'll try and figure it out along the way. But you know, definitely bear with us. We're trying out this new technology in this format. All right. So co-organizers. So there's me. So this is one of those like action shots of me looking like I'm doing something important. I think I was like midway saying, this is what I want for lunch. But we also have, in addition, we have Mike Rain from UMass Boston. Okay. We have Yusuf Naderi from Northeastern. We have John Slododa from MIT Haystack Observatory. And we never actually seen Anil Pandya, but this is kind of a rough approximation of how he looks like. So I had to doodle this in like paint or something. So that is the best image we have of Anil Pandya that we can find on the web. So, and of course, he's holding an all-important USRP in his hand. So we've heard that Anil Pandya is usually in the wild have a USRP in possession at some point. All right. So no NEWSDR would be possible without the generous support of our sponsors, right? So it's super duper important. Well, it's a community, right? So we have an industry half, we have an attendee half, we have a sponsor half, we have an organizer half. There's a lot of different communities that come together to make this happen. So we really want to thank our sponsors from MediaTek, from MathWorks, from Link, from Analog Devices, from Edis Research, from NI, and from Verizon for making this possible. Right. And in fact, you're going to be hearing from a lot of them throughout today. Right. There's going to be a 15-minute each presentation by each of the sponsors talking about the latest and greatest that they have in terms of SDR related technologies. We're also going to have lunchtime virtual booths of some of our sponsors. And then later on, we have 2 evening tutorial sessions with NI and with MathWorks. So there's a lot of involvement by our sponsors. So we really appreciate the generous support of this event. So I kind of described the agenda, but let me be more specific. So in the agenda, like right now, I'm doing the welcoming address. So welcome, right? Then we're going to go through sponsor session 1, which will have analog devices. We're going to have MathWorks, NI, and EDIS, and MediaTek, each giving 15 minutes about what they're doing in this like cool area and its sort of related areas. We'll then have, like, we'll save questions till the end, and then the Q&A. Okay, so for all you folks out there in YouTube land, right, watching this on YouTube Live, what's really important is that if you want to ask a question, you got to enter it through our SDR Boston Slack on the NEWSDR-2020 Slack channel. So if you're not part of Slack already, sign up for Slack, okay? Join, and we'll admit you. And then what happens, ask your question there. My co-organizers are going to be fielding all the questions that are going to come in. They'll relay it to me, and then I'll ask it to the sponsors. This is, I think, the best way of herding all the different sort of random variables in this multi-dimensional space that we need to optimize. So I'll be the moderator. I'll be relaying the questions to our sponsors if there's any questions from the audience out in cyberspace. Then, oh boy, after the Q&A, we have our only keynote talk of the day from Dr. Tom Rondo, who's like an absolutely spectacular SDR expert, as well as a good friend of mine and a good friend of NEWSDR. So he'll be giving the keynote talk, followed by the second sponsor session with Link and Verizon, and a Q&A that covers both Dr. Rondo, Link, and Verizon, like any questions from the audience out there. Then we're going to have an intermission. Like, this live stream will still stay live, but no one's going to be on. All the action, if you registered in advance, there should have been 4 Zoom links sent to all registrants, each to a different industry sponsor, okay, that is hosting a virtual table at this event. MathWorks, NI EDIS, Link, and Analog Devices. So if you registered, there should be a Zoom link for each one of them. You log in, you can ask questions, they have stuff to show you, and it's going to be really cool for an hour. And then we promptly start our program again at 1 o'clock with community spotlight talks. So 12 folks from around the world have cool things they want to talk about for 3 minutes each. So it's kind of like an elevator pitch about software-defined radio and related technologies. Following that, okay, we have half an hour of virtual posters of those same speakers. So in that same registration link, there should have been 12 Zoom links, each one to a separate poster that you can independently log into to ask questions from each of the speakers directly. Then from 2:30 all the way until 4, we got 3 really cool fireside chats. We got one on spectral coexistence. That's going to be really neat. We have one on Internet of Things. And then finally, open source software at the end to end it all. Then finally, we conclude the day, sort of the main event. And then from 5 to 7, we have two tutorial sessions, evening tutorial sessions, one with NI and EDIS, and one with MathWorks. And again, that should have been sent out if you registered by the deadline on Sunday for this event. Okay. So that's the agenda for today. In order to ask questions in the program, which has been posted on the NEWSDR 2020 website, there are specific hashtags to call out let's say, different entities if you want to ask them questions. So for instance, if you had a question about analog devices during their 15 minutes, in the Slack channel under the NEWSDR-2020, you would put hashtag ADI to help us identify, oh, okay, there's a question there by somebody for ADI specifically. It will help a lot, especially since if there's 350, potentially more people out there asking questions on Slack, this helps us filter out who and where and what questions are being asked and who to exactly. All right. So keynote speaker, again, super, super honored. We're really happy to have with us here Dr. Tom Rondo. He's going to be giving our keynote talk later this morning. So we're really, really excited to have him. So definitely stay tuned for Dr. Rondo's presentation later this morning. Okay. Fireside chats, Again, I kind of took the thunder out of that lightning. So the first one's on spectral coexistence. And so we have Dr. Philip Erickson from MIT Haystack Observatory, Mr. Tim Fisher-Jeffs from MediaTek, and Professor Dola Saha from University of Albany. So we're really excited to have them to talk about spectral coexistence. And the format there is each one of them is going to give, let's say, 3 minutes on their perspective of what spectral coexistence means to them. There's going to be a middle 10 minutes of that half-hour session where I'm going to be asking a few questions. And then the remaining 10 minutes are for questions from the audience. Fireside Chat 2, SDR, and IoT. And we're really honored to have with us Professor Son Han from University of Connecticut, Professor Brian Kelly from University of Texas, San Antonio, and Mr. Matthew Knight from Agitator. And then last but not least, Fireside Chat 3 with respect to open source software and SDRs. And we have Professor Paul Klosas from Northeastern, Dr. Freda Fung from NYU Tandon School of Engineering, and Professor Juha Virinen from University of Tromsø. Oh, this is going to be absolutely awesome. And then, again, the sponsor tutorials, in case you're wondering, oh, what are they going to talk about for those 2 hours this evening? So for MathWorks, deploying 5G new radio wireless communications on an SDR, the complete MATLAB and Simulink workflow. So if you're interested, definitely check it out. The other from NI and EDIS Research, FPGA programming on USERPs using the RF NOC framework. So 2 really exciting evening sponsor talks, tutorials this evening. So definitely check it out after today's main event. Okay, so with that, connect with us. We have a LinkedIn page, Slack. That's going to be the main medium today in order to close the loop in terms of providing us with feedback, with questions, with comments along the way to myself and the co-organizers. So definitely, if you're not part of our Slack, connect it. If you are part of our Slack, definitely engage with us. We're on call like throughout this entire event as much as possible. So I'm going to also put in a personal note. So over the next week, it's kind of funny, both my father and my father-in-law, their birthdays are occurring within this time window. So I want to wish them both a super duper happy birthday. And, you know, great way, like, you know, it's like great event like NEWSDR 2020, as well as like, you know, two birthdays of very important people in my life as well. So with that, I am going to turn the floor over to the first speaker that we have is Mr. Robin Getz from Analog Devices. So Robin, I am going to, let me see, I'm going to try and unmute you. So Robin, can you hear me?
I can very well, yes. Thanks, Alex.
So let me see, did you have anything to share?
Yes, I do.
Okay. So let me make you a co-host. So you should be able to share whatever's on your screen.
Yes. Hang on. So you should be able to see me fumble through PowerPoint now?
I see a thumbling, yes.
Okay, thanks a lot, Alex. My name is Robin Getz. I'm a Director of Engineering at Analog Devices, and definitely happy to be here, wherever here may be for everyone watching. Just a little bit about Analog Devices for those people who may not be familiar with us. We are a company founded actually in the United States in Norwood, Mass. We're founded in 1965. We have about 15,000 employees worldwide now. So, you know, we have lots of different places across the world. When we work with companies, one of the things I like to do personally is understand like what's important to people, and what's important to people is always where the money comes from. And that's the only reason I show this is like communications is a big chunk of ADI's business. We are about a $6 billion corporation in the semiconductor world, which is about a $450 billion market. 6.2 isn't actually that big. We're somewhere in between Chipotle and Chick-fil-A in terms of sales. We do have, you know, organizations across the world. It's, you know, from the US to Europe to Asia, China, India, South America, and Australia. You know, over 30 different countries. And it seems like there's quite a delay between the sharing on the WebEx and the Slack. So unfortunately,
It's about there's a 20-second delay between YouTube and Zoom.
oh, is there? Okay.
Yeah. That way we can censor anything you say.
Hopefully I won't have any FCC problems. But yeah, so, one of the things that we try and do is ensure that we have we try and translate the real world into insights that can transform our customers' industries. So whether it's sense, measure, interpret, connect, power, secure, analyze, predict, we want to be able to take those real world phenomena and shoot them over to people where they can add more value to things. And that's made possible through the breadth of our complementary capabilities, whether that's the sensing, the measuring, interpreting, securing pieces of things. So in a little bit more detail, it's like machines, sensing, sensor technologies, measurement technologies, ADCs and DACs, connecting people. We just introduced actually industrial grade Ethernet PHY. So we're actually in the Ethernet business now as well, from a 10-100 kind of perspective. A lot of wireless connectivity, which we'll be talking about, a lot of security, a lot of system level security, software security, as well as power, the infrastructure that drives all our systems and is able to ensure that the wireless systems that everybody uses can last for as long as possible. And it's just a little bit more detail in terms of processing, interpreting, secure, measure, connectivity, and sensing. Really trying to drive a lot of different industries. We have approximately 135,000 different customers worldwide, whether in a variety of different industries. So one of the other things that we try and do as well is also ensure that we have a pipeline of not only new customers all the time, but new employees. So one of the things we try and do from a circuits perspective, because we are an analog company, is ensure that we have circuits education is like super important to us. So we do actually a lot of things on the education side from a circuits perspective with a few instruments, with parts kits, and on the SDR side as well with the Pluto radio that hopefully some people are familiar with, as well as even full textbooks and labs that we worked on with Alex to go through entire classes for people in like a second year communications kind of theory perspective and practical hands-on. One of the interesting thing is software-defined radio is coming into a lot of different applications. One of the more interesting ones that I've seen in the past was a large MRI company. Their single point of failure, or their largest failure point, was actually in the cable between the MRI machine and their instrumentation cluster on the other side, because cable is pretty fragile and has to have 0 iron in it to make sure that it doesn't get sucked up close to the magnets in the MRI machine. So they actually designed their own modem, their own system to get rid of that single point of failure. So a lot of people are doing wireless communications, maybe not necessarily in a traditional kind of manner. And what that means for us as a chip supplier is we have these fantastic chips and people need to turn them into products. And sometimes that can be quite a daunting chasm in between those chips and products. And that's where we try and work with lots of different people to and provide different solutions to try and cross that chasm. So it's software-defined radios are difficult. It's a variety of different skills, from software engineering to DSP algorithms to digital hardware to RF design to SoC assembly. The DSP algorithm people may be actually more pure mathematically focused and not really care about the rest of the other things, because they're more focused on, is this possible to do, not is it practical to do. And so when we kind of work on things, we kind of look at it from a design flow perspective. And if you are in academia, you may only be interested in, you know, understanding what you want to do and understanding if that's possible. When you want to make a radio and ship a product, you have to understand, you know, if that's practical. You need to be able to see it work, and then eventually you need to make it a form factor that maybe somebody can carry around. And we understand that tools are a customer choice, so we work with MathWorks, we work with a variety of different other ecosystems, from OpenCPI to ADS to Microwave Office, to ensure that whatever tools people are comfortable with, they can actually use to design their own radios. One of the new devices that we just actually announced last week was the ADRV 9002. So this is a 2 receive, 2 transmit device that actually has kind of an interesting PLL settings in it. So one of the things that's possible to do is because we have these muxes that can come up into the PLL or into the receive or transmit pieces, you can actually take PLL1 and drive that into receive 1, and PLL2 and drive that into receive 2. So you can actually be doing like a TDD application, setting this up for your narrowband system, and actually looking at on the other system for your more cognitive radio, searching for a different frequency to use, all in the same chip, trying to be as integrated in the low power as possible. This does have a 30 megahertz operation, so we've definitely heard from a lot of communications operators where they want to get a lower frequency, so we want to be able to do that. So 30 meg to 6 gig, and very narrow channels to try and handle some of these legacy systems like P25, like Tetra, like those kinds of things. And a variety of different pieces. We'd also make system on modules where we actually have the radio and then like an FPGA and ARM kind of system. So this system is 200 kilohertz to 56 megahertz. We have other systems that where the radios are more in the 200 megahertz kind of range. So we actually have 2 devices down on here. So we actually have 4 channels of input and output on this system on module. And when you start doing 4-channel systems and multi-channel systems, its synchronization across channels is super important. And not just synchronization at the LO, but synchronization at the ADCs, synchronization at the DACs, synchronization all the way back up into MATLAB Simulink, so that buffers are synchronized as well. And, we can do that on a device where we can show phase synchronization across power cycles, across radio on, off, across initialization, so that after you get going, you're always at the same level. But so this was done, like 1, 2, 3, 4, 5, 6, 7 times. And when you're doing industrial grade systems, 6 times isn't enough. What those kind of people ask for is what they say 5 nines of either repeatability or uptime. So they want repeatability over 100,000 cycles. So what we were able to do is take this system and plug this other card into it over here. So that gives us 8 channels, 4 devices, all driving into a single FPGA. And we can actually cycle that 100,000 times to actually see the phase difference between all the channels is actually constant over 100,000 cycles. Well, this was 95,000 cycles. And then you can actually measure and provide histogram data of how often or how much different things are, and look at or provide some metrics to people so they can actually design their higher end systems. We also have other systems like LTE primers for people who are just getting interested into LTE. So this is actually an application we actually created with MATLAB compiler. So just to give you a brief kind of flavor of LTE, what it can do, what your signals look like, what all your channels are, and EVM over time, EVM over spectrum, EVM over the grid. And so if you're just getting started on LTE or 5G, this can be a great kind of on-ramp to kind of understand what all the acronyms mean. how big are the dots? What does 2% EVM really look like? What does 5% look like? Can you do 256? Can you do 1024? And how does that change the shape of everything? And again, it's even with that same application, we can do repeatability over time, because anytime there's some kind of device, there's always calibration, there's always like some algorithm that's trying to converge, and in terms of IQ correction. And when somebody says converge, the first question you need to ask is like, well, how repeatable is that? And you can see here as we change at low frequencies, it's very constant, and at higher frequencies, like almost 3,500 gigahertz, we can see there is a little bit more variability to things. So you can kind of understand how your system is going to work and what your worst case numbers versus your best case numbers are going to be, as opposed to just looking at the typical numbers that would come out of the data sheet, which would be like the median. But what we won't say in the data sheet is what the spread is. We are always hiring. There's definitely spots available if you go to careers.analog.com if you're interested in doing these kinds of things. So Analog Devices, even though we are a chip company, we do work a lot on algorithms, a lot on systems, as you can kind of see from some of the things I've shown. And then definitely at lunch, like Alex said, try and come see us at some of the demos. And with that, I think I'll pass things back to you, Alex.
Thanks, Robin. That's awesome. What I'll do is I'll switch over the mic over to Mike. Oh, there we go. Haha. So first of all, what I'll do is withdraw. Okay, yeah. So there's this these things that Zoom makes me do. So okay, so Mike, I think you should be co-host and you should be unmuted. Is that correct?
Indeed, it looks like.
Awesome. Okay, take it away.
All right, thank you so much. Let me go ahead and share my slides. Let's see. Okay, share. So hopefully you can see my slides.
Looks good to me.
All right, get that ugly picture of me out of there. So anyway, I am Mike McLernan. I'm with MathWorks, have been since 2001. I've been associated with NEWSDR almost since its inception. Very, very happy to be here. That was a great talk to start us off, Robin. Thank you very much. So we're here at an SDR conference, but I'm going to be a little bit more expansive and talk about more than just what we do for SDR. So it's a little bit of an overview and what are we currently doing at MathWorks. So first off, we are a global company. So what you see before you, that's a picture of one of our campuses in Natick, Massachusetts. But we really do span the globe. We've been around for over 35 years. Our tagline, we want to accelerate the pace of engineering and science and discovery for all of our customers. We want to help you all do your best work. And so we are trying to build tools across many domains to make that happen. You see many offices in most of the continents of the world, and we're used in over 6,500 universities worldwide. When I saw that number just the other day, I updated it. I was shocked. I don't know how many universities there are in the world, but 6,500 is quite a lot. So to that point, I want to tell just a little bit of a story. When I travel, and I used to travel often, not so much anymore, I find out that someone that I meet is of a technical bent, an engineer or a scientist. I always ask, well, do you know MATLAB? And 9 times out of 10, they say yes. So the most telling story about that occurs one time when I was in the Dominican Republic, and I happened to meet someone at an ice cream stand. She's from Romania. She was doing research on bats in the jungles of the Dominican Republic. And so I asked, do you know MATLAB? And she said, well, yes, I do. I'm using it to process my data. And I think, how do you like that? A guy from Massachusetts and a lady from Romania in Santo Domingo, Dominican Republic, talking about MATLAB. Who would have thunk? So I just think that shows you the reach and the spread of MATLAB across the globe. So our products cover many, many applications. This is a bit of an eye chart. No, this is a really significant eye chart that I don't expect you to read, but it tells you where we have products in domains such as automotive, aerospace, education, bioinformatics, finance, text analysis, deep learning, GPU coding. So, but I don't want you to go quite that broadly. I'd rather focus in just a little bit on applications that we care about in this community. First, we have numerous products in the signal processing domain, because you really can't have communications without signal processing. And then wireless communications. Again, I've been associated with the communications toolbox for many, many years, which serves as a platform for our standards-based products. I'll be talking a little bit more about standards later on in my talk. But I just want to make mention of something that we're investing in the communications toolbox these days, and that's AI deep learning. So I would like to point you forward to our noontime talk, which is going to be about a deep learning application of RF fingerprinting for Wi-Fi routers. I think it promises to be very, very interesting. You can't really have a communications link without RF. And so we have multiple products that model RF for you at multiple frequencies, incorporating all kinds of nonlinearities and imperfections. And we also work with wired signals as well for people who are interested in signal integrity and SerDes. And finally, for people who want to do more than just algorithmic exploration, we do provide a path to actually build your radios. So with FPGA, ASIC, and system-on-chip development. So you see the products there, including a wireless HDL toolbox that covers, that has IP for multiple standards. And as long as I'm camped out there, I would like to point you forward to the 5 o'clock session, where one of my colleagues will be talking about an algorithm to prototype workflow using MATLAB and Simulink and wireless HDL toolbox for a 5G application. So that promises to be very, very interesting. I will certainly be there. So what do we do with standards? Well, we love standards. We started in about 2013. We decided we have to invest in standards. And so we shipped an LTE product. But since then, we've been building many, many more. So the standards that are represented on this chart, we have products for, and there are more in the pipeline. Because if you are in industry and you're working in communications, likely you are not inventing your own signals, but rather you are working with standards. So we want to cater to all those people in industry that care about standards. And we want to provide for multiple use cases with these standards-based products. First off, we want to provide waveform generation. This really helps the tester, the chip designer. I need a transmitter that has to provide so much EVM. I need a golden reference waveform. These products support that use case. Or I want to do end-to-end BER simulation. We provide for that. We enable you to do that. And by the way, these products are all open MATLAB code. So we are not claiming at MathWorks to be the world's experts on receiver design, but we give you a reference, a baseline with open MATLAB code. So if you have a better carrier synchronizer, well, you can just rip ours out, insert yours in, and see the improvement. So that's another use case that we provide for. We also allow for design verification. Again, if we allow for a design that's going to meet BER specs that are specified by standards, but if you have a better algorithm, just plunk yours in, take ours out. That's why we write it in open MATLAB code. And finally, we allow for signal analysis and recovery. That gets into some of the SDR world. That gets into some of the Plutos, the RTLs, the USRPs that we provide connectivity to. So we love standards. So we also model full links. So what you see before you is pretty simple notional transceiver with a channel. But as you and I know, there's a whole lot more that goes into it than just this simple block diagram. So you have to start at the beginning with waveform generation. So we provide many, many different standards-based, standards-compliant waveforms. And then if you want to build your own MIMO systems or OFDM systems, we allow you to interact with generic capabilities such as those, so that you can tune, say, your OFDM modulation just the way you want. And then modern communication systems, they will always be MIMO. And so we allow for beamforming, the traditional beamforming that enables you to steer your nulls and your peaks to particular geographic locations. Or if you need to do spatial multiplexing pre-coding, you can do that as well with our beamforming capabilities. You got to have an antenna, and typically at the outset you need to model that antenna. So we provide tools for that, to the extent that if you have a physical physical picture of an antenna, and you can just insert the image of that antenna into our software, and it will do all the analysis to tell you what is the pattern. So that's very, very handy and practical. If you're going to do link simulation, you have to model your channel, because that's where all of the crud comes in to ruin your signal. So if you need to model a fading channel or RF impairments, we supply that capability for you, which it turns out is very, very useful in AI applications. Watch Etham's talk at noon to learn more about that. And if you're going to impair the signal, you need to be able to correct for all those impairments. You need to perform synchronization. We give you tools for that. Again, all open MATLAB code. And finally, if you are going to get some kind of meaningful metric of performance, you need to be able to do measurements. And so we provide many, many scopes and measurement capabilities for you to assess the performance of your links. So we really feel that on the fly, we provide a really complete suite of tools for modeling, simulation, and analysis. We model channels. Typically, if you are going to build a receiver, you have to model the channel, but you might not want to build it and maintain it yourself. It's just part of the ecosystem that you need to use. But that's an area where we, as a tool builder, have been investing for nearly a quarter of a century. So with the modern move of communication systems to higher and higher frequencies, i.e. millimeter wave, channel modeling using ray tracing has become much more of a going concern for the world and for us. So that is a current investment for us in ray tracing. So we now have a capability where if you have an urban scene, you can use OpenStreetMaps to import buildings into that scene and then perform, as you see here, a point-to-point analysis of where are the rays coming from, what's their angle of departure and arrival, and what's the power levels as they impinge upon the receiver. We also incorporate the loss factors from different building materials in that analysis. So again, you can do point-to-point, you can do coverage analysis. So that gets to the idea of multi-user systems, system-level modeling. So these coverage analyses are very, very important to that. So we will give you that capability as well. And then from the ray tracing analysis, we can create impulse responses from which you can actually create a channel filter and then work with the bits that you've simulated using the other capabilities that I've mentioned earlier. So that's a very, very powerful capability. And if you want to learn more, and then you can also see the effect on your signal by using constellations and measuring EVMs and MERs, etc. If you want to learn more, just Google channel model. Okay, as long as we're talking about models and we're getting closer to hardware, we also model RF hardware. What you see before you is an analog devices 9361. And we offer what we call a support package that uses a Simulink model to model all of the behaviors of that board, which has hundreds, thousands of registers. I'm sure Robin could quote me chapter and verse on how many registers that chip has, but we model it in software and how much easier it is to assess performance and behavior in software than in hardware. So these are exact validated models of both 9361 and the later model 9371. And the beautiful thing about this Simulink model is that it employs multiple domains. So you've got the analog portion, you've got mixed signal, you've got digital programmable filters, and you even have a state machine to perform the AGC. And it's all in one environment. Very, very handy and useful. If that's something that is of interest, you would want to Google AD9361 Simulink. And quite pertinent to our time today here, we connect you to SDRs. Now, I've been mostly associated with data input, data output for SDRs, but what is useful? What is that useful for? If you want to test algorithms and live signals, we can give you many, many examples where we do that very thing with standard compliant waveforms and then do demodulation of, say, an LTE or a 5G waveform at the receive side. If you want to learn more, you would Google MATLAB SDR. And also, I want to just share with you a little bit of the platforms that we do support in terms of I/O. First, USRP, RTL SDR, low cost, only $20, $30. Zinc, which is highly useful for targeting. And again, I would point you to the 5 o'clock session where you're going to learn more about using the Zinc for hardware targeting. And then the Pluto. So we love all of these radios. And that reminds me of a story of that my wife often tells when she is asked, which one of your kids do you love the most? And she says, the one that I happen to be with at the current time. So the radio that we love the most is the one that we're working with just at this very moment, but we really do love all of our radios equally. Also, we provide educational resources, much like Robin mentioned with the ADOM work that he has done and that we use. We want to provide resources for professors to use SDR in their classes. So I'm going to get on a soapbox for a little bit here. Comms professors, I have found from many conversations with them, they want to insert realism into their classes. Too many students feel that comms is just a bunch of mathematical gymnastics, mathematical heroics, and there's no real practical application that they can see. With the introduction of SDR in the classroom, this can change by quite a bit. And we've helped to create resources for that. Robin certainly mentioned a book that he and colleagues have created for the Pluto SDR, and we love that book. I worked with a professor from Milwaukee School of Engineering on an intro class using mostly RTL SDR, but also some Pluto and USRP. And it really is a wonderful, say, sophomore, junior level intro class that covers the typical analog pieces and spread spectrum and OFDM. And the class is littered with labs using MathWorks software and the RTL and the Pluto. So if you're interested in this, we put this up, I don't know, about a year and a half ago, and it has been shockingly popular. I wish I knew all the people that were downloading it and what they were doing with it. But if you are interested and want to learn more, simply Google Intro Comms Course File Exchange. And so with that, I would want to return to basically a tagline that we like to use. We at MathWorks want to give you antenna to bits on the desktop and on the radio. And I thank you very much for your time. I want to give it back to Alex at this point.
Thanks, Mike. Thank you. So that was an excellent talk. So next on our agenda is MediaTek and Henry Cox. And again, just a note to everybody that's watching us right now, please save your questions for the Q&A session at the end of this sponsor session 1. Okay, so let me, how do I do this? So Mike, I'm not sure if I think you need to stop sharing.
Oh, okay, sure.
Okay, great. Yeah, I know the technology. Okay, so let me do that. Oops. So Henry, can you hear me?
I can hear you. Can you hear me now?
Yep.
Okay. Cool.
And I just made you co-host, so you should be able to share any slides about MediaTek.
Does that get? Did that share? Can you see that?
Not quite. No, not yet.
Not quite means I screwed up.
It's there we go.
Did that work?
Yeah, that's it's there we go. Awesome.
Okay, cool.
Thank you.
Now I've lost half of my screen. Oh well, what the hell? I'll go with what I got. Okay. So my name is Henry. I work at MediaTek, and my manager asked me to come up with a presentation. I'm going to warn everybody that I'm not a marketing guy. They gave me a bunch of marketing slides, and I pretty much threw them all out. So my apologies if this is not what you expected. So if you've never heard of MediaTek, the company, it's the fourth largest fabless semiconductor in the company in the world. That translates to about $8 billion US dollars revenue in 2019. About a third of that comes from smartphones, which, SDR, which is why we're here. The company is based in Taiwan. There are about 16,000 employees worldwide. About 500 of them ish are in the US, and about 150 are in Massachusetts, in Woburn. In this site in Massachusetts, basically we do a number of things. One of those would be the compiler and the tool chain for various different modem SDRs for the DSPs. We also do a domain-specific language, which we use for writing algorithm to firmware for various of the modem products. We do a fair bit of work on various simulators typically for algorithm and instruction set simulator kinds of things. And there's also an analog mixed signal group that do magical stuff that I don't really know anything at all about. If you haven't heard of MediaTek, you almost certainly own some MediaTek products, even though you might not know that. If you have an Amazon device, especially like an Echo or something like that, you'll almost certainly have the MediaTek chips. If you own a digital TV, you almost certainly have a MediaTek chip inside. If you bought your phone not in North America, there's a good chance that you have a MediaTek chip. If you were careful, or maybe not so careful, in the US, you could also have bought one with a MediaTek chipset. So it's fairly widely deployed. If we go and look around at analyst reports, and if we want to believe analysts, and I don't know if we do or we don't, here we have a blurb I found from Citigroup, who say that they're projecting that MediaTek will sell between 80 and 110 million 5G chipsets next year. Cool. So if we go do a little bit of back of the envelope calculation, if we take the lower bound of their estimate and we say 80 million chips, and let's guess that they sell for 20 bucks a pop. I have no idea how much they actually cost. I'm just using a round number because I made it up. Anyway, so if we take 80 million times 20, that gives us $1.6 billion, which is a fairly large number. If we divide that by 365, we get $44 million a day, which says to me that there's a really high value for anything that our group can do, or the company in general can do, to improve the schedule predictability of one of the modem projects, or to shorten the schedule even by a single day. A single day might be worth $44 million. Similarly, if we could reduce the cost of the chip even by a penny, that would be a fair amount of money. Or if we could increase the value of the chip, if we somehow made it so that people wanted to spend $21 or $20.05, again, that would be quite valuable, and would more than pay for our group, our whole team, for a very long time. So, okay, so that's why we do what we're doing. If we think about a smartphone SoC, there's a whole lot of parts to it, or there's a whole bunch of bits and components. So there's the part that that users actually see and interact with, the apps processors, which are often ARM devices, or typically ARM devices. There's a GPU. There's probably an AI engine. There's some sort of image processing. There's audio. There's some RF components, and then finally, at some point, we get down to the modems that are on the SoC. Wi-Fi, et cetera, is there too, but we're thinking here 3G, 4G, 5G. So in that SoC, again, and viewing from our local site, right, we don't do any of that top stuff. That's just not us. But what we do is this bottom part, the 4G and 5G modems, which are SDR devices. If we now stop and think about what we see in a modem processor, or in the modem processor, what we discover is, well, 80 million chips, that's a pretty high volume part, right? And it's really deeply embedded in the SoC. it's unless you're actually designing the modem, you typically don't see the processors. So they're a deeply embedded component. And because there's so many of them, and it's so deeply embedded, you can make it a very specialized device. It doesn't have to be general purpose by any stretch. And more than that, actually, the modem processor actually only ever runs one program, which is the modem firmware, whatever that happens to look like. And in fact, we know what that program is going to be, or what that program is, while we're designing the chip, or at least in theory, we might know some of this stuff. So again, thinking back, we can say, we'd like to make this thing smaller and faster, or run cooler, use less energy, et cetera. And anything that we can do to make it faster, make it cheaper, make it consume less energy, so it's fair game. That's something that we would want to do. So what sort of things could we think of, right? And there's obvious ones, right? Well, we could add special instructions to the processor, do special operations, right, to make something go faster or whatever. We can add specialized memory or special capabilities to the address generation units to support the kinds of memory access patterns that you see in modem firmware. We can use some sort of special numeric systems and special processing. We can, pretty much anything we can think of, we can do. It's all fair game. But again, whatever we do, we have to consider the system as a whole. And again, probably given our, my bias or our bias, given that the compiler team is local, whatever we do has to be programmable. So programmable in the sense that, a mere mortal has to be able to understand how to use it and how to write a program to use whatever features. But also, the feature has to be something that the compiler can understand so that you can generate code for it. If it's not programmable, or if the compiler can't understand it, then users are going to have to write low-level assembly code, which is time-consuming and error-prone, and it isn't portable. So it gets to it'll be a substantial effort to rewrite it for the next generation of the processor. So programmability is very, very important to us. Similarly, whatever hardware, if we're changing hardware, we add anything in the hardware has to be verifiable. We have to be able to prove that it's working correctly. It has to be manufacturable, right? You have to be able to place and route it. It has to be, something that TSMC can manufacture. You have to be able to test the part from the perspective of hardware test when it comes back. There's a whole laundry list of considerations that we have to be aware of, in addition to just, and we want this thing to be small and fast. So a fair number of constraints to consider. Okay, so that's kind of high level, like, there's a problem set. So now the question is, you're sitting there, or if I was sitting there, I'd say, so what do you guys actually do, right? We, at the site. And so kind of, I'm an R&D guy. So what I thought might be interesting is to go talk to you guys about, very briefly, about a number of different projects that we've done over the last couple of years, either as internship projects or sometimes as by employees, to sort of give you a feel of what sort of thing that we actually do. Why would that be interesting? Well, I think there's a number of graduate students that are probably attending, or at least I hope so. You might be interested to someday apply for an internship, or even, God forbid, apply for a job. Somebody else might want a job. Who knows? Anyway, I think it's just generally interesting to know what people are working on and what's out there. So moving along, we say, so one project, the first one mentioned here, is basically as a compiler project. And here the basic idea is to take Super, which is a super optimizer for the LLVM compiler infrastructure, and do some tweaks and hacks and modify it so that it's applicable to the DSPs, well, one of the DSPs that we use internally, and use it to generate a candidate set of people optimizations. So basically to improve the compile code quality. Manually producing people optimizations is quite expensive, so automating this, the process is quite helpful, and there's a huge number of candidates, so automation is useful. This particular project was done last year and was presented at the LLVM developer meeting last autumn, if you happen to be interested in compilers. Another compiler-related project is to do with testing the compiler to check to see if the compiler is correct, is generating correct code. Here, the issue or the basic idea is that fuzzing or an automatic program generation is really handy for testing compilers. You get you generate a program and then you compile it in various different ways to see if the compiled code gives you the expected result or gives you the same result when you optimize this way or that way or with these options and those options. If you don't get the same result, then you believe that you have a compiler bug, or possibly you have a program generation bug in the sense that the generator has given you some non-portable code, basically has generated undefined behavior. In either case, when you have one of these mismatches, you have this huge program that's been automatically generated, and it can be a pain, very painful to try to manually debug that, send it to the poor compiler dude. So this project is basically to find a way to reduce the generated program to be something that's as small as possible, minimal, that still exhibits the same bug, so that and then give it to the compiler guy so he can figure out what happened and fix it. Again, handy project. Totally different area. This project was essentially to check the correctness of a set of constraints for a particular DSP part. In this case, the DSP in question has a very complicated instruction set and has a lot of complicated requirements for what it means to be a correct program. So for example, there's a lot of constraints on the order of, if you use this register as the destination for this operation, then you can't use it for this as a source of a subsequent operation for this number of clock cycles. Or the source and destination registers have to be on a quad boundary or whatever. Anyway, there's a whole long list of constraints having to do with limitations of the hardware. The hardware has limitations due to, manufacturability or routing, timing, just hardware complexity. So we have this, long list of constraints, but the constraints are also written by hand. Some poor designer wrote it, and because it's manually written, they can be incorrect. It's common, basically, for somebody to, go update the hardware and forget to update the constraint, or the other way around. So we get incorrect constraints. That's a problem because we actually use these constraints in lots of different ways. For example, for design verification to generate verification tests. If the constraints are wrong, then our DV is going to be either incomplete, there'll be behavior that we haven't tested, or will be error prone, will end up generating a lot of mismatches, and there'll be a lot of debug time spent debugging issues that aren't really issues in the code. Similarly, we use constraints for the compiler to tell the compiler what it means to be correct code, so the compiler can take advantage of those constraints to do a better job of optimization. So anyway, so constraints matter, or the constraints matter to us. The project in question was to take Z3, which is an SMT solver, and used Z3 to verify properties of these constraints to check for inconsistency and bogusness, basically. And it turns out, kind of to the surprise of the intern who did the work, he found really quite a number of bugs in the constraints. He was so thrilled when he came running into my office to say, "You'll never guess what I found," because I think when he started the project, he was convinced that he wasn't going to be able to find anything. So it was kind of cool. My clock stopped, Alex, so you're going to have to just break in when I'm going too long, okay?
So yeah, I think we're a little bit over, so perhaps we'll like I'm not sure if any concluding remarks or anything like that.
I just, I have just I was planning to go for whatever the 15 minutes and just go through, you know, here's a project that people did, here's another project in a different area, here's another project in a different area. And then when I ran out of time, I would just run out of time.
So yeah, so I think we're a little bit over
Okay,
the minute, but Henry, I think I mean, like, so maybe just to conclude, where can folks find more information about MediaTek? Like, obviously the website, right? Like www.mediatek.com. Is that correct?
That would be a place to start. You know, if you're curious about particular, particular projects or internships, you can contact, well, me or Tim or Vince. I think Vince is probably here too. He's the compiler team manager and was responsible for most of these compiler-related projects. So,
okay. Well, yeah. Awesome. Okay. Well, thank you, Henry.
Okay, I'm going to stop.
Thank you. I'll make you. I'll remove co-host permission. There we go. All right. So with that, what we'll do is we'll switch gears to our final company. Without further ado, we'll have Hayden Nelson from the NI, right? So recent name change, and also they part of NI is Edis Research. So definitely some really exciting stuff to talk about. So without further ado, Hayden, please take it away.
Hey, can you hear me okay?
Yep.
Oh, excellent. No, it's great to be here. It's I sure wish that we could be there in person at WPI. I'm kind of sad, but I can confirm that is an accurate depiction of Neil Pandya on your slide from earlier. So that was pretty much spot on. We had a good laugh about that in the side chat, Professor Roglinski. So let me go ahead and share my screen here. Screen 2, let's go that one. All right, can you guys see my screen?
Yes. Yep.
Excellent. All right, so I just want to give a quick presentation here. I'll try to keep it within the 15 minutes. Let me start a stopwatch here to keep myself honest over here on the side. So I'm Hayden Nelson. I'm a technical principal marketing manager for SDR here at NI and Edis Research. So I just wanted to go over some kind of things or what's new and share some cool things that have been going on that we've been doing with SDR in the community and things of that nature. So the first thing is you are right. We all have, many people in this audience, I would assume, are quite familiar with Edis Research and as the big supporter of open source SDR and our green branding colors. And so the major thing you'll see here is there's a lot of green on this slide. And so I figured I would address what you just said was a major kind of a rebrand of NI. And really, what does that mean for open source SDR? And it's kind of, being just real, direct and honest. I mean, National Instruments is, we acquired Edis Research in 2010, and National Instruments, NI is a global company, national, so we're international. So that word, necessarily kind of didn't apply as we continue to, become a larger and larger company. And instruments, well, we're doing things from enterprise systems to supporting wireless research communities with software-defined radios. Well, that's not necessarily just instruments. So both those names kind of needed to evolve, and most people called us by the nickname NI. And so we just kind of said, hey, let's make our nickname our official name. And so that's kind of, what happened there with the rebrand and whatnot. But it really is it's kind of more than just colors and logos to us. At NI, it's really about kind of evolving our company to address customers' needs. We've rearranged ourselves in the last few years to be a little bit more industry aligned to different aspects. And that means that hopefully more useful products, but with all that said, we're in the SDR space. We're still, investing in radios. We're still building software-defined radios. We're still, investing in the USRP, the Universal Software Radio Peripheral that many of you in this audience probably know and love. And so, we kind of, so what I'll share is a few new hardware products that we've come out with since NEWSDR last year, which, I kind of am sad that we're not at Worcester Polytechnic. It's such a beautiful campus. I had such a good time at UMass Boston last year, looking over the bay and the harbor. So I'm here in my home office now, as you saw a minute ago. So we're still investing in radios. Some of the new things that we've come out with since the last year is a couple options on our N series and a kind of an evolution of the X310. But we still got the B series, the known and loved USR B200s, the X310s, the embedded systems radios where you got embedded zinc processors. Mind you, there's a lot of Robin would love this. There's a lot of analog devices chips on the front end of these things, in the N series. So one of the latest ones that we released since we spoke last year at NEWSDR was the N320 and N321 radio. This is a kind of more on the higher end side of our radio portfolio. It has 2 channels in, 2 channels out. It has 200 megahertz of bandwidth per channel. And the cool thing about this one is it has local oscillator sharing, so you can do multi-channel phase coherent applications. And so I actually, bumped into Robin Getz at ADI at IMS last week in another Zoom room meeting. That's how we meet people nowadays in this pandemic, is just Zoom meetings. And we were kind of like, we had a short discussion about challenges of multi-channel synchronization, and this particular radio is something that we've put forth as a way to help people with those kind of challenging applications, because you really need to synchronize the clocks plus the local oscillators. And there's, people could do this in the past with previous radios of ours. We just tried to make it a little bit easier by having built-in local oscillator exports and imports. And of course, this is supported fully by GNU Radio and is, a standalone radio that you can run an embedded Linux on it with the Zinc processor. And so, the other thing is kind of an evolution. We found that people that are doing wireless research projects, that they'll be working in the lab and they get something working and in kind of ideal conditions, and getting out into the wild, I guess, so to speak, is always the proof. Let's say you wanted to build a wireless test bed and you wanted your radios to be outdoors mounted on light poles, or in a kind of a harsh environment where you could, apparently it rains, it might even snow in New England from time to time, I'm not sure. I used to live in Boston, and the snow was a lot of fun. And so we built this X310, we call it the RX310, in partnership with a company called Pixis Technologies. And so they've basically taken an X310 and repackaged it in a weatherproof enclosure for that kind of outdoor environment, rugged environment, in this conduction cooled enclosure with no fans and things of this nature. So that's something new since last year that we didn't have to really talk about. But for software defined radio, I got my, air quotes up, software is the first word there. And so we continue to support a number of different software, tool chains. And as Mike kind of said earlier, which one's my favorite tool chain? It depends on who I'm with at the time. We are NI, and of course, NI is still the NI that many people know and love. I mean, part of that rebrand was about expanding beyond our perceptions of it just being a LabVIEW company. We still have LabVIEW, but we aspire and have ambitions to be more than that. But in the software-defined radio space, LabVIEW and LabVIEW FPGA is still supported as something, a tool chain that some people use for prototyping different wireless communications or SDR applications, as well as a myriad of other applications. And of course, we have a really good relationship and partnership with the MathWorks and MATLAB. They do a great job with their communications toolbox. I actually, recently gave a presentation, going to the depths of that, and it's a pretty nice tool chain that you can use. And so for me, I look at that and I go, there's a lot of people doing machine learning and AI for spectral, sensing and awareness, and they have a lot of cognitive machine learning algorithms in MATLAB that you can model and then quickly bring it into the real world with real world signals, hooking it up to your radio. And so that's a nice tool flow that people take advantage of. And of course, one I probably spend the most time with is around the GNU Radio community. GNU Radio is a free and open source software radio community. And I'll talk a little bit more in depth around this, because for GNU Radio, most of those people that are working in the open source side of SDR, and I'm excited about the talk later about this, is the USRP hardware driver, or UHD. We have a new an update coming to that, a new release driver that will give you a number of capabilities for your wireless applications soon, as well as a major update to our RF NOC framework. And RF NOC is, for those who love acronyms, is the RF network on chip, and it's our framework for putting SDR algorithms down onto the FPGA without having to build the entire infrastructure of the FPGA yourself. And so we've tried to make that easier for you. And we have a workshop today that Neil Pandya and Jonathan Penlam, who was actually one of the original architects of RF NOC, will be giving today at 5 p.m. So I encourage you to take, hopefully you get to take advantage of that. Neil's, Neil, if anyone, I got to come up with a reward, but if you can stump Neil and Jonathan on an SDR question, I'm going to be pretty impressed. Those guys know their stuff. So UHD is our open source driver. It's on GitHub, all the source code. And so we have a version 4.0, and this is probably is going to release around GNU Radio Conference this year, which is in about a month and a half. And so this update to UHD 4.0 is a pretty big one for us. It's a major step forward with lots of enhancements to the driver. And the main things, I guess the summary is we've done a lot of improvements to the FPGA, so you can get full rate streaming, all 4 channels on an N310 at 125 megasamples per second on all channels. Come to our booth at noon, and I'll show you a demo of that. I have a video I can share. So we've done a lot of enhancements to the FPGA and on the host side, re-architecting the FPGA framework so you can have more IP blocks. You have more flexibility to trade off between throughput and latency, static routers versus dynamic routers. And so you kind of have more options to adapt it easily without having to rebuild the entire thing to your application, and a number of just critical bug improvements. I mean, it is software. I always tell software engineers, if you don't write any bugs in your code, we won't have to debug it. But bugs do exist, but we've done a major amount of testing on this driver to where we've got a lot of critical bug fixes in there, and several new features like network mode on the E310, which allows you to run it kind of headless, or run it where you don't need to use the onboard processor for debugging, and just a lot more documentation. We have a full RF NOC specification that I'm happy to share with you to help you get up and going with these tools. And it is fully supported in GNU Radio 3.8. I want to call that out, 3.8. Marcus Mueller, I saw you in the chat. Sure you'll be happy to hear that as the major developer and supporter of GNU Radio 3.8. And so that's a good thing. And so with that, I'll kind of use my last 5 minutes here just to share a couple things we've been doing for the community. And so me and Neil, Neil Pandya, who we saw in Alex's slide, it's a perfect rendition of Neil. He and I are both really passionate about this community and these applications. I mean, you can see you guys can't see my camera, but I have a stack of USRPs behind me. One of the things we're really passionate about is getting people more excited about it, and so we're doing this in sort of 2 ways and getting people onboarded. I actually kind of built some very introductory content on edis.com for just like getting people started with the drivers. If you're in this group, that's probably not the content for you, because you probably already know how to use these drivers. But we are building out a course that is a digital online course that will be split up into very small modules that you can come and watch to learn about topics just kind of getting started with UHD, some topics of GNU radio as it relates to using it with actual hardware. There's a lot of great tutorials on GNUradio.org for just getting started with the tools. We'll be covering some of that, tips and tricks, synchronization, and embedded applications. And so our first drop of this course, and we're going to continue to build this out over time, but the first drop of this course is going to happen by GNU Radio Conference this year. And so I'm excited about that. And, and we'll be, doing things on RF Network on Chip as well. But, you got an opportunity today at 5 p.m. to talk to Neil. And then one other thing I said in the chat was, do you want some free radios? That's always, I know the answer is yes. And so we've actually worked with some folks over at the Air Force Research Lab in the Sensors Directorate, and they actually put on this yearly competition called the SDR Challenge. Last year we called it the Beyond 5G Challenge, and accredited universities can apply. Here's reach out to Bob Lee. But how this works is the AFRL University SDR Challenge is you can apply, you get if you're accepted into the challenge, you kind of propose a research problem, you're given free radios to do that research on. So AFRL with the Wright Brothers Institute, that's kind of like the sponsoring entity outside of the DoD. They will give you free radios, and you will be able to execute a research problem. And if you get accepted to a conference to present on it, maybe even here at NEWSDR, they will pay for your radios. There's cash prize for winning, and they'll sponsor you to fly to that conference to present your paper. And so if you are an academic, so this is really for the academic audience out there. If you're interested in this, reach out to Bob Lee at this email address on the screen. So take a screenshot right now. And and apply. The deadline's September 1st. And I will call out, this last year I was on the evaluation committee, and our known and loved Professor Alex Wiglinski came home with the gold in the unconstrained category. Congratulations, Professor.
Thank you.
So if we were in a big conference room, I would expect a round of applause for Alex and his team. Well, it was your good guidance, but your students did great work. They put together this kind of a LTE jamming test bed using open air interface. It was pretty impressive what they accomplished in that short amount of time. And usually we all get together to present and celebrate these accomplishments, but the pandemic this year, we had to do it all virtually. And so we all submitted like videos and did an evaluation. But so I encourage you to apply. Alex needs some competition. He get in there and compete with Alex, dethrone him from his win this year and whatnot. So the last thing I will say is, as my time is running out, is, I do encourage you to come by our virtual, quote, air quotes, virtual lunch open tables in the Zoom room. I'll have a couple of videos to share. We will have Michael West is a senior R&D SDR engineer for open source tools. So Jonathan Penlam and the original RF NOC architect, Neil Pandya, who will be teaching the class with Jonathan this afternoon, and Sarah Yost, who's our senior business development manager. So let's get technical. We're very friendly. We like to talk nerdy about this stuff. Come in, let's have a conversation. Let's talk about your wireless application. Maybe we can help you out, steer you in the right direction. Got feedback, good, bad, or ugly. We love to hear all of it and have just engage with this community, because we really are passionate about this stuff too. And we appreciate the chance to speak, Professor Wiglinski, and are a huge supporter of NEWSDR and proud to sponsor this event. And so here's some ways you can reach out to us at edis.com, sales@edis, or you can email me directly. I'll get you connected to the right expert, to whoever you need to. I'm happy to do that for anyone on the presentation today. So thank you, Professor Wiglinski. Back to you, sir.
Thank you, Hayden.
Yeah.
Excellent talk, especially, and yeah, that actually one of the winning team, they're going to be poster P01, like Yaya is going to be presenting on that exact work. So So definitely people are going to have a great time asking how did that work, and definitely ask about the experience as well with NI and Air Force Research Lab. So thank you, Aidan.
Yeah, one last comment was that you will get access to AFRL SMEs as well as, EDIS support personnel and things of that nature. So we've been really supportive of these universities. So I'm actually going to have to come watch that. I didn't know that team was presenting today. Thank you, Alex.
Thank you. So with that, what I'm going to do is just to point everybody to the Slack channel. It is like on fire. So I I'm unable to keep track of everything. But if you do have a question for either Hayden, Mike, Henry, or Robin, please communicate that in the Slack under the NEWSDR-2020 channel. And I'll try and relay it. But maybe while, let me see if I can. So I'm going to. So Mike, Henry, Robin, and Hayden. Let me see if I can unmute. Can all of you talk? So Robin, can you say something?
Hi, can you hear me?
Yep. Hayden, can you say something?
I'm here.
And Mike?
Oh, say, can you see by the dawn's early light?
And Henry?
Yeah, I'm still here.
Excellent. So right now, I'm not sure if I'm getting any questions.
Well, there were definitely some questions about, maybe Mike, you could address about MATLAB and AI and some of the RF fingerprinting work.
Yeah, no, and that's the thing. Is that coming up? That's going to be at the noontime session, right? Like
it is in great detail. I mean, I can share a little bit about it right now. Sure.
Okay. Well, because the one thing is like we're running a bit behind schedule, so I just want to make sure that we're in sync with the schedule. Like unfortunately, I let it slip a little bit. But actually, there was one burning question, since there is a lot of chat about that on the Slack. So maybe, yeah, like let me think. Well, perhaps what I'll do is there's the big Q&A afterwards. We can save some of that questions there. But yeah, let's say if that seems to be omnipresent on people's mind, and then in the second Q&A we can ask more questions about also NI and MediaTek, if that's okay. But yeah, so what was the question? I'm just looking. Yeah, it's difficult to talk and read Slack at the same time.
Yeah, I think are you kind of suggesting you want to take a break here, give people a bio break, and then because Tom Rondeau is going to Dr. Rondeau start here in 5 minutes. That's exactly kind of where I think you're leaning towards.
So maybe while let's say before Dr. Rondeau's talk, how about this? Like, given the pandemic, I'm going to ask each one of you, what have your companies done in terms of so everyone's now at home, work from home, but more importantly, this is the burning question, right? We have a boatload of kids at home, everything from toddlers. I'm not going to count my 18-month-old, right? But we have elementary school kids, we have middle school kids, we have high school kids, we have college kids, we even have university grad students, right? Is there anything that each company is doing right now that or could be doing in terms of trying to keep these kids sort of engaged with their professional development, with their growth, especially in something like the wireless world? I know that's a huge question by itself. That's like a half hour, but so Mike, you mentioned Milwaukee School of Engineering. Robin, you mentioned our book that we wrote together. And Hayden, you mentioned that there's several educational activities that are being led by NI, right? Including this Air Force Research Challenge, which is really good at this time. Henry, obviously, there's a lot of material out online, especially for graduate students that they can look at with MediaTek. But in let's say in 30 seconds each, is there any where can you direct, let's say, the parent out there who has a kid that says, I would really like my kid to do something, right, over the next few months. So maybe what would you recommend to them in terms of SDR technology? So I'm gonna start with the order in which we presented. So maybe Robin, 30 seconds. Where would you direct those parents to?
Well, so I think it depends on their level of competence. I think that there's a lot of great things online. SDR has become much more accessible in the last 5 years, especially with things like RTL SDR. And tools like the interactivity with like Python and MATLAB and GNU Radio, which can decrease the cost for a lot of parents because they want to play with things without investing a lot.
Okay.
Or maybe that's just me.
No, that's really but that's really fair because like like there are a lot of kids out there that like already in Massachusetts there are some schools that are saying like no, we're going completely online, and that's like and that's across like the spectrum, right? The spectrum. But in all seriousness, like what are opportunities for them to grow even in under this
Absolutely.
environment?
So I think that we actually run a virtual classroom on analog devices support forums, as I'm sure MathWorks and NI does, where people can come ask our engineering teams, questions about how to get up to speed and these kinds of things. And I would definitely say, reach out and try and use these resources that are available for people.
Cool. How about you, Mike?
So if you're wanting to get started on the ground level, there is a MATLAB on-ramp that is a self-paced online class. Take you 2 hours to get through, and you can learn the basics of MATLAB, even if you're 13. From there, we have a similar Simulink on-ramp, and if I'm not mistaken, a deep learning on-ramp. And I would also echo Robin's comments about the RTL SDR. You can literally get going with the RTL SDR in 30 minutes. I've gone to many, many different schools and conducted workshops where we download, they got MATLAB installed. We download the support package, the software. We give them RTL SDR radios, and they are off and running, getting FM broadcast and tracking airplanes in 30 minutes.
Wow.
So that's
awesome.
That's about as easy as it gets.
Right.
That's awesome.
But that's about as much as you can do with an RTL SDR.
I agree. Oh yeah. We're not talking about.
No, but I
think
like,
aping for me.
You want people to grow up to different things, including like the things that we provide or the things that NI provides and those kinds of things.
Yeah.
Yeah.
So how about you, Henry?
On mute.
Oh, sorry. Did I? Let me see. There we go. There we go. Sorry about that, Henry.
I guess as a company, maybe I should say everybody should go out and buy more 5G smartphones. But from a personal side, I have a high school student, and actually he's found some local college classes, that he can take, and I think your basic skills, I think, are still really important. Basic math skills, et cetera, are probably the best thing that your kids can do. I think that playing with hardware devices and playing with tracking aircraft, or reading all the tire sensors as cars come by on your street, and then figuring out who's driving every day, all of that is good from a perspective of inspiring kids to say, oh, this is cool, I'll go mess around with it. But I think that my personal observation is that I have seen a number of job applicants who will claim, for example, experience with LTE at the time, right? And in fact, what they knew is how to hook the various different components from in a MATLAB model together to do whatever, but had no idea how any of it actually worked, right? So if you go and so for what we actually need, or what we do, to say, well, okay, so the simulation performance totally sucks. How are you going to make that go faster? You get a ba-ba-dee, right? Or, okay, well, we need, somebody to work on, channel coding. Can you explain, how the decoder works, right? Can you, and the answer is b-ba-dee, right? And so, I think that the inspiring kids is really good, but I think that focus on the fundamentals is actually, if you really want people to be able to do the job in the future, that's the part that's really important. Perfect. In my opinion, right?
No,
and so,
but this is very insightful, because I think the thing is, like, honestly, like, unfortunately, I don't think we have. Well, I think we're all parents, right? But imagine the greater masses, like, people saying, what do we do and stuff? And it's like they're turning to teachers and teachers saying, here's a package, come to me next week for the next package. I think something like this, or if you homeschool, or if there's an online academy or something like that, like I think that this type of insight's really important. But no, this is good. This is really good. Hayden, how about you? Your perspective? I mute you. Oh my God, I'm just muting everybody today. There we go.
I think I muted myself, so it, I guess for me, NI has been really helpful in this pandemic of allowing us to work from home and giving us time to work from kids, work, take care of our kids when they're in school. But, here, come here. I've been trying to get this guy right here involved in some radios, but we just got to talk him into it. So this is Kai, but.
How you doing, Kai?
Yeah, so Kai, come up here. So he I really am passionate about getting people interested in, kids, especially my own, interested in STEM from an early on. But yeah, it's all about like finding that fun little thing to do with it, but we've at NI been focused on like people using the products and getting the fundamentals of the radios. But it is, academic is something we've always, been a big, proponent of at NI because, we kind of came from academia, but yeah, it's super important. And we're building this courseware right now. We have some of it. So those are some of the things we've been doing. NI has been super supportive of, us in this pandemic. So anyway, I'm excited to hear Dr. Rondeau's presentation.
Yeah, no, perfect. No, so first of all, Robin, Mike, Hayden, and Henry, thank you again for your time. All great talks. I think there was very informative. We're going to have a lot more. Like a lot more of a Q&A after Dr. Rondeau's talk, as well as the two remaining companies as well. So a big round of applause. So and the other thing is that, again, the Slack channel is like on fire. So I don't think I can multitask typing and talking, but nevertheless, there's a lot of good questions there. So we'll definitely continue the Q&A after the second sponsor talk session and the keynote presentation. So speaking of keynote, so thank you. I'm going to put you all on mute and then unmute Dr. Rondeau. So, but thank you. I just muted myself. Oh, there we go. All right. So with that, I would like to welcome Dr. Tom Rondeau. So I'm just making co-host. So welcome, Tom.
Hello.
Hey. So I'm gonna so first of all, like I'm gonna read your biography because it's really impressive, and just like let the entire online audience, which right now, like live streaming, we have 118 people like are just watching right now, minus a 20-second latency, like a delay. So that must be an FCC rule or something. Right?
So you can bleep me out when I go off script.
Yeah, exactly. It's like, and I have another thing. Please stand by, So we're very honored here today at like NEWSDR 2020 to have as our keynote presenter, Dr. Tom Rondeau, who is a DARPA program manager who focuses on adaptive and reconfigurable radios, improving the development cycle of new signal processing techniques, and exploring new approaches for the applications of electromagnetic spectrum. So prior to DARPA, Tom was the maintainer and lead developer of the GNU radio project and a visiting researcher at the University of Pennsylvania, as well as an adjunct with IDA Center for Communications Research in Princeton, New Jersey. So on a more personal note, Tom was actually our first keynote speaker at the first NEWSDR, if I remember, in Boston. And I was actually able to find a photograph, but I was like saying, should I put this side by side with the current photograph? I'm like, but I mean, what better way to celebrate the 10th anniversary than sort of an awesome keynote presentation. So with that, Tom, thank you again for joining us, for giving the keynote presentation, and again, welcome to NEWSDR. So
thank you, Alex. So I'm going to share my screen. I pulled down my presentation here. Let's hope this works. And all right, Alex, you seeing it in full screen mode?
Yep, we're good.
Perfect. So yeah, so it's been 10 years since I keynoted the first one. So I have a little bit of a running joke here. For those of you who are sci-fi geeks like I am, maybe you recognize the title here, Got to Get Back in Time, the Huey Lewis and the News song from Back to the Future. But I also want to warn everybody, you know, it's been 10 years. I got a little rusty at this. So if you thought my first keynote was great, just remember that lightning never strikes twice. I'll do my best. But we want to review some of, not real, well, I want to explain to you what I've been doing at DARPA, frankly, for the past, I'm in my 5th year there now. I was with the Microsystems Technology Office, and now I'm with the Strategic Technology Office. I just switched roles back in May. So the programs that we're going to talk about span both of those. But if you're familiar with GNU Radio, you just heard from National Instruments, I saw. And so, you know, with GNU Radio, with the USERPs, with the technologies that have been in the works over the past few decades in this real software-defined radio focused world that we're in, you'll see a lot of similarities, or I guess a lot of the motivations to where these programs are coming from.
Tom,
yeah.
Sorry. Yeah, no, it seems like the presentation slides are no longer in full screen. Like, I'm not sure. It's in PDF, right? So well, let's see. Sorry about that. Yeah, no, if there's like another view setting.
You know what? Let me stop sharing. Okay. I'm going to put it into full screen mode and then just try to share that mode.
Yeah, that might. Yeah, Zoom is a funny little beast. So.
And it looks like.
Oh, perfect. Thank you.
Great. So, but I want to kind of set the stage for what's been percolating in my mind for a while, and really kind of hitting home with again, keeping with this theme of Back to the Future. One of my favorite movies. My license plate was actually 1.21 gigawatts back in high school, so longtime fan. But I was just actually fairly recently rewatching Back to the Future 3. And this, when they're reading out, if you're familiar with the movie, right? Doc gets sent back into the Wild West, sends Marty in the future a letter, and he goes and finds the 1955 version of Doc, and this is them reading the letter. And one of them, it just struck me as interesting, what I highlighted here in red, that he's working as a blacksmith back in the Old West. He's trying to fix the time machine, but unfortunately this proved impossible because suitable replacement parts will not be invented until 1947. And I thought, well, that's a very specific year. What happened? And then, of course, it struck me because I've been giving a talk on exactly this problem for the past couple of years. I first created it for keynoting the IEEE Radar conference a couple of years ago, where I was trying to motivate people in the radar world to start thinking like software-defined radio people, where we changed the approach to communications by thinking about it from a software first and really from a numerical processing first. So it struck me as how interesting and specific this little call out was. So what happened in 1947 that could possibly make time travel possible? So skipping over some of my step-by-step through the timeline, the history, what I did is I went through a history of computing and a history of radio. And I noticed a really stark point of contrast between those two histories. And so instead of trying to do the build like I normally do, just so we can get through this, let me just show you the full timeline. We go back, or I went back to Lovelace and Babbage doing some of the early computational sciences. And then there's almost nothing for a while until really, there's some mechanical devices being made, calculators, but it wasn't until the Turing machine really codified what the theoretical mathematical concept of a computing machine was in 1936. But you also have Maxwell's equations in the mid 1800s. And then there was a lot of work being done by people who called themselves Maxwellians, and you had the Hertz experiment, you had Marconi in there with his patents, you had the super heterodyne receiver, all these really amazing inventions. And then you can kind of see this dilation happening right around that red line that I drew when the transistor radio came out in 1954, the same year that the transistor computer, the TRADIC, was the first transistor computer, comes out the exact same year. And ever since then, the computing world has exploded. The radio processing world kind of slowed down in invention. There was a lot of good engineering. I'm not trying to minimize the impact of the engineering work that went into creating SATCOM and cell phones and Wi-Fi and all those things. But when I look at this, there was less dramatic invention, new theoretical modes that came about. I have a much more complicated version of this diagram, but this is just to try to show you where I think some of the gaps were in this time period. And I really think that software-defined radio brought us back to some of those early days of exploration and experimentation, that quick ability to explore the world of electromagnetics. And that's my running tagline here, is that software-defined radio is programming the electromagnetic spectrum. And it's a nice tagline, but when you really think about the power that shows us, this is me and Ben Hilbert and a few others are now tagged with saying this, right? This is one of the 4 fundamental forces of the universe, and we're writing Python code that allows us to manipulate it. I think that's a pretty awesome thing. But what happened was in 1947 was the demonstration of the transistor effect. And that was the change. That was what Doc Brown was referring to in his letter. And that was the change that made, in his mind, time travel possible. In my mind, though, the transistor is what's made computing possible. But if you think about it, its invention was around being an amplifier for radio. It was never meant, really, to be the foundation of computing that it turned into. And frankly, it was 2 of Claude Shannon's ideas that really came into this. In his master's thesis work, Shannon's master's thesis, which is considered one of the most influential master's work of all time, he demonstrates the use of Boolean algebra to mechanical switches. That brings back this idea of Boolean logic that was almost lost. So we think of it as a given today. But it wasn't well understood. It was almost lost until Shannon kind of revived it and said, hey, we can use these switches to compute Boolean algebra. Then the transistor is invented, and then we figure out, well, that's a great switch. Let's apply Boolean algebra to that as a switch. That allows us to explode this realm of invention and computing science. Shannon's also credited with his famous essay, A Mathematical Theory of Communication. A wonderful paper if you haven't read it. And if you're listening to us now, I say you probably either have read it, and if you haven't, I highly recommend it. It's very easily digestible, frankly. But this kind of teaches us how to think about communications from a very fundamental mathematical perspective. And the transistor opens that up to us. But when you think about it as a black box of a switch that's either on or off, that's a fairly easy representation of the transistor circuit, and allows us to build computers and computer chips and all the way up to our smartphones and our embedded systems today. When you think about it as an amplifier, the math is much harder. If you've ever built around a transistor, it's not quite as easy as thinking about it just as a switch, but as an amplifier and all the effects that you have to control to do that. Really tie this black box into this very specialized computing world. But when we move that to software radio, where the software radio is processing on a transistor to manage signals that are captured through a transistor, there's this synergy here that I find incredible and also inspirational. And so that's where the software-defined radio world is bringing these disciplines together and helping us expose and increase our ability to access and manipulate this force for all sorts of things. And so what I want to talk about in this presentation are 3 of my programs at DARPA that I think that I'm trying to use to push the technology to make sure that we're constantly making revolutionary investments in revolutionary technologies to take full advantage of what I just talked about here. And so we'll talk about a program called Hedgehog, which some of you, if you've been to the GNU Radio conferences in the past, have heard some about, and I've got some good news on it. SDR 4.0 and the domain-specific system on chip. So let's go into Hedgehog. So this is what I call the next generation software-defined RF platform. This is the high-level, almost slick sheet concept behind Hedgehog. It is a combination of 2 technologies that DARPA created or invested in, I should say. One is this, on the far left-hand side, this matrix RF FPGA. This was a DARPA program, the RF FPGA program that I ran, that it created this building block structure, like an FPGA-like structure of analog components, mixers, amplifiers, oscillators, filters, all inside of a programmable switchable fabric that allows you to access a massive amount of spectrum and manipulate it in many different ways. Hedgehog has taken that idea and amped it up to another generation of transistors, fundamentally. So a new process node that we're utilizing, and that's helping us push this chip to be able to cover 40 gigahertz of spectrum. So you can tune this device from basic DC to 40 gigahertz. Instantaneous bandwidth of the chip itself is 4 gigahertz. Now we have a commercial variant of that. There are regulations involved here. So our commercial version allows us to go to 500 megahertz per channel. You can also have multiple channels in this thing. So we can have 8 simultaneous functions running across this board simultaneously. And all of this was because we were integrating this RF concept of a switchable fabric with digital concepts of digital fabric. So working with Xilinx and co-investing with Xilinx to create the RF SoC, we created an FPGA, really a system on chip, because it has FPGA logic and ARM processors, as well as integrated analog to digital converters and digital to analog converters. So if you match 4 of these matrix chips with one RF SoC, you now have this multi-channel, large instantaneous bandwidth sweeping over a very large spectrum, now integrated onto a single platform. So we've got the 4X variant, or the quad variant, on the left here. I'm also showing you the Hedgehog Solo, which is we wanted a smaller form factor, so we have 1 matrix chip there. So it's smaller channel count, but much better form factor for use. And then down on the bottom here, we have the matrix chip itself. So this is a silicon germanium process that we package up onto this interposer board with RF connectors on it to marry into the digital processing. So this is a platform that is serving our needs in the DoD. But I'm excited that, and frankly, inspired by the flexibility and the ideas that happen when we start thinking about access to the electromagnetic spectrum. There are more knobs to turn in this device than could ever be explored by a single person in a lifetime. 2 to the 300 is roughly the number of states that you can switch the matrix chip into. And now you have 4 of them, and you have the digital logic. So what do we do with that? Well, I don't think we're going to figure that out by keeping this as solely a military capability. So we do have a matrix chip that is designed for export and for use in research labs. It's been certified by the Department of Commerce, and we've built those chips. We are now in the process of actually building hardware, building the Hedgehog hardware around these commercial variants so that we can get them out to folks outside of the DoD and outside of kind of ITAR restrictions. In fact, I'm really happy to announce we just got them on contract two weeks ago. Software Radio Systems, SRS, Paul Sutton and Ishmael Gomez between Ireland and Spain. We're working with them on some 5G development work, and they'll be porting that work onto the Hedgehog devices so that we can have the 5G waveforms, UE and to a limited extent the G-Node Bs operating on this kind of hardware. And so we're producing the commercial variant of these to support that operation. For those of you who have been familiar with Hedgehog, I think we had 2 years ago, we had a talk about it at GRCon. We are now producing the final boards. So at least within the DoD version of these boards, they are being produced right now and are going to be distributed to a lot of our partners that have been working with us on this. Turned out, it's delayed, but it turned out that fitting 40 gigahertz into a single chip was hard. So it took us a little while to get the process right, but we did, and I'm excited that they're now being produced. And so my joke here is that Hedgehog covers all the Gs, and so you can see down the bottom there, 1G through licensed 5G. Although I was upset when Julie Knapp told me that they were trying to open up some spectrum in the 40 gigahertz range, which kind of ruins my tagline here. But we're pretty close to covering a lot of the cellular bands for work, and I think that's where the Hedgehog device, with its tunability and multi-channel access across from the low, mid, and high band of 5G communications, could be an exciting platform for us to study how to utilize the spectrum appropriately. Like, this is a backpackable solution for doing channel propagation analysis at 20 gigahertz, for instance. I think it's pretty exciting. So that's the background of Hedgehog. Just to, the other aspect that I was focused on in the program was its programmability. I don't believe in building silicon that you can't use. So we made sure to work with National Instruments on the UHD interface, making sure that UHD and RF NOC could be supported on the Hedgehog device, so that all of the tools that we know and love that understand how to talk UHD from GNU Radio, from MATLAB, LabVIEW, any of those tool sets that and development frameworks that we use to build our applications, I didn't want to have to throw them out the door and start from scratch to reprogram this thing. So that's another feature of this program is figuring out how to tie these together. Now, of course, the challenge is if we're pulling in hundreds and depending on your capabilities here, possibly gigahertz of spectrum simultaneously, how to process that is going to be the next challenge. And so that's really where the next couple of talks are going to focus on. So let's get into that. What we came up with was working with the GNU Radio world for, I started working with Eric Blossom and Matt Edis back in 2004, I think was when I first contacted them. I've been running it, or I ran it from 2010 to 2016 when I entered DARPA, and still been, keeping involved with the community as I can. One of the big outstanding questions that we have is, how do we modernize the scheduler within GNU Radio? How do we take that framework and really make it applicable and deployable across modern compute systems, specifically heterogeneous processing? And so SDR 4.0 is looking at kind of the history of, when you start with software-defined radio, you can really go back into the 70s. The early DSP work was kind of the foundation of software-defined radio. Then you basically had Speakeasy and Joe Mottola and the work that was done under those programs and kind of JTRS growing out of that. But then you also had GNU Radio, which was coming at it from a very different, very ground-up perspective. And I think we fundamentally changed how we think about signal processing and accessing the spectrum. But now is the next iteration of this, which is to, like I said, take advantage of heterogeneous processing. And that's why I call it SDR 4.0. Nicely, it just happens to match the work going on in GNU Radio to develop GR 4.0. And you just heard from National Instruments with UHD 4.0. So we're all kind of at this 4.0 stage, and maybe someone will figure out how to integrate it with Industry 4.0. I don't know. So what we're doing in this this program is bringing in expertise in mostly FPGA processing, but really heterogeneous processing in general, and trying to marry that with the GNU Radio scheduler. So whereas our previous attempts at this have been fairly clunky, we want to work directly with the GNU Radio Foundation or GNU Radio project team, I should say, to integrate this as a first order principle within the next generation scheduler. So we should be able to increase our signal processing capabilities, our end-to-end speed, hopefully reduce a lot of latency, and just make sure that we're taking advantage of our processor resources as GPUs, FPGAs are really getting integrated into system on chips, or at least system in package kind of ideas here. So we're hoping to get a pretty significant improvement in the speed of GNU Radio without having to do a whole lot more work from the user perspective. So I want the users, the application developers, to still focus on their, the GNU Radio companion, dropping blocks down on a canvas, and just thinking about the math processing required for the application space. And let GNU Radio understand how to dispatch that to the different heterogeneous processors underneath. So you have CPUs, central processing units, or general purpose processors, whatever you call them. These are good for any kind of computation, right? This is the Turing machine. It can compute any computable number. It just doesn't necessarily do any of it particularly well. There's no guarantee that it's the right model for any type of math operation. You've got GPUs. Everybody loves their GPUs. You've got 10 teraflops in a package with a cool GPU. But they don't do all flops equally. It's really good for dense linear algebra processing. So when we have dense linear algebra processors, we want to be able to offload it to GPUs. Then you have FPGAs, dense I/O, that compute fabric for high parallelization. Again, it's not the right compute model for every problem, but it's really good for a lot of problems. We're trying to pull these together under GNU Radio and be able to target them. So we're working with folks, like I said, who are specialized in FPGA processing as well as GPU processing, and engaging with Marcus and Bastian and Josh and the core architecture team behind GNU Radio to make sure that what we're doing is relevant to the problem space, and as the ability to transition into the core code as we develop it. So we're fairly new in the program. This has been going on for just about 4 months now. The main team, this group Black Links that's mentioned here, they're due to brief me on their phase 1 kind of study phase of what they're going to do within the next couple of weeks. So we'll really get a feel for what's going to happen here. But fundamentally, I'm pretty excited about this because they've already shown the ability to offload LDPC code to an FPGA and get a pretty significant improvement in processing speed there. What's nice is they're also targeting the ultra-scale RF SoC. So that's if you remember from 5 minutes ago, that's what I talked about as the core processor for Hedgehog. So the RF SoC is a component here that we get to utilize for many different purposes, and we're targeting it as our example FPGA, not as the only one, but at least as an example. And then working with the GNU Radio community to focus on things that are more like the standard Zinc processor, which is a little bit more cost effective and available to more people. So we're trying to balance this kind of exquisite, more expensive capability with a little bit more of accessibility to the community as a whole. And then simultaneously, we're working with the teams to look at GPUs as well, so that we have that as an offload capability. And so together, we think that we're changing the way that GNU Radio processes the signals and how to dispatch it to these heterogeneous processors. It's been on our minds for a long time. Marcus, Bastian, myself, Matt Edis, Ben Hilburn, all of us have been talking about Jonathan Corgan, I need to credit him as well. These custom buffers in order to manage this. We're finally, I think, putting the attention and the engineering talent required behind those ideas to make it real. And so we hope that comes out as part of our program, as part of GNU Radio 4.0, as a new way of scheduling these tasks. So now, regardless of the underlying hardware, so I'm excited that this can match with Hedgehog. Doesn't have to, right? That's been a very important perspective of GNU Radio from the beginning. Matt Edis and the National Instruments folks creating the usurps as closely coupled with, but not dependent on GNU Radio, and GNU Radio closely coupled with, but not dependent on usurps. We want the same thing here. So we're trying to make GNU Radio a more powerful tool for really today and future signal problems. Well, if we had, as we've invented new ways of accessing the spectrum, getting access to gigahertz, simultaneously gigahertz of spectrum and all over the DC to millimeter wave. And as we're talking about restructuring the frameworks of heterogeneous processing, the exciting thing that this next program here, domain-specific system on chip, is trying to solve is, what does the next generation digital processor look like that takes advantage of both of these, or solves the problems of both of them? One is we have too much data to process. One is we have a flexible processing environment that doesn't have the hardware to support it. DSSoC is creating a many-core heterogeneous processor and how to program it. So that's important to me. Back to that, I don't want to build silicon that I can't use. When we kicked off this program a few years ago, the joke that I made out in San Jose was, if you give me a processor without a compiler, you've just handed me solidified sand. And that's all it's good for. It's just looking pretty. Can't do anything with it unless we have the software tools to support them. So this wasn't trying to build a new processor for the sake of a processor. It was trying to build new processors that we can utilize and apply to many different problem sets. So what does this look like? I called it the domain-specific system on chip because we want to build functional or programmable processors that are also specialized and are high performing in their areas. So I was asking the community to build us a processor that's optimized for speed and programmability. Usually those things don't work together. Usually we have ASICs that are really good at their job, but they only do one thing. Or maybe you can parameterize them, but you can't program them. And then you have FPGAs and CPU or GPUs and DSPs somewhere in the middle there. And then you have CPUs, which again, can process anything, but can be programmed for anything, but doesn't necessarily do anything particularly well. So why am I asking for both? Why do I think we can get both? And the thing that I'm giving up is kind of the full universal processing problem. I'm not trying to make this the next Intel platform or x86. It's to scope to a domain of interest. I don't want to build it so tight that it is only good for a single application, and I don't want to build it so broad that I can't make use of specialized silicon to process the math. So if we scope it to a domain, such as software-defined radio or image and video processing, there's different domains that we can identify here. And then what we wanted to do in this program, some of the hard questions that we were trying to answer in the program is, what constitutes that domain? What kind of specialization is required for that domain? So if we're going to build this kind of, like the cartoon that I have on the slide here, is these different colored blocks that are representing different types of processor elements. Some of them could be general purpose so that they can kind of do the bookkeeping. Some of them can be highly specialized, like Fourier transforms. Some of them can be more, like GPUs or DSPs that are kind of somewhere in the middle. How do you distribute those kinds of processor elements? How do you understand which processor elements you might need for your domain space? So that's one thing that we're challenged with. The second thing is, if we have a system on chip that has dozens to possibly hundreds of processor elements in them, how do you program that thing? How do you leverage all of those cores underneath there? Today, we'd be very manual. I call it plumbing. We're basically our embedded processing on system on chip today is plumbing. It's somebody's in there trying to figure out how to move data from one processor element to the next, and try to hide the latency as much as possible. And it's a very manual, very time-consuming problem that only experts are good at. So we're trying to figure out, how do you actually program this thing and lift the burden of the specialization of the processor away from the application developer? As I've been saying about this program, I want developers to focus on math and applications and not on the hardware. So those are the two challenges that are being addressed in this program. So how we're doing it is a very iterative process. It's a kind of double loop that you're seeing under here. And if you're familiar, this is a variant of the OODA loop: observe, orient, decide, and act. It's a very good model for trying to figure out, okay, what's my domain look like? How do I figure out how to scope that down to a processor that I can build? Let's build the processor, run applications on it, and observe what's happening on those to readjust and to specialize or to optimize for the next round. Meanwhile, you have the inner loop here, which is the software. Software is always running much faster. So we're going to build programs, compile them down to the hardware, schedule them on the hardware, execute the applications, measure performance, and use that to feedback as feedback into our programming and our compiling system. So our compilers are now solvers as well. They're high optimization tools that are looking to have more input coming from execution of the programs than they are currently. So what I scoped out here for the program were kind of 5 technical areas, but if you're familiar with DARPA programs, these weren't different TAs. This is everybody had to come and solve all 5 of these in a single effort, because they're also interconnected to make the system workable and possible. So I mentioned, how do you schedule, or how do you avoid the manual programming of the underlying hardware? That's what we call the intelligent scheduler. Can you, and this is what's fun about it, is for multiple simultaneous applications running on an embedded processor, trying to access different processor elements for specialization of their math goals. How do you identify what processor element is required, and how do you assign it based on contention with other processors? If you think about it, I'm effectively asking us to solve a variant of the traveling salesman problem, as well as a variant of the knapsack problem. And I'm asking you to do this in 5 nanoseconds per decision. So you have to solve an NP complete problem in 5 nanoseconds. I feel like that's what we call DARPA hard. The next one is software. You got to be building the software for me: compilers, linkers, debuggers, those types of things. And it's really exciting to work with Arizona State. They're building these fat binary concepts in their compiling tools. We're working with University of Illinois Urbana-Champaign, so Vikram Adve and Sarita Adve. They're the inventors of LLVM. They're now doing the heterogeneous processor virtual machine. So we're really pushing some of the compiler tools to think about this problem space and how to attack the heterogeneous processor problem. I talked about, how do you design the specialization for your domain? That's an ontology problem. It's trying to identify what key kernels, what math kernels exist in your domain area, and how do I map those down to underlying ASICs or specialized components within my SoC, and how do they relate to each other? And then we actually have to build the hardware. So I called it the MAC, the medium access control, kind of coming from my comms theory background. We're building network on chips. We're pushing the network on chip technology to make sure that it's fast, low latency, so high bandwidth, low latency, and power efficient. So power is a key metric of the MAC. They're all network on chips. I didn't want to call it a network on chip because I didn't want to constrain the thought space if somebody had a unique solution there. But right now we're really focused on the NOC concept. And then finally, build me a chip. So this year we're just moving into phase 2 of the program. And this is the phase that the teams are going to build hardware. So we should have prototype silicon within a year to test So to go over this program a little bit more in depth about where we are, what we've accomplished, as I mentioned, the DARPA hard problems, identifying what we accelerate and how to accelerate it, that scheduling problem and how to schedule things in nanoseconds, and how to create a programming environment that is suitable for heterogeneous processing. And so over the past couple of years of the program, we're showing our ontology tools as the ability to automatically discover in the binaries, or really in the intermediate representation of the compiler tools that we have, and how to map those to the accelerator functions. And that's teaching us more about what kernels actually mean. So we have a new idea of what a kernel is. I can say an FFT, but it's not just an FFT. There's so many surrounding elements to an FFT before you actually utilize it. We actually maybe want to bundle those together. So what is the kernel? What's the code telling us about the specialization and how to map it? The next one is these runtime schedulers that are matching and often being better than the best human optimizers. So we often bring in an expert to sit down and work through our problems, or ninjas. We often call them, use the term ninja, and I like it because ninjas are hard to find and they're really expensive. Well, if we can avoid the costs and the difficulty in hiring them by automating this through the tools, even if we were within a few percentage of the best human optimizers, I'd be happy. We're actually on par with and often better than all the time that it takes for a human to optimize. So we're building that out. And what that leads to is different companies that I'm working with on this program, their internal analysis is showing that they're 40 to 100 times better programmers. So they can go from problem to solution almost 100 times faster with this model of programming than with the previous approaches to FPGA build and design and dispatching. I mentioned that we're building these network on chips, so these on-chip interconnects. So we're building these high bandwidth and low latency, and we're reducing the power. Right now, a NOC can consume about 40% of the power of your chip. We're trying to push it down at least below 20%, so that you're not using all your power just to move your data. And finally, we're working with a number of groups out of Columbia, as well as, again, Arizona State, working with University of Michigan and ARM, to build new accelerators and be able to integrate them with your silicon much faster. So those are some exciting accomplishments that we already have. And as I said, this year, we're going to prove it out with building actual silicon. So what does this lead me to? I spent time talking about the DSOC program. I tried to walk us into it with why it's necessary, like where it came from in my mind from a software-defined radio perspective. So hopefully it makes sense. There's much more to talk about. There's so many exciting things going on there. But to kind of raise us back out into why is this exciting for the future of where we are with technology and where technology is going. And so I put this together for our ERI summit. So DARPA's Electronics Resurgence Initiative we kicked it off a couple years ago. We have a number of programs that are helping to try to adjust the way we think about technology in a post-Moore's Law era. We're having our next ERI summit next week. Hopefully some of you have signed up for that. But this comes from that motivation of, okay, what does the future world look like as far as communications and processor requirements? And the two are intimately tied together. So over the next few years, we're going to see the deployment of 5G systems under release 15. We're going to solidify release 16 and 17, and those are going to be slowly deployed over the next 10 years. And they're promising all these really incredible ideas that can be supported on a high bandwidth, low latency wireless network. Localization, ultra low latency communications for robotics and kind of assembly line manufacturing, massive IoT, industrial IoT, again, back to that kind of factory model of automation. I call this enhanced auto, but this is autonomous vehicles and vehicle-to-vehicle communications. Wearables, I think, are on the precipice of showing their real value. AR, VR, and drones have been in more of the hobbyist and gamer community, but I think when you have a network that supports the latency and bandwidth requirements, you start to identify what those key apps, those killer apps are that support these types of ideas. Well, the problem is we'll have the network to support them, but most of them are going to be not plugged into wall power. So you have a battery problem. So you're going to want to do more processing and less power. And so you need these kinds of innovations in our processor technologies. And while we're pushing into 5 nanometer transistors, and there's continuous push into getting smaller and smaller, we are really running out of space and cost. Moore's law, if you actually look at it, was a cost analysis as much as it was just a transistor size, feature size. We're running out of that. And as I joke, I stole it from a friend of mine who stole it from Churchill. The money's run out, it's time to think. So if we're lacking just scaling as our way to get to this future, we need to rethink what our architectures look like, what our deployment strategies look like, what our software stacks look like in order to support high performance capabilities on lower power platforms. And so that's where a lot of the technology is really going, is I think codified in this vision here of opportunity with constraints, and how do we solve the technology to match those constraints and build the future that we want. And with that, I'm gonna cut it off. Let's see, I'm 5 minutes behind my scheduled time, but Alex, I don't know if we want to open it up for questions.
Yeah, no, I mean, thank you, Tom. So I think everyone, if they could, they like online, like, you know, again, the Slack channel has been, like, I think I've been seeing a lot of discussion about a good accelerator and what makes a good accelerator. And I think there's some questions. The Q&A is going to be after the 2 remaining sponsor sessions, but like the 2 sponsor talks. But yeah, no, I mean, already I have like 2 questions lined up already. So if that's okay with your schedule.
Very good. Yeah, I can stick around. Well, actually, I do have a hard stop at 12, but I'll stick around.
Okay. No, that's when we're stopping too. So okay. Okay. Thanks, Tom. Thank you. Excellent talk. Okay. So with that, what we'll do is we'll switch gears again to in this case sponsor session 2, and you know, we're really happy to join with us today for the first time, and even despite pandemic. The folks from Link, and you might say Link, like, what is this company? What do they do? And such. And after talking with several folks from Link and looking at their website, it's pretty darn impressive stuff. So with that, we have with us one of the members of the core leadership team. I think it's the CTO of Link, Dr. Ty Speidel. So. Doctor, welcome to NEWSDR.
Hi, yeah, it's great to be here. It's, as you said, my first time. It would have been nice to do it in person, but happy to join virtually. I will correct you. I am unfortunately not a doctor, but thank you anyways. I like to think of myself as, you know, a relatively intelligent guy. Yeah, so I've got a presentation prepared. I know I only have 15 minutes, and
Yep.
I assume that's all right if I go a little past the original 11:30.
Yeah, just a little. Yeah, and I made you co-host, so you should be able to share it.
Okay, great. Let me go ahead and do that.
There we go. Okay.
So, yeah, as I mentioned, I'll try to go quickly and as a way of an introduction. So yeah, my name's Ty Speidel. I'm one of the co-founders of Link. I'm actually responsible, one of the technical co-founders. So on the technology side, I'm responsible for a lot of our intellectual property and the patents behind the secret sauce for how it is we're going to do what I'm going to tell you about today. I will caveat that with I'm not a software-defined radio engineer. My training and background is in space systems, mechanical and aerospace engineering from Cornell. And so I came into my career really as a satellite guy, and now happen to be putting that technology to use in the communications application world. And somewhat of a self-taught RF engineer. But at any rate, my goal here is to disseminate some information to folks in the software-defined community or software-defined radio community about our project. And hopefully you find it very interesting, and hopefully you find it so interesting that maybe you have some ideas, hopefully interesting questions, and maybe you even want to get involved. And we're always looking for folks to join our team, small startup at this stage. And so the thesis here is Link is building a a satellite constellation in low Earth orbit comprised of small satellites, microsatellites specifically, that are designed as networks in a box, cellular networks in a box that can deploy anywhere from 2G, 3G, 4G, or eventually 5G technologies from orbit that provide direct to handset connectivity. So, the classic paradigm in satellite communications is this here shown on the left, where you've got a satellite phone or a satellite terminal, which is uniquely designed, and often the protocols are unique as well as the hardware. And they speak to satellites, and then your cell phone that you carry around in your pocket and use most abundantly, and is actually less costly from a subscription perspective, speaks to cell towers. And there's a lot of friction with this model. Satellite phones have been adopted on pretty meager basis, and often are mostly adopted by military entities or government entities who have deep pockets. And the fundamental drive here at Link is to find a way to connect the world in a meaningful way that is a bit more commercial, a bit more focused on the end user, and ultimately is compatible with the existing device that you have in your pocket, and is also compatible with your existing subscription. So the future is going to look a lot like this here on the right with Link in it. Where you can take your standard cell phone, and as you're, running around the city or even in suburban areas where you have a good cell connection, you maintain your terrestrial connectivity. And then when you step outside of that terrestrial connectivity, our satellites fill in all the gaps. And they fill in all the gaps almost as a roaming provider might, when you travel abroad or you're not connected to your home network as you would be in the United States. In a similar way, you'd effectively be in kind of like a national roaming kind of configuration. And so this technology is very powerful. When you look at the economics of this, and you put an eNodeB or you put a BTS in orbit, you can provide a lot more coverage. And so for each asset on orbit, and in some cases it can act as multiple eNodeBs, but you get 4 orders of magnitude cost reduction in cost per square mile relative to a terrestrial tower. And so this is the classic problem in today's telecommunication industry. Networks want to promise this ubiquitous coverage, and they put out these beautiful coverage maps that are often can be a bit exaggerated. And they have a real problem with providing coverage to the last mile, to the rural areas of the world and of the landmass, and inclusive of the water, where there aren't a lot of people. And because of that, there's not a lot of revenue density. But if you reduce the cost per square mile to cover that square mile, then you can make a profit on very low population density areas around the world. And so this gap filler theory on a global scale represents a large opportunity. And so to do this, we leverage a little bit of secret sauce, our patented secret sauce, and also commercial off-the-shelf materials. Of those are small satellite hardware, and that is comprised of things like processors, FPGAs, specifically on maybe a software-defined radio. We play around a lot here at Link with agile development and tinkering and testing. And so we have taken it upon ourselves to evaluate a suite of commercial off-the-shelf software-defined radios and fly the ones in orbit that we like and space qualify them. And to this hardware, ultimately, we add our secret sauce, which acts as effectively modifications or libraries to a typical cellular mobile stack. So think a typical 4G or 2G, GSM or LTE stack. And we do ultimately 3 things. So the secret sauce, this is the patented secret sauce. There's actually a couple concepts for this. You could deploy this as satellites that, way back in the day were originally repeaters, where just, the base station effectively sits on the ground and then sends some RF up to the satellite, and it does some up converting, down converting, and then repeats it. And then, communicates with things on the ground. We've taken a different approach. It's a bit more attractive and more effective for our deployment of this application, where the satellite acts as a network in a box. And so the RAN, the radio access network, is deployed with additional Doppler and timing compensation, which is unique to the terrestrial network, where it's designed to communicate with cell phones that are anywhere from 35 kilometers away, moving at speeds synonymous with a bullet train. And those Doppler shifts and propagation delays just don't carry over to orbital trajectories. And so when you're in an orbital trajectory trying to provide coverage to a standard handset, you need to implement a Doppler and timing compensation component. And this is relevant to a repeater configuration or a network in a box configuration, and is defined in some of our patents. And that lives as software, and can be implemented on FPGAs as well. And then there's a virtual cell network in the sky component. So when you're flying these satellites in orbit, they're no longer the mobile network is actually flipped on its head. So now the phones, which are usually the mobile element in the network, are no longer mobile. The satellite in the sky, which is the base station, is mobile because it's moving so fast relative to the phones. And there's a lot of advantages that you get from this fact. And you can actually predict links much more accurately than you could terrestrially, where you don't have a lot of knowledge about where the handset is and how it's moving relative to the smaller cell on the ground. You can also, using software, configure the base station to operate as a relevant base station all over the globe. So at different frequencies, maybe it's a different technology. So as we're flying over Africa, we might be doing 2G or GSM or GPRS, and then over the States it might be 4G, LTE, later down the line it might deploy a 5G scenario. And so this is a little bit about what the technology is and how we're doing this. And I'm just gonna, to save time here, I'm gonna skip over some of these slides. We are in the process right now of demonstrating this technology from orbit. We've already gone through a pre-seed round, if you will, doing R&D work in the lab, developing the software and using equipment in the lab that you can simulate orbital RF links, which is relatively off-the-shelf technology. And after we had that working in the lab, we decided to invest money into building satellites to demo it from orbit. And we've been leveraging the ISS, the International Space Station, and their cargo resupply chain to do rapid prototyping and agile development of this technology. This will eventually segue into commercial services. So as the technology is developed and demoed, we will start pushing things more into production and build a fleet of satellites to provide commercial services around the planet through mobile network operator partners or customers. And these partners and customers are actually working with us already. We've got 27 mobile network operators around the globe signed up to test the technology with us, representing 1.5 billion subscribers, so almost 25% of the telecom market globally. And eventually the service will reach a state that looks kind of like this. This is a little picture of our orbital mechanics simulation of a final constellation of satellites, basically creating this seamless bubble wrap around the Earth with enough capacity to serve all of the demand, latent demand for connectivity, and seamlessly connect all geographies. And so real quickly, I mentioned leveraging the ISS and cargo resupply. It's actually very hard these days for companies to build satellites quickly. We've taken an approach that leverages commercial off-the-shelf components where we can, and designing bespoke components where we must. And we're able to hit very aggressive development schedules. Also partially because we focused on just the payload for the satellite on our first 3 missions and leveraged a hosted payload CONOP, where effectively we're strapped to another satellite and we use that as the host that provides power and commanding and control. And so we've conducted 3 missions already. The 4th mission is the very first free flyer. So that's flying on its own in orbit at about 490 kilometers altitude in a circular orbit. And that's still in early operations. It's been on orbit for maybe a couple months now. We're going to move out on test. COVID has made it difficult to do field testing. I'm about to show you some pictures of our field testing here in a minute. But we'll be moving out on field testing for this payload or this free flyer here pretty soon. These four satellites have represented the first 4 iterations on our payload from hardware and a software perspective. So each time we step through, we typically modify something based on test results. We take lessons learned and we feed that into the design the next time around. And so we've completed 3 of those missions to date. The 4th one's on orbit, and then we're in the process of working. We kind of keep a horizon of a few missions. So we're working toward the build phase of this Link 5 is going to be another hosted payload mission, and then a Link 6 mission, which will be a 2nd generation free flyer towards the 2nd quarter of 2021. Everyone likes pictures of the hardware, so we've got a couple pictures here of some of the hardware that we've launched to date, and some of the team. You can see the team is grown over time, and this is kind of what it looks like. So the first couple missions leverage these hosted payload ConOps. So this soda can looking spacecraft here, some of you may know, is called the Cygnus. It's owned and operated by a company called Northrop Grumman, and they provide cargo resupply services to the space station. And basically what we did was we piggybacked on the nose of the Cygnus. After it would deliver all the cargo, the nose is closed up, and it actually is, well, before it's closed up, it's filled with trash, and then the satellite flies away and burns up, and typically does garbage disposal for NASA as its service. But before it's disposed of, there's an opportunity to fly on that satellite. And so we leveraged this fact and put a payload on the nose of the Cygnus. And then there's an umbilical basically to the back of the bus that gives us power, telemetry, commanding, and then the spacecraft itself can act as an attitude control mechanism, it's called, to point us to the ground. We stepped through 3 of these missions each time, actually in some cases adding new software-defined radios, single board computers. We have a common RF front end for a stack of these SDRs and single board computers that basically act as test beds or like a sandbox, and we can try a variety of different configurations and test different hardware on orbit, see how it performs. And the RF front end has been iterated. It's all a custom RF front end in-house to get the sensitivity of some of the software-defined radios that we use off the shelf low enough to receive signals from cell phones on the ground. And then this over here on the bottom right is a picture of our first free flyer. We basically took the payload and added the things that I mentioned Cygnus provides, telemetry and commanding through actually 2 different modems. One using an SDR, actually both are really SDRs, but one uses a relay, an orbital relay through another satellite constellation for more nearer to real-time connectivity. And then there's another S-band modem, a modem to communicate with ground stations, large antennas on the ground, to move higher data rate telemetry and commanding. And then, of course, there's attitude control mechanisms as well. And a lot of that's actually from torque coils. We use hardware that pushes against the magnetic field to point the antenna ultimately towards the ground. And then these solar panels here, I don't know if you can see my cursor, these solar panels provide power. And that's on orbit now. We enjoy, as a small team, we enjoy these missions, all these projects we get to do end to end. And by that, I mean, we don't just design, build, integrate, test, launch, and operate the satellites. We actually do the field testing as well. So we have a mock mission control center in our offices here in Falls Church, Virginia, that we use to command the satellites. And then other of our colleagues who aren't in the mock will go out into the field. We pick test sites that are in very remote locations of the world. And as I mentioned, we have partners all around the world. And given orbital mechanics, there are certain places on the planet that are better than others to do testing, given overpass rates and things like this. So one of the places we've gone before twice is the Falkland Islands. So there's a picture up here on the top right, me and some of my colleagues with the penguins. And so it's a lot of fun. You get to go to a lot of cool places. This one down here is the Falkland Islands as well. We have test sites in New Zealand. And there's a nice test site shot from the beach in the Bahamas. And one up here in Canada as well. So it's a lot of fun. We take out a bunch of equipment with us, also software-defined radios. We even use software-defined radios to design some of our own test equipment that we use on the ground. And then, of course, all the other off-the-shelf stuff that's good and handy, like spectrum analyzers and things like that. We even turn the spacecraft as into a spectrum analyzer sometimes and do receive-only operations. And I'm almost done here, Alex. I've got one more slide.
Okay.
Sort of some of the highlights of our missions to date. We've actually, I'll just highlight it here in the middle. We have broken a world record here at Link. This technology has never been developed before, and things like this have never been done. And so this year, actually, just before COVID took over in March, we demonstrated the first transmission of an SMS text message from a satellite to a standard unmodified smartphone using the cellular broadcast protocol. And I want to be careful about the time, so I won't play the video now, but This is actually, you can find this online. There's a lot of publications that published it after the results of the test were made public. I mentioned, I think, a lot of these things in passing in the call already. So with that, I think I'll wrap up. Sorry, one more final slide. As I mentioned before, we're always looking for folks to come help us connect the world. And so if you're an electrical engineer, SDR engineer, or even if you do RF and possibly even aerospace or general software engineering, we want to hear from you. And I've got the link here to our website for our careers postings. So, thanks so much.
Thank you, Ty. This was an excellent presentation. Thank you. And of course, you, MathWorks, Analog Devices, and NIEDIS research all have presentations also during the lunchtime hour with, like, for everyone who registered, there's separate links for the virtual booths too, right? And you can talk with folks more one-on-one during those Zoom sessions as well.
Beautiful.
Excellent. Thank you.
Thank you.
So first of all, I'm trying to look at the on the Zoom session here because there's a lot of names, but I don't see anybody from Verizon, and I'm wondering there might be a technical difficulty. So is anyone from Verizon on the call? I don't see any names of the folks I know from Verizon. So doesn't look like it. All right. Just one last call. No. All right. So what we'll try and do in the interest of time is we're gonna switch gears into the actual Q&A session. I so far have 2 questions, both for Dr. Rondeau, but please, if you have any questions for any of our presentations, sponsor talks, as well as Dr. Rondeau's keynote talk, please definitely let me know via Slack. Okay. So what I'm going to do, and this is always the scary thing, so I'm going to unmute everybody on the Zoom. Unmute all. There are several other folks that are on the Zoom session here with me right now. If you're not one of the sponsors or the keynote presenter, Dr. Rondeau, please do not ask anything or make any noises. Keep yourselves on mute during this, because it's like otherwise it'll be like a fiasco. It'll be like one of my classes. It's like 74 students, like So with that, so Tom, first question. This came from a very, very interested radio astronomer. So it is, some of the tools could be applied to radio astronomy. Have you reached out to this community, such as through the Event Horizon Telescope? Unmute all. There we go. So you should be. I think there should be an option to unmute on your end.
Okay, we're good. Yeah. Okay, great. Quick answer: not explicitly. I think you're right. I think there's a lot that can be done here. I think the potential for having the phased array digital format of Hedgehog is an exciting one for beamforming for lots of different aspects that are, it's hard in the same volume. Well, it's not hard. It's physically impossible in the same volume to beat a dish for gain, but the electronic steerability and the kind of close digital processing to the signals might be of interest there. So the thing that we have done is I went out to the GNU Radio Hackfest that was held by Breakthrough Listen and SETI, so Steve Croft and the SETI folks. We did this last year at Hack Creek, the Allen Telescope Array. Fantastic event. We did a lot of good work there. That was more kind of my GNU Radio hat, more so than my DARPA hat, really. But so there's been engagement there, hasn't codified into anything real. And I think as we get the commercial versions of Hedgehog out, there's probably a lot of work to be done there. From the software perspective, I should mention this too, the DSSOC program I mentioned, what those processors could do for signal processing for other things besides what I typically use them for. I think there's potential there from the radio astronomy world. But also I want to mention that almost all of the software tools that we are funding to be built in DSOC, the compilers, the debuggers, the ontology discovery tools, the dynamic tracers of programs, all of that's being released open source. We had a huge, I think we had like 17 talks at FOSDEM, the Free Open Source Software Developer European Meetup. So we're trying to push a lot of that out there because, again, I think there's utility there for many things besides just what I'm focused on. So, short answer, not really. Longer answer, certainly potential. We'll see where that grows.
Yeah, Tom, this is John Swoboda. I work at a Haystack Observatory, and we are part of the core team for the Event Horizon Telescope. And so I just saw that we are looking into updating that Event Horizon Telescope network. And I think Hedgehog could fit in quite nicely, especially the tools that in the geospace community use. We already use GNU Radio. We use, EDIS stuff, and it feels like we could fit that in. And there are a number of, we have a number of dreams of creating large-scale arrays that could be doing some sort of, radar for geospace applications, but also passive listening for other applications as well. And I think Hedgehog might be a really interesting platform to sort of that can allow that. And so that's why I was so I was very interested. I was like, oh, can I have one? So that sort of thing.
I get that a lot when I give the Hedgehog talk. So like I said, hopefully soon we'll figure out a way to actually get the capabilities out. Kind of what we're building, kind of one-offs or small what are they, LRIP, low rate initial product kind of things. I would love to carry this forward, and what is the real way that we get that commercial matrix chip integrated with a system that so that we don't have to build necessarily a relationship with you, but you can just buy the capability as you do today. But yeah, I mean, let's reach out. We'll talk more because where how does that intersect with the DARPA mission could become an interesting conversation on its own.
Okay.
Great,
cool.
Thanks.
So there are two more questions, both Hedgehog related. Just a catchy name, but so the first one is, will Hedgehog be available globally, or are there any export restrictions on it? Do you have any idea on price range for the commercial Hedgehog? Wait.
I think you muted him by accident.
Oh,
you mute yourself.
I think we're both unmuting, so we're there we go.
Got it. Sorry. I muted myself to keep, because I have construction noise going on next to me, and I didn't realize that I couldn't then unmute myself. So as I mentioned, we do have this commercial variant of the matrix chip available. DARPA, obviously, we're doing the research and development for the chip and for the concept here. I think it's a powerful concept to get integrated or to get proliferated around the world because, as I said, and we made very strategic distinctions between what the ITAR, or basically the military version of this is, versus the non-ITAR restricted or the commercial variants, because there's certain capabilities that we don't want proliferated. What we have there, I think there's value there, and just understanding more of what we can do with the spectrum. There's no clear path right now. DARPA doesn't go into commercial business like this. So we're hoping that we can, through exploration of relationships or through other commercial entities, we can actually get it out there to the larger community.
And Tom, when you say we, who are you talking about? Because DARPA doesn't write data sheets.
Right. So BAE is a big defense prime contractor. They're the ones that are producing the matrix chip and the Hedgehog hardware. I already mentioned the RFSOC was co-funded by DARPA, but that is now a Xilinx part. And so BAE will be producing the data sheets, the user manuals, those types of things. But they're also not a commercial vendor. They don't really, that's not their business, that's not their interest. So I'm still hopeful, and we're working to try to make those kind of ties, those relationships that can happen. So I think that there's, what is the intellectual property, or what is the sales kind of process that allows a commercial company such as analog devices or National Instruments, to name a couple on the line here. What does it mean for you guys to be able to potentially get access to this type of technology? I think there's a conversation to be had there.
Absolutely.
Okay. Another question for Link. How does your service how will it compare to global internet through satellite projects going on, given that there are many smartphone apps that can provide voice connectivity through the internet?
Yeah, so that's a good question. So the fundamental difference is that the satellite internet projects that people have heard most about are probably Kuiper, Starlink, and well, OneWeb's going to come back, I guess. But these projects require you to buy a terminal. Typically, it's quite large, and it looks like Elon's going to start with a parabolic steerable antenna. There's a lot of companies like Phaser and Kymeta that are building phased arrays for the terminals. And so anyway, it's about like the size of a pizza box. It really isn't something that you can take mobily with you. So when you put that on the earth, you're really going to fix it to a building or maybe a car. And so the type of customer that you're talking about is typically has deeper pockets. Maybe it's a hospital, a remote hospital or something like this. Or so the minute you step away from that user terminal, you no longer have Wi-Fi connection, right? I mean, you leave the building and you're out in the middle of nowhere and you've got nothing. That's where we come in. So they are actually very complementary. You could kind of think of the Starlink and the Kuiper projects of the world as fixed broadband from space, and Link is more like mobile broadband from space. So you'll have your LTE connection when you step away from a terrestrial cell tower, or you step away from your satellite user terminal if you so choose to buy it. And so in that regard, it's complementary, and that's the fundamental difference. Alex, you're muted now.
Thank you. So another question for Tom. So machine learning question. Ooh. Have you seen, is there any promise for using machine learning to tackle the FPGA, LDPC, DSS, OC applications?
Yes. I mean, LDPC, there's a play there for just channel coding in general. So yes. There's actually some really cool work that's just in general that I'm seeing coming out, or just in the research world, for putting machine learning concepts at different stages of the transmitter or receiver. Obviously, DeepSig, I know those guys very well. I was just down visiting Virginia Tech, and Lijing Liu down there was showing me some really interesting concepts there. So, I think LDPC, Robert Gallagher created it in the 50s. Pretty well understood how it works as a straightforward approach to the channel capacity problem. But kind of changing that mentality of just what is, how do you actually back up? So the theory is that almost everything in the world is some form of map reduce problem. Not little m, little r map reduce. It's convolution to identify something, then filtering to reduce the noise, get the noise out and just focus on the information. That's what all of our receivers do, is map something into some space, filter everything out to reduce the excess amount of data to just focus on your information. Machine learning problems, in one sense, deep neural networks are just good at pattern recognition. They're very good at it in many cases, but that's really what they do. But pattern recognition is a way of filtering information out of a big space of kind of chaos. So I think there's something there from the channel capacity problem, and I've already seen it applied in some other iterations within the modems.
Okay, great, thank you. Another question for Ty. Do you have any thoughts on applying Link as a massive remote sensing platform? Also, how are the SDRs used in Link to be able to adapt to future trends?
So a remote sensing platform, is that there's no like pictures, or so we do have so there's software defined radios on the satellite, and we can use them as receive only units. I want to be careful about getting into the details about what the remote sensing applications for that might be. But if you can think about akin to optical satellites taking pictures of the Earth and having visible light images, we could take RF pictures of the Earth. We have some concepts for that, but that would be the one application I think in terms of remote sensing. For the SDR, so we have tried to think about the architecture of the hardware such that it can grow into additional features over time. So as we develop software on the ground, we can just patch that up to the satellite network and reconfigure it. So as an example, for a lot of the 5G elements, those might come a little bit later. We would just need to size the hardware in a way that it was able to take that processing load, and that the spacecraft was designed well enough to thermally get rid of all the heat that it generates. It's a big problem with small satellites, is thermal design and control. Yeah, I don't know. I try to answer the question as best I can, but we can also use similar radios. So like the same radio on the satellite could be used as a modem for the payload, or even for a TT&C link as an S-band, 2 gigahertz link. It looks like with Hedgehog, maybe we can do some of our inter-satellite links as well. So there's a lot of hardware out there, and it looks like some being developed that gives you a lot of flexibility with turning one radio into a different node in the network.
Yep.
We think about those things.
So I think John Swoboda from MIT Haystack, he mentioned like if the two of you could talk offline afterwards, because I think they do a lot of remote sensing at Haystack. They do a lot of radio astronomy, remote sensing, radar, and such. So this is up their alley. So yeah. So he'll maybe even during the lunch session, you two can connect, because I think that would be a cool conversation.
Perfect.
So another question, a few quick questions for Dr. Rondeau. I'll clump it together. Is there a timeline for the commercial Hedgehog device? Is DSSOC open source, and how does it relate to GNU Radio? It's like,
yeah. So timeline for Hedgehog, hard to say. We're starting to build. We have the chips. We're starting to build the hardware for our initial run for the research program. As I mentioned, working with SRS on 5G. We've got a few other places where those are going. It really depends on if we can really make that connectivity happen to the commercial world over the next year. So probably nothing at large scale for the next couple of years, frankly, to be honest, as far as getting it out there, transitioning technology, getting it built into the right form factors, the right support, and all that stuff. But what I am hoping is that there are, at least through things like DARPA and NSF grants, that we would be willing to support the production of the commercial versions for specific research problems. So if you're with a university or like Haystack or something like that, and I talked to Thiaga at NSF quite a lot about this type of stuff. I think this could solve a lot of his problems. He's excited about it. So I think there's some kind of a mode there, not on mass, but at least targeted over the next few years to get people stuff. Again, I'm not here to compete. I'm here to create new kick-ass technology that can be useful. As far as DSSOC, yes, as I mentioned, we went to FOSDEM. In fact, we do program reviews. Every 3 months, we have a deep program review with all the who we call performers on our programs. The challenge was, can you get a talk accepted into FOSDEM? And we'll have the program review over in Belgium. Worked great. We got a ton of talks out there. We number in the free software developers room, the LLVM room. There was some graph processing that was for another program. But we were kind of all over the place with FOSDEM, and you don't go to FOSDEM, talk about a cool thing, and not publish it open source. You get booed off the stage pretty quickly. So yeah, we're really focusing on making sure that this stuff is available in open source. Was that all the questions, or did I miss?
I think there was one more. for you, Tom. Yeah, I know. It's just like I think it's something that's kind of interesting. That would be because I think the hedgehog is definitely seems like if there was like an analytics hedgehog there would be a little bit of a spike there. Any plans to integrate commercial versions of the hedgehog to existing power platforms? Because I think when you mentioned NSF and you mentioned Thiaga, that's like ding 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 ding. It's like power is like the kind of like a big
Great
big
point.
part of it.
Yeah. So the platform for advanced wireless research, if you're not familiar with, if people aren't familiar with Power, a big NSF project really looking at, advanced wireless research, but 5G is a big topic for it as well. No plans, but I really should engage Thiaga again soon, because to be honest, I've been holding back a little bit because there were so many, as I said, fitting 40 gigahertz into one chip was really hard. So there was a lot of promise for the technology. The last year, I kind of wanted to make sure that it was going to work. It's coming out, right? Like we're actually producing, we've produced the chips. We now have yield numbers on them. They've been tested. We're putting the in package and all that stuff. So it's getting exciting again. And I think, yeah, it's the right time to talk to Thiaga about, and to the power folks, getting out into the powder test bed over in Salt Lake City, I think would be fantastic, or what's going on down in Raleigh, Durham now. Yeah, huge opportunity there. It's good motivation for me to kick the dirt with Thiaga next time I talk to him. So unfortunately, is there?
I think that's it. I think we actually have to transition to the lunch session, but so Tom, Mike, Hayden, Robin, Ty, and Henry, all of you, thank you again for your time this morning. Awesome talks from all of you. Great to see a lot of insights on what you're all doing. This is a great part of like what NEWSDR is all about. And thank you again. So everyone, an applause. If you're looking at Slack, you'll see a lot of emoji hand claps as well. Any questions with our industry sponsors? We have now the industry lunch virtual booths for Tom and such. I'm not sure if anybody, how many of you are connected to Slack, but there's already a ton of conversations happening on Slack. Feel free to connect with folks offline as well through that. But we'll resume our main track at 1 o'clock. But again, thank you all for your time this morning, and we'll reconvene at 1. So thank you, everyone.
Sounds great. It's good to see everybody again.
Thank you for the opportunity. A pleasure to be a part of it.
Thank you.
Thanks much.
Bye.
Okay, everyone. So welcome back to the main track of NEWSDR 2020. So hopefully that was a great lunchtime session with all our sponsors, great sort of networking opportunity and find out more one-on-one of what folks are up to. So with that, what I'm going to do is this part of the event's always been a lot of fun, which is what we're going to be focusing on here is what we, for lack of a better term, elevator pitches about what your work is about. So 3 minutes, it's very short, it's very sweet. And then after that, we have a half-hour poster session where each and every poster presenter during the community spotlight actually proceeds to give sort of a more in-depth sort of the discussion for half an hour in a dedicated Zoom session, similar to what we just had with the sponsor lunchtime virtual booths, right? So what we're going to do is, let me see, there is definitely a roster, and I'm going to try and go through this. So just bear with me for a second, folks. All right. So it seems like our first presenter, okay, paper, as usual, I'm very organized. So our first presenter is, well, oh, there you go. I feel embarrassed. My own MS student, Miss Yaya Brown, okay? And her poster is entitled, Evolving LTE Security via Software-Defined Radio Testbed, right? So let me first, before I forget, I do have slides. Here we go. So make this big. Of course, now I need to find the Zoom link. So let me find where, I think I saw Yaya. So yeah. So Yaya, can you see me? And no, it's still, okay. Yaya, can you hear me now? Can you say something? Okay.
Hi.
Hey. All right. So what I'm going to do is I'm going to just I'm going to share the screen. There we go. Right. And I'm going to make it big. So in 3 minutes, if you can describe to the audience what your poster's about and what's a cool thing that you've been doing with software-defined radio.
Okay. So the project that I will be presenting on will focus on LTE security, mainly the development of an LTE testbed with the use of the open source software open air interface and a B210 USRP acting as the eNode B. And a Samsung S4 cell phone was used as the UE, and N210 as a jammer, and then the X310 as a counter for jamming attacks. So the motivation for the project was the increase in the number of cell phone users and the importance of reliable and secure wireless communications, and its increasing importance as we as society depend on that technology more. So this LTE testbed enables the ability to test potential security threats as well as possible countermeasures that can be taken for those threats. Although the development of this testbed, throughout the development of this testbed, it also focused on a single use case where my other teammates and I focused on potential physical layer threats, mainly attempting to jam the LTE network, mainly to attempt to jam the LTE communication link, and my other partners focused on countering that attack. So going into a little more detail, we first installed open air interface, and then we ordered a SIM card and programmed that to work with the network. And then OAI has an interface for B210 specifically, so we just had to change some parameters to make that work. And then once that was all set up, we had a working base station where the UE could connect and use data and play YouTube videos and stuff like that. For the jammer, we had decided to do a frequency hopping jammer, which we used the N210 and GNU radio to program it to hop to different frequencies within a set interval, this being 2.66 gigahertz to 2.7 gigahertz. This was to ensure it wouldn't be predictable and potentially harder to detect since it was a narrow band jammer. So in order to analyze the effects of this jammer, Wireshark was used on the Ethernet port that the eNodeB was connected to tell us what packets were successfully being transmitted, and more importantly, when packets were dropped or when they were being retransmitted because they failed. So the frequency hopper jammer had two different effects on the LTE system: packet corruption and denial of service. So the first effect was packet corruption that caused the loss of a few packets and showed a decrease in the number of packets being successfully transmitted. The time between packets increased once the jammer starts because a few packets were being dropped and retransmission occurred, which caused more time. So denial of service was achieved by running the experiment multiple times until the phone disconnected in one case. So this occurrence was probably due to chance because the frequency hopper was random and it just so happened to hit a subcarrier the UE was on, or an important signal that caused the DOS. So to go a little into detail about the countermeasures, the basis was an X310 was used to detect when the N210 was causing the interference in real time. Once the jamming had been detected, the eNodeB was alerted and changed its downlink center frequency to be outside the jamming interval, but still within the LTE band 7, which is what we used. And so then this enabled a continuous and adaptive jamming detection method. Yeah, that's the basis.
All right. Okay, great. Thank you, Yaya. So our second presenter, I'm trying to like multitask like mad here. Boop. I'm trying to be like a Zoom presenter. Our second presenter is, one of my other graduate students. Yeah, there we go. So let's share. So our presenter is Mr. Kyle McClintock. So first of all, let me mute. Where? Oh, there you go. Yeah, thank goodness. Yeah,
I'm unmuted. Yeah, thank you.
You're unmuted. Okay. Okay, great. So Kyle, and so the presentation that he's giving is entitled Multi-Objective Localization of Signals of Opportunity under Ambiguity Using Unsupervised Learning. And so this is a collaborative effort with several other students in the lab and myself. So Kyle, take it away.
Sure. Were we planning on showing a slide or a poster with this?
I can't seem to find, like I have some slides, but not all of them.
That's
but
fine.
I think in 3 minutes, I think you'll do a great job with how.
Okay. Sure. So hello, everybody. As Dr. Wiglinski said, I'm from the Y Lab. I'm a second-year PhD student, and the research we're looking into is about multi-hypothesis tracking. So in radar, this is a very popular problem where you have some known reference signal and you perform active localization. So you send out this known reference signal, it reflects off reflective surfaces, you observe those reflections, you estimate the time of flight, and you perform multilateration and you estimate the location based on those range estimates. Then you gate those, you form hypotheses, you compute the maximum likelihood, you predict and you repeat. And that's how radar does the multi-hypothesis tracking. And it's a particularly interesting problem when you have one or more objects very close to each other and you're trying to figure out, are these radar detections from the same thing or from different things, and how many things are there? So we wanted to kind of look at this problem from a different angle. Instead of radar detections in an active setting from reflected signals, how can this problem be looked at if instead wireless beacons are being localized from their wireless emissions in a passive setting? How does this problem change? So a big change, of course, is instead of location estimates being along the edge of some unknown geometric shape, the beacon estimates are instead a multivariate Gaussian random variable, either 2D if you're localizing in 2D space, or a 3D variable if you're localizing in 3D space. And so we use a mixture model to tackle this problem. And then we additionally ask the question, if there's multiple wireless beacons per vehicle, how can we kind of differentiate those beacons as well? So it's kind of an ambiguity problem within an ambiguity problem. How many vehicles are there, but also how many beacons are there in each vehicle or building or person that maybe has multiple beacons on them. And that we model as a random walk problem. And we use a different unsupervised learning method for that, a Markov chain clustering solution called Chinese Whispers. So if this interests you, please come to my poster session at 2 o'clock, and I look forward to seeing you all.
Awesome, thank you, Kyle. So I think for a little bit of a break, I think those are going to be the couple of WPI presentations. We're going to have a whole bunch of others and then a couple more WPI presentations. But awesome. So that was Yaya and Kyle. Our next presenter is not from WPI. Not just kidding. It's Professor David Starobinski, along with his students Johannes Becker and former WPI students Stefan Grezovnik and Ling Xiao Zin. So with that, I am going to unmute David. So David, can you say something?
Yes, can you hear me?
Yes, excellent.
Perfect. Thanks so much, Alex, for organizing this great workshop, as usual, every year. So what I'm going to talk today about is about a wireless testbed architecture for IoT devices, primarily that we have been developing over the past year or so. And the motivation is as follows. We all know that there is an explosion of IoT devices of all different kinds: wearables, smart bulbs, smart locks, long-range motion sensors, and you name it. But at the same time, the issue is that there are a lot of different IoT protocols. So, you have the traditional Wi-Fi, Bluetooth, and, they have different variants that are more tailored toward IoT. But also we have Zigbee, we have LoRa, we have Z-Wave, we have Sigfox, and so on and so forth. And so the question here is, how can we assess the physical layer performance and security of such devices in a cost-effective way? At the high level, you may think that all the devices behave the same, but once you look and scrutinize, you'll see that in practice, if you look at the physical layer performance, they can be quite different. And so the approach that we've been proposing is to use SDRs, software-defined radio, because they are universal radios. And as such, we can generate and as well receive arbitrary signals, analog signals. And so the idea is to employ the SDR because it allows precise timing and control on the physical layer. And that's one of the challenges when running testing is to have very precise timing on the level of lower than milliseconds, even microseconds level, as well as, say, control of the gains of different signals. So this provides an affordable setup and allows us to uncover significant difference in the performance and behavior of IoT cards. And so here I'm just showing a few examples, showing one specific example for Zigbee. We have done extensive experiments as well with Wi-Fi. And so the idea, if you look at the lower left quadrant, is that what we can do with this setup is that we can generate signals for a certain protocol. Say we can generate a Zigbee beacon request packet. We can play with the signal gain, as well as with the timing. We have some delay, we can shift in time. And at the same time, we can superpose, we can add some interfering signal and additional signals. So this could be a noise, just some random noise, or it could be a jammer, or it could be some various type of interferences. So one specific type of experiment we run a lot of different type of experiments, but an interesting one we run, and you can look here with the truncated packet one, is that we send the first packet we just send a preamble. We send a Zigbee preamble, and then we wait for a certain amount of time, delta t, and then we send a regular packet, a beacon request, and then we look whether we get a response back, a beacon or an ACK. And so that's why we can see with the Universal Radio Hacker, it's kind of a spectrum analyzer. Over time, you can see the preamble that we sent, then the time, the delta t, and then the actual packets. This is one of the experiments we have run. There are many other experiments. We have run experiments for RF sensitivity. We also run experiments for capture effects and the like. So with reference to this specific experiment with the truncated packet or just with the preamble, so we run this over a bunch of that you can see now on the upper right, a bunch of different Zigbee devices, 5 different ones. And so what we see here is that what you see in pink here on the figure is the time during which we transmit the preamble. And this is the kind of the interferer. And not surprisingly, you are unable to receive the signal, the beacon request. But what is more surprising is that even when you transmit the beacon request after that truncated packet, after a certain amount of time, you still cannot respond. You still cannot get a response back from the device. And so in effect, what you are doing here is a denial of service. And the reason is because in the preamble, you have a length. You have a length field, and the length field informs the receiver how long you are going to transmit. In practice, you are not transmitting anything, but because the receiver is in the receive state, if another packet comes afterwards, the packet is not received. So it turns out that all the ZigBee devices were kind of susceptible to that type of attack. We call this truncated after preamble attack. And then you can see that it takes a different time for the different devices to recover till they can actually receive the packet. And that can be used to fingerprint the devices because they don't behave all the same way. You can distinguish between the different devices. Okay. We have done another experiment, short test interframe spacing, which I won't go into. If you're interested, you can come to our Zoom poster session. In our Zoom poster session, I can also present results about Wi-Fi. So just in conclusion, we have done benchmarking, and we can do very low level, very precise testing of the performance and behavior of the different cards. And we can also fingerprint them at a very, because we can distinguish their behavior. We are currently testing other IO2 protocols, as well as doing various other fuzzing at the physical layer.
Okay. Thank you, David. Thank you. Thank you. Next up, from Northeastern University, Jaeming Xu and Miriam Leeser, and their poster is Hardware Architecture of MIMO Matrix Processors for SDR. So let me see, do I have to... I'm guessing, is that you, Jaeming?
Yep. Yep.
Okay, great. Yeah,
Yep.
I couldn't. I was guessing like JMX. Yeah, that's probably it. Okay. Well, well, take it away.
Okay. Yeah. Hi. So I'm Jaeming Xu, and I'm from Northeastern University under Professor Miriam Leeser. And what we did is the hardware architecture of MIMO matrix processor for SDR. So as the massive MIMO would be the 5G's main technique, but the problem is that as the antennas, number of antennas grows large, the complexity also grows dramatically, and the data you want to process is also complex numbers. And from the perspective of MIMO's receiver and decoder, for the linear decoder, we need whatever, and we need the matrix multiplication inverse. And for the MIMO transmitter, you have decide how many streams you can use. You have decide the rank of the matrix, rank of the channel matrix. And also for the nonlinear decoder, you have the QR decomposition for the Cepheid decoding. So we find these three matrix operations are the mainly operations that use in matrix and for MIMO decoding and encoding. So we proposed an architecture which merged the SVD, QR, and the matrix multiplication together to use the same resource. So in one way is that because some operations in the MIMO are decided, it depends on the previous one. This is because, and if we transmit data back and forth, will consume some time. And the second is that if we put the work on the software, it'll consume a lot of time, and which cannot achieve real-time processing. So, and in our design, the system is designed in Simulink, and we use the HDL coder to generate the HDL code. And sometimes you can directly use the floating point. It can support the fixed point and floating point. And you can use the fixed point or the floating point, and floating you can use networks design one or Xilinx one. And we have already give a code which can replace this. And if you want to take a look at the details, you can go to our session to see how can we merge the SVD, QR, and matrix multiplication together based on their dependency graph, because their dependency graph is are very similar. And from the result, we can see as the number of antennas or the size of matrix grows large, the resource also grows large. And the accelerations for SVD is obvious, but for QR, if you go to the fixed point, it's also acceptable. So as a conclusion, we can say that we merge the three operations together, which make it easier for the SDRS developers to use, because it's designed in Simulink and can easily use it in your hardware for no matter testing or real work. And it's easy to test your algorithm using our system. And also our system is driven by instructions. So it can also work as a co-processor for the ARM core or whatever the controller. And then our next step, we plan to open source this design on MathWorks Central, and this is funded by MathWorks. Okay, thank you.
Okay, so thank you.
Yep.
Thank you.
Yeah, thank you.
So next, after Jae-Ming, is Andrew Rivet, and I believe, from what I heard, like unless situations have changed, he might not be able to make it. So let's just see. I'm going to just scroll down and see in the interface, and John, you don't see Andrew. I'm just double checking. Doesn't look like it on the participant.
Yeah, he's not in. He's out.
He's out. Okay.
Yeah.
Okay. So next up is Jeffrey Wallace from Rocket Technology Systems, and him and his co-authors have their posters on software-defined global navigation satellite systems and resilient navigation for embedded automation. So let's see. Where is it?
Hear me?
Yep, perfect. So Jeffrey, welcome to NEWSDR, and take it away.
Thanks so much. We started off the project for the Air Force with the idea that we needed to come up with a new solution beyond the current generation of embedded GPS INS systems. So we knew already that we were going to break apart the existing hardware paradigm for PNT devices. And this led us then down the path, once we started the project, of experimenting with then a wide number of software-defined radios to do our global satellite navigation systems work. We did everything from a proprietary Northrop Grumman M-code GPS using the latest and greatest capability that was just launched, all the way down to GNU radio-based. There's a GNU radio-based GNSS package. I encourage everyone to investigate that, which does a decent job compared to the price point that really would work for the class of problems all the way down to Arduino and Raspberry Pi and things like that. Analog Devices, we worked with their several of their systems, so we just found it a very interesting circumstance. And then we were paired with a different requirement, which was to work with a software-defined radio that was very sophisticated for next generation drone communications. And then we had the idea wow, we could just piggyback off of this really fancy SDR for the communications. And so now we're down a path of commercializing that into a package. We then took a little detour and thought through how this would work to modernize AR/VR training systems, as we indicate down in the lower left, where we found an opportunity where higher accuracy, lower swap was, and really a next generation approach on comms that then could benefit once again from an upgrade in GNSS was of interest. And then we really kind of swing for the fences on a roll and deciding to then suggest to the powers that be that we could do something for the good old F-35 and help them perhaps lose a lot of weight off of the system when you think about redundancy and the kind of internal structures it takes to be able to safely secure under vibration and all of the conditions of warfare, all of the different radio systems, radio-based systems that we've indicated in yellow in the figure to the lower right. And this is a pretty entertaining conversation which is ongoing, and highlights, I think, what hopefully others will come to see, that this idea of using SDRs in a more fundamental way in embedded systems is something that I would hope to see more of when we think about working with things like analog devices and Lime SDRs. Just getting ready to receive a shipment of Lime SDRs and doing some fun things with that. We really think that everyone should look into this, and I encourage everyone to hear more about the fancy SDR in my breakout session.
Awesome, thank you, Jeffrey. Our next presenter is from Northeastern University, Saranga Handagala, and advisor is Miriam Leeser. And the title of the poster is a software-defined radio-based real-time baseband processing platform for wireless communication research. So I am going to, I saw you somewhere, Saranga. Here we go, unmute. Does that work? Can you say something?
Hi.
Yep, perfect. Okay,
Hi.
You got the floor.
Yep. Hi, everyone. My name is Suranga Handagala, and I'm a PhD student at Northeastern University. This poster is co-authored by my advisor, Professor Miriam Leeser. We know that software-defined radios are becoming increasingly popular in wireless communication research. If you take modern SDR platforms, they not only provide a flexible radio frequency front end, but also support back-end digital signal processing. However, the question is, do we really make full use of their capabilities? We know that various SDR-related tools are available, but many of the academic researchers have not really leveraged them. So the focus of our research is to use the back-end processing power of SDR platforms to demonstrate real-world wireless communication applications. We know that a practical wireless communication system has several defects. For example, frequency offsets, channel effects, and you name it. What we do is we build an LTE receiver that can compensate for such defects. We implement all our compensation algorithms and other baseband processing algorithms on an FPGA, or what you call a field programmable gate array. We have set up an over-the-air link between the transmitter and the receiver, and our carrier frequency is 3.5 gigahertz. The FPGA does real-time baseband processing of received signals. In this poster, we are going to talk several important aspects of a digital receiver, including synchronization and channel estimation. We have implemented a simple but robust channel estimation and equalization algorithm on the FPGA that allowed us to demodulate higher orders of modulation, such as 256 QAM and even 1024 QAM. With this receiver platform, we have demonstrated some real-world applications. One is we're going to show the receiver side how the receiver side constellation is affected when we increase the transmitter power amplifier gain. We know that OFDM signals have very high peak to average power ratio. We are going to see how the power amplifier is driven into saturation by looking at the error vector magnitude of the received symbols. In another application, we are going to use an interference transmitter. The purpose of this setup is to show a practical asynchronous communication situation. We also change the center frequency and the power of the interference And we see how the received symbols are affected when you make those changes. Make those changes. We show that we can use spectral shaping filters to improve the error vector magnitude of the receiver. For these experiments, we have used AD9361 FMCOMS tree with Xilinx CZ706 evaluation board. And for the power amplifier experiments, we use BGA 7210 power amplifier for the nonlinearity experiment. So for more details, I invite everybody to visit our poster session. Thank you.
Thank you. Thank you so much. The next presenter is Evan Faulkner from University of Connecticut. And his poster is on advanced receiver for IEEE 802.15.4 OQPSK physical layer. So let me unmute Evan because I have the technology. There we go. Okay, Evan, can you hear? Can you say something?
Can you hear me?
Yep. Okay, you're all set.
Okay, good. Hopefully it stays good. It's been a little bit choppy for a minute for me. But like you said, I'm Evan. I've been working with quite a big group of people from UConn on this project for the last year. I actually had a great time presenting here last year on the beginnings of this project. So I'm back this year to wrap it up and let you know how everything went. So my poster is about an advanced GNU radio receiver for the 802.15.4 or Zigbee standard, specifically the OQPSK physical layer, which is a pretty interesting one, which admits a couple of different types of receivers. So the reason we started this whole project is that the receivers that are available for use with GNU radio as of now are non-coherent receivers, which treat the OQPSK signal as an MSK signal and decode as such. We determined that there is some room for improvement there by switching to a coherent decoding scheme, treating the OQPSK signal as an actual OQPSK signal, which would give us a 3 dB power improvement in the performance of the receiver. And so we thought that it was probably worth investigating that potential improvement. And as we started digging around and testing in simulation, we actually showed that we do even better than 3 dB. So when I spoke to you last year, we had a receiver that was doing about 6 dB better than the non-coherent receiver that's available for use with GNU radio as of today. But now we have a completed coherent receiver that's actually 10 dB better than the non-coherent receiver that's available. And so we implemented this in GNU radio. It currently runs in real time. And in the curves on the right in the poster, you can see that the left curves show the vastly improved performance over the right non-coherent curves. So this GNU radio receiver is running in real time, appears to be doing really well. We're pretty excited about it. And so if you're interested in learning a little bit about how it works and how it might be useful for you, or even how to get your hands on the code to play with this in GNU radio yourself, come check out my poster presentation.
Great, thank you, Evan. So next up, one of the several international entries is Miklos Marotti from the University of, I'm going to hopefully pronounce this right, Szeged from Hungary. And their poster is Team Marmotti, Lessons Learned from the DARPA SC2. Okay, so let me unmute. Here we go. Miklos,
Right.
Can you say something?
Yes. Can
Okay.
you hear me?
Yep,
Okay, good.
perfect.
Okay, so this is an international team. I'm from University of Szeged, and you said it correctly. My collaborators are from University of Budapest, Hungary as well, and Peter Bertoshi from Vanderbilt and Sándor Szivasi from Bastille in Atlanta. And we all met at Vanderbilt. And this is just a short report what we have learned on the DARPA Spectrum Collaboration Challenge. Probably many of you have heard about this challenge. It was between 2017 and 19, 3-year program. And the challenge was to use AI for spectrum sharing and to collaborate with peers without co-design, so without agreeing how to collaborate, and we have to communicate without constraints, so there was no restriction of the waveform you can use and protocols what you can implement. And it was really up to you how you solve this problem. You were given a very powerful set of machines, servers, and USRP X310s. And the whole thing was running on probably the world's largest channel emulator, which is 256 by 256 channel emulator. It can support 128 users simultaneously in a 2x2 MIMO setup. Arbitrary delays and can be introduced. It has a 4 non-zero complex step filter. I'm not going to talk about the Colosseum. You can learn a lot about that online, but the real takeaway from there is that it can simulate complete movement, simulated movement, can simulate RF environments, can simulate traffics, and it's implemented in 21 racks. You can see it on the top left side, and the cooling system is like a 40-ton cooling system. Our team placed first in the first preliminary event, second in the second preliminary event, and second in the championship event. And what I like to talk about is about our approach. We implemented our modern, so we broke up the problem into two parts. The modern, which is implemented the GNU radio, and the decision engine, which we call MAC, but it's really like a decision engine. The modern is a BMC based. It's high performance, can handle 40 megahertz bandwidth, can break it up into 40 channels, up to 40 channels, and can transmit and receive on any one of those channels simultaneously. It is open source, so if you want to play with it, you can get it. If you search for GR Marmot, it's free. And it can report lots of interesting parameters about the traffic, about the RF environment, and you can tune it very detailed how it can perform. So it's basically like a racing car, very high performance, but very dumb, and you need a driver. And the driver is the decision engine. It is just observing and tunes the modems. There is a what protocol is that? Google implemented protocol, so you don't even have to touch the modem. And the decision engine is collaborating with peers, and it's a distributed algorithm. The interesting part is how we used AI in this system. We used only for short-time predictions about the RF environment, about the traffic. So it turns out that it's very, very beneficial to make decisions once you know what's going to be in the future in the short term, especially about traffic and RF. And it has a handwritten expert system, long duration strategy to follow the rules of the competition. And some of the key takeaway lessons, AI challenges that there is no consistent snapshot of information in the distributed system. So we had to handle 10 nodes simultaneously. And even within a node, you had multiple, like 70 GNU radio blocks, and the packets are flowing through these. You really don't know what's really happening, even within a single system, because the packets are flying through it and then buffered and everything. So there is so typical AI solutions are not really applicable. And on top of that, even if you do some reinforcement learning, what is your loss function? It's not well defined. And on top of that, the rules were changing constantly. So that's why we broke up the problem to something which we can predict and verify, short-term predictions. And then on top of that, we had our expert systems. And about the collaboration, it was very important for us. We learned in the 3 years that it's really important to know more what the others are doing and to have the chance to verify that what they are reporting is actually accurate. Without knowledge, without trust in the validity of those reports, we are not going to know. No teams were using information from other teams. And once in the third year, validation was implemented and people started to use these collaboration messages, and many nice things came out of that. And the last thing what I'd like to say is this was our best Docker project we have seen so far. So thanks for Luman for that. If you'd like to know more details about this, please come to the poster session. Thank you.
Great. Thank you. Thank you, Miklos. Next up, back to some WPI. This is actually a collaboration between WPI and Université Gaston Berger from Senegal. PhD student Fatoumata Thiam, who is also visiting WPI, is the first presenter, and her work, as well as the next poster, is on IoT, specifically with respect to agriculture. And the name of the poster is Self-Optimized Irrigation Based on the Internet of Things in the Sahel Region. So let me find Fatoumata. Fatoumata, are you there?
Yes, hello.
Excellent. Okay. So with that, please take it away.
Okay. Hello, my name is Fatoumata Thiam, and I am from University Gaston Berger in Senegal. And also I'm a visiting scholar at WPI, and I'm working in a self-optimized irrigation based on the Internet of Things in the Sahel region in Senegal. So this work is supervised by Professor Wiglinski at WPI and Professor Maïssa Bay in Senegal. And to talk about the Sahel area in Senegal, so this area is an exceptionally favorable climate for market gardening, and so it represents a natural pole of agricultural and production in Senegal. However, it is presently confronted with difficulties related to to climate change and regarding also to access to water and a lot of dryness due to the desert in the north part of the country. But second, also there is a problem with network coverage. GSM network coverage is missing in some places that prevent from monitoring those areas. So in fact, in rural area, only GSM cellular network is available there to collect data and store them in local database or in cloud. But due to the huge amount of data that have been that are transmitted, that can be very expensive, and also that method might not be sustainable in long term. And furthermore, for a couple of locations, as we said, are in a white spot, and we cannot monitor those areas. To overcome those limitations, we aim to develop an Internet of Things based on that will help leverage and use free ASM band frequency in order to transmit and collect data from those areas. And we propose an architecture that use wireless sensor network in order to monitor in real time the need of the soil and also program actuator or is in real time. And that brings us to the actual development, and what we have tried is to develop a math processing approach for reliability in order to maximize the network longevity in order to keep track of the area at any So I invite you to follow my poster presentation. Thank you.
Okay, so thank you, Fatimata. That excellent, excellent. Part two of our IoT sort of collaboration. So also from Université Gaston Berger in Senegal is Emmanuel Effa, and his, I would say in terms of acronyms for projects, his takes the cake because he was
Hi, sorry about that. Alex dropped out, unfortunately. We're going to be doing the next poster, FA, which is energy efficient, fault tolerant, fault avoidance, adaptive, and heterogeneous clustering based on agro IoT. FA, can you hear me?
But unless you unmute me.
Okay, can you speak up a little louder?
Okay, can you hear me?
Yes, I can.
All right, thank you so much. My network was very unstable. I had to be running around looking for a better signal. So as my colleague has already said, we are both working on agricultural IoT. As we know, agriculture has become the bedrock of the global economy, especially on our continent of Africa. And with the current climate change, the traditional way of doing agriculture is no more reliable. So this precision or smart agriculture has become the way forward. And this agri-IoT is just made up of self-configured sensor node or IoT devices that are equipped with sensing, computing, and communication abilities without any infrastructure. The typical network layout is what I've illustrated in the figure. But the main challenge with these IoT devices, which are serving as the bedrock of IoT, is the nodes are highly resource constrained. For instance, they are frequently powered by batteries, which restrain their communication capacities, the distance of communication, memory, and so forth. And again, there is lack of post-deployment maintenance in most cases of agri-IoT applications. And these prone the network to a lot of faults. Again, there is also high topological dynamics, and the level of scalability of agri-IoT also keep changing. One other problem with agri-IoT is interference from coexistent signals and also physical obstructions, especially in the field of agriculture. You start the farming, the network is set up, but after some time, plant to grow and there is obstructions to signal. But the good news is the routing protocol is able to manage all these challenges mentioned if well designed. And as we speak now, with respect to agri-IoT, there is lack of energy efficient and adaptive routing protocol, which is effective in ensuring self-healing and self-reconfigurability. So the main aim of this research, which I am doing under Professor Alex Wedlinski at WPI here, is to develop and implement a new cluster-based routing protocol for this network that has the capacity to self-detect and manage faults, that is able to scale comfortably and also adapt to network topological dynamics, and also implement a lot of power optimization techniques. So as we speak now, there are several ways of doing this, even though as they exist in isolation in literature. People believe that, or literature has documented that it is possible. We can do scalability or network adaptability through reclustering, self-reconfigurability, and multi-hop routing. We can also manage faults using fault detection, fault tolerant or self-healing or fault avoidance techniques. Then with regards to power management, the areas where power needs to be managed has to do with control message complexity of the entire routing protocol. Again, event sensing, which nothing can be done about it because it's constant. Then data computation strategy can also be exploited to optimize energy. Then communication and the sensor node activity schedule issues can also be taken advantage of. In this particular work, we have proposed these potential remedies, which is still a research in process. So with regards to fault management, we are using the adaptive clustering technique to manage sensor node out of service faults. Then we are using threshold-based decision theory to manage data outlier. And these two are the two main root cause or root faults in the sensor network parts, which we are working under the Agri-IoT. And under power optimization, we are using the multi-objective optimization framework from the network design perspective. Again, we are also taking advantage of multi-hop routes optimization framework. As we speak now, there is no framework which is closing the gap between the experimental result or simulation result and practice. And unique to what we are doing, we are coming up with something that will be able to close the gap between the philosophy of several propositions and the reality on the ground. Again, we are taking advantage of the architectural requirements of the network. And here we are looking at local processing of data as a way of optimizing power. Then in-network data redundancy checks. There is likelihood of reporting the same or concurrent reporting. Is it possible to control this one to reduce communication overhead? Yes, that is what we are also taking advantage of. Then we are also looking at local network management because management involves communication. So if we can manage network locally, that is a way of optimizing energy. Again, under scalability and network adaptability, we are using the adaptive clustering technique, then multi-hop routing technique, then local network administration as a way of ensuring that's key principal objective. In conclusion, I want to say that Agri-IoT remains indispensable component of the global smart agriculture agenda for addressing the socio-economic impact of climate change in agriculture. And as we know, and as the statistics says, about over 70% of African youth have the potential to go into this for their livelihood. And already more than 60% of people in sub-Saharan Africa have their livelihood dependent on agriculture, which has been severely impacted by climate change. For instance, in my home country, Ghana, we used to have 2 seasons, but because of climate change, we have just a single season. So we need to take advantage of IoT to improve resource optimization. As for the water bodies, they are there, but how do we manage it so that we don't abuse it? How do we control pests? We know pests has become a global issue now, especially on the continent of Africa. They are affecting crops. How do we track and remotely control our farms? As my sister said, the irrigation system, the underlying technology should be reliable so that it can function very well. And that is exactly what I'm doing in my research. So I want to invite people for my poster session so that we can discuss more about what I'm doing and see possible research collaborations in the future. Thank you.
Thank you, Emmanuel. Thank you. And in fact, in a few seconds, like Neil is going to post the links to all the poster sessions, the virtual poster sessions. So that's excellent. Like so definitely everybody should take a look at the posters that they've really connected with. Last but not least, very, very exciting is Marco Mezzavilla from NYU School of Engineering. So with that, Marco, there we go. Can you, okay, there, I hear you. Okay, so you got the floor.
All right, it's going to take just a couple of minutes, and then I let everybody go to the respective demos. So as mentioned, I'm a researcher at NYU and also co-founder of Pi Radio. My colleague Aditya will give you more details in the session, in the demo, at the Zoom link. I just wanted to share, a snapshot of what we've been working on, give you some details, and hopefully catch your attention. So at Pi Radio /NYU, we've been working on fully digital transceiver architectures that can be prototyped and evaluated through software-defined radio platforms. So that's been our focus over the last few years. Recently, earlier this year, we were finally able to conclude our transceiver board design at 60 gigahertz that features RF chips by analog devices on the RF board, as you can see in the bottom part of this picture on the left-hand side. And the RF transceiver board connects to the powerful Xilinx ZCU111 RF SoC board. So the system that includes these two parts is what we propose as this fully digital millimeter wave software-defined radio platform that's actually being sold as we speak, and we have some early customers, universities, and industry. So what I wanted to share briefly here is the fact that we are going to talk more about some early results that validates the calibration of the system, the ability to form beams as per textbooks, and the actual ability to observe the fully digital beamforming capabilities of millimeter wave, which in a simple sentence means the ability to receive energy and transmissions in multiple directions at the same time, as opposed to the more traditional analog phased arrays, according to which the transmission happens sequentially. So you can look in only one direction at a time. This effort was originally partially sponsored by NIST for the early designs, the pre-commercial board, but then thanks to the support of NSF through an STTR program, we were able to build this board that we're going to talk about and demonstrate today, the Pi Radio 60 GHz STR board. Additionally, we are also working on more advanced security, millimeter wave security algorithms and hardware to, and this is part of the Army STTR program. So in the Zoom link, we'll tell you much more about the capabilities of this platform. And importantly, I want to conclude this session by saying we are hiring. We are looking for FPGA experts, passionate just like we are, to join the team because we have a lot of ideas in the roadmap. There is a lot. But for now, let's just focus on this platform, which we feel very excited about, and we're so happy to share with all of you. So I think I am done with this brief introduction. It's 2 p.m. Sharp. So I'll give it back to you.
Great, great. Well, thank you. So that, folks, like with Marco, that concludes our sort of the spotlight talks, right? So now you got sort of a sample of what everybody is doing, from things like millimeter wave and phased arrays and IoT and sort of end-to-end software-defined radio, the sort of development pathways and such. So there's an awful lot of cool stuff. Now And thanks to Neil. Again, Neil, thank you for doing this. In the NEWSDR-2020 Slack channel, all the links to each individual Zoom session. So you can meet Marco, you can meet Yaya, you can meet Fatoumata and ask them one-on-one virtually the questions of the work that they're doing, what they just talked about. So what we'll do is we'll pause this main track, and everyone's encouraged to go to the poster session, the posters that they found very interesting. And then at 2:30, we'll start the one of 3 fireside chats for the afternoon. Okay, so we'll reconvene at 2:30. So in the meantime, chop, check out those posters, and we'll touch base in 29 minutes. Okay. So hey Tim, hey Phil, and Dola. So let me unmute everybody because that's how. Let's see. And last but not least, there we go. So I think us three, we can be heard. And as for the masses, well, they don't count. No, just kidding.
Aye.
So Dola, like Tim and Phil and Dola, have you three ever met before? Past
I have
life,
met.
current life? No.
I have never had the pleasure. No.
Okay. Okay. So so Tim works at MediaTek, and he's been a prior participant at NEWSDR several times. It's given some great talks, especially on like 5G new radio. So I think Tim, you're actively involved in 3GPP activity, right?
Yes, I'm involved in actually both 3GPP and ETSI.
And ETSI, cool. Phil is both, like a radio scientist at MIT Haystack Observatory, and also a fellow Central Massachusetts person. So we're just a couple of towns over from each other. But Phil is very active in sort of the radio astronomy, remote sensing, radar type of space. That's like, not a lot of people think about when they're, or maybe they do. Like, that's what this discussion's all about with respect to like 5G coexisting with, let's say, radio astronomy. And Dola and I go back like a super duper long ways, since you were like a PhD student at UC Boulder, right? So.
Yes.
And since then, you're faculty at University of Albany, which, claim to fame. I think you said it's the second largest single pour building of concrete in the world, right?
Yes. Yes. I'm glad that you remembered.
Well, how can you not forget that fact? It's like I work in a building that is one single pour of concrete, and it's big. It's like University of Albany is like this massive, massive structure.
The largest one is Pentagon.
Yep.
Oh, yeah.
Yep. Yeah, you can't miss that from space.
Yes.
Well, I grew up in Schenectady, so.
Ah, I see.
There we go.
Albany is extremely familiar to me.
You visit Albany.
Yes.
Yes, absolutely.
And I have a very, very strong suspicion that some of my relatives work in the same area as you, Dola, because I think the New York State Police, they share the same campus as you do, right?
Yes. Yes.
Okay. So
it's very close. Yes.
Yeah. Yeah. Because like a lot of my relatives, for some oddball reason, settled in 3 blocks of Colony, which is a suburb of Albany. So let's get this show on the road. So to everyone who's signing in, and let's see what the live stream looks like. So this is the first of 3 fireside chats with respect to, in this case, the topic of spectral coexistence, which is something that's actually becoming more and more of a topic of discussion, especially as we're rolling out new wireless applications that need bandwidth. We also have a growing number of applications that depend on access to electromagnetic spectrum, and then of course how techniques of monitoring what's going out there in the electromagnetic spectrum world, right? So it is with great honor that we have with us here today Dr. Tim Fisher-Jeffs from MediaTek, so one of our sponsors for this event. We also have Dr. Phil Erickson from MIT Haystack Observatory. And we have Dr. Dola Saha from University of Albany, which is the other side of Massachusetts. But no, I'm going to be your moderator. Alex Wiglinski, I've been on this all day. But this is a topic that I'm really, really super duper interested in. And we have a half hour. So perhaps the best way to start off is for each of you to give a 2 to 3 minute sort of discussion, or your own perspective of what does spectral coexistence mean in your perspectives. So maybe we'll start with Tim, if you want to kick things off.
Yeah, I I did prepare some slides. I don't know if you would like to share them or if I can just
Oh,
talk.
sure.
It's
Like,
entirely up to you.
let me make you a co-host. Okay, so yeah, you should be able to share slides now in this interface.
Not quite sure how that is.
Oh, so there
done
should
there.
be like a green
share
button.
screen, right?
Yep, that's the
Right.
one.
And then you just have to pick which window is the right one from the little menu that pops up.
Exactly.
Well, currently I only have one.
Oh, that's good.
All right, how's that?
Coming along. There you go.
Come on. There we go. So in terms of 6 gigahertz, I'm not trying to be antagonistic, but unfortunately the ship has somewhat sailed in terms of the decision. And I would say now actually the real work begins on how do we make it work and not be a disaster. I don't know if anybody is aware, but the FCC very recently, April 23rd of this year, came up with their report and order for the 6 gigahertz spectrum, where they lay down the rules of what's allowed in terms of unlicensed spectrum usage for the Uni 5, 6, 7, and 8 bands. I'm not going to go into the details, but other than to highlight bullet 2, that the idea is to limit the transmit power and or the geography using what's called AFC, which is a terrible name, of unlicensed transmission to protect the incumbent services. But the decision is essentially there now. So, and there's a very similar decision for the EC, for the European community. And the rest of the world will follow because basically the EC governs more than just the European Union. It governs the CEPT region, and then the other major jurisdictions around the world pretty much just follow what the FCC and ETSI does, with maybe minor perturbations. But it's largely indoor, and if it's not indoor, it has to be geographically controlled, is basically the overriding message out of both of the regulatory bodies. So this is what it looks like from an unlicensed spectrum perspective at the moment. So the 6 gigahertz is the new spectrum. The thing that should stand out to you is that it's almost tripled the number of 80 megahertz channels that will be available for use for unlicensed spectrum for you and I running our Wi-Fi systems or our NRU systems or LAA systems. And it's almost doubled the total amount of spectrum. The European Union just incidentally is only focused on this first band, the Uni 5 band. So their actual regulatory framework for now at least stops here. But you know, it's a big deal in terms of the amount of spectrum that has been made available, provided it can be used fairly and without affecting incumbents. And well, why do they do that? Well, it should be obvious from these charts what's going on in the world. This is pulled from Cisco's VNI. If anybody doesn't know it, it's a very useful source of a snapshot of what's going on in the world in terms of internet and sort of wireless communication in general. But these graphs are basically telling you that there's billions of devices, there's billions, well, there's not quite billions, there's millions of hotspots, and it's only getting bigger. And then COVID gut punched us beginning of this year. And can anybody imagine what life would be like without a Wi-Fi connection maybe a decade ago, and where we would be right now? I suspect many more of us would either be back at work or out of a job if we didn't have what we have right now.
Yep.
So there is definitely proven importance to this Wi-Fi spectrum, sorry, to this unlicensed spectrum, provided that we can use it.
Right. Okay. Well, thank you, Tim. Thank you. Phil, like, do you have any slides you want to share, or you?
I don't, but I can leverage off of what the things that Tim has just said. Okay. So the 6 gigahertz band is actually a very good example of things that are happening, frankly, across the spectrum, and especially up into millimeter wave. Until relatively recently, there weren't that many devices that were being generated that could use, for example, 60 gigahertz, 80 gigahertz, 70, 90 gigahertz. Now that everyone has a automobile bumper radar, which are all operating at 60 gigahertz, I will remind everybody here, the largest phased array radar producer in the world is the Bosch Corporation, selling new radars that go into bumpers of cars. But 60 gigahertz in a microcosm is something about coexistence that the scientific community, which I'm sort of representing here, is working with. In the middle of that chart that Tim had showing you all the new bands available, there's a little sliver of spectrum from 6.65 to 6.6752 gigahertz. It turns out that's where methanol masers lie. In the universe, in star-forming regions, clouds of methanol coalesce into stars. And that particular band is what radio astronomers use to probe those particular areas from the surface of the Earth. That's set by the laws of physics and chemistry, and so the science can't really move out of the way of those kinds of uses. So in fact, in the order that Tim talked about, there is a particular call out to not allow outdoor devices to radiate into that little sliver. A similar thing applies to something called EESS, which is Earth Exploration Satellite Service. Those are the people that make passive measurements, for example, of ocean height. They also operate in these very same bands. There are various levels of protection ranging from primary, you must protect this band at all costs, to we encourage protection of this band, to if possible, you should protect this band. So what we're working with in the science community is that spectral coexistence means that we don't want to be naive and tell everybody to keep out. You're always going to keep out of these bands. That's not realistic for the very reasons that Tim talked about. But on the same hand, coexistence means maybe thinking about a little bit of a wider variety of users. And so the last general point I want to make is that in addition to the users that are doing commercial kind of systems where there's a certain noise floor, you may have neighbors that are radio astronomers that are operating literally at the thermal noise floor. And so adjacent channel interference, things that say, that emission mask that meant that you're supposed to be 60 dB down a certain distance away from the channel center, we really need that. Because in the case of 6 gigahertz, a whole bunch of unlicensed lower power emitters raise the water level to the point where the noise level then becomes impossible from the surface of the Earth to conduct some of these measurements. So the idea is more dialogues of exactly the kind we're having right now. It's been very clear that we need to do that in order to efficiently share the spectrum, to exchange ideas, to figure out, okay, what could you live with? Could you live with using it only in certain regions and not in other regions? There's a couple other points, but I'll save those for later. But that's kind of the frame and the perspective I'm coming in from.
Awesome. Thank you. How about you, Dola?
So instead of just looking only at 6 gigahertz band, I would like to see spectrum as a large spectrum mass, not just 6 gigahertz. We don't want to talk about only 900 megahertz or only 2.4 gigahertz. From scientific community, I think I like to see spectrum as a large band. And we have been looking at spectral coexistence under the name of dynamic spectrum access for a long, long time. About 20 years worth of research has been done, or if not more, on how dynamic access can be done based on just communication. So if you have multiple links, how do you efficiently stay with the incumbent? And at that time, I think the definition that communication researchers were mostly looking at were someone else who is also transmitting. But we are now talking about something which is very, very different. There are 3 types of application or usage of the spectrum. One is for communication that me from my background, and we are all using Wi-Fi, so we all know that yes, there is a use of spectrum for communication. Now, the second part is there is a lot of use for radar, which is, again, it's easy to detect when it goes out, but we really don't know when it is reflecting back. So we are measuring something where we can't measure. So that's a problem for understanding how to coexist with radars. And then the other part is the remote sensing. So remote sensing not even transmit anything. So they are just passive measurements, which by looking at the noise floor, we can get to know various different parameters like salinity of ocean or humidity of the soil, and all of these important factors, which we cannot define how much it is based on the number of bits per second. It's bits per second wise, it's absolutely nominal, but the importance is extremely high. So I see spectrum as a really wide highway, where if we are not discriminating vehicles in our highways, then we should not discriminate applications in the spectrum. On the other hand, we as a researcher need to know how to coexist within the same spectrum. And that requires much research in this domain before it can be deployed or it can be implemented in any way. Also, it's not just coexistence, but how do you know whether someone is not breaking the rules? So for example, in highways, there are police patrols, so we need similar enforcement or spectrum enforcement or regulations in place, either by people who are actually using the spectrum, similarly as like people using the highway, drivers in the highway, similarly for either crowd sense basis or some other system which requires to say that, well, someone is really breaking the rules. So there has to be rules and there has to be enforcement of those rules as well, so that all the applications that are there can meet their requirements. So I think that it has a long way to go.
Okay, cool.
Alex, I'd like to follow up if I might for a moment there. It brings a number of interesting things up. One of my colleagues point out that you were talking about detecting the interference. I think there's really two aspects to that. The first one is that the completely free market approach of just letting the market decide, it work itself out doesn't work terribly well. I think number two is that the regulatory agencies are so overburdened and understaffed that honestly, they leave it up to the users to bring a problem to them. And often the burden is on the user to prove that another user is violating their license to the point where, okay, now we have a framework that we can attack that on. So for under-resourced kind of things like often government-funded fundamental physics research, the resources to do that are very, very limited. It's very time-consuming to do so. And as another colleague of mine pointed out, the best instrument to detect a interference problem is the sensor itself often. And that goes right back to what Dola says. If I have something where I'm looking for something 60 dB down below any commercial analyzer I can get, I've got to use my radio telescope to figure out if there's a interference problem. There's a technological aspect to how do we solve this problem. There's also different aspects to what the particular applications need. My idea of time coherence may be very, very different than the idea for someone that is pushing bits. Canceling some of those data streams may, in my case, require that I have a coherent phase pattern over a certain amount of time, commensurate with the integration time that I need to do my measurement. If we don't talk back and forth about that, you can easily get a situation where you have a radiator who has a coherence that's short enough that I can't pull it out with conventional cancellation techniques. And then it is another uncoordinated, incoherent clutter source that just keeps raising the water line. These are the sorts of things that we think about all the time, being sometimes a passive user that's buffeted kind of by the winds of, again, very legitimate uses. It's like none of my colleagues, as Tim pointed out, really want to short circuit these things from the ground up. But what's happening right now is that the separation that used to happen between the science bands and the commercial bands, that's all blurred now. these two communities are overlapping so thoroughly now that the things we used to rely on, even ground terrain protection for a radio astronomy instrument, there are many commercial people who are putting things on 60,000 foot mobile platforms. All of those protections don't work anymore. So we need a dialogue, we need a new set of coexistence parameters. And the last thing I'll say is, frankly, we also need to understand what dynamic spectrum means, even. Because I hear that from 4 people, and often it means 4 different things. How is the bureaucratic, you know, if you're telling me I can use it from 10 to 12 today, and then you can use it from 12 to 2, in addition to what happens if my bookkeeping screws up, who's going to know? And what would I do if I saw that? Or if I'm analyzing data a month after it was taken, because science often does that, it's too late.
So maybe to interject. So those are some great points. Just speaking out to the audience, if anybody out there in cyberspace has a question, please post it in the Slack channel under like NEWSDR-2020. Like right now, I don't see anything. I think there was one person who did mention something. But first of all, is the Tim or Doha, do you have any comments? And while if you do, like while you're talking, I'll see if there's any questions that come in. But any thoughts on what Phil said? Because it actually relates in particular to communities communicating with each other, and everybody has different frames of reference. But yeah, like Tim, Doha, like what your perspectives? Maybe Tim, like
yeah, I can add something to that. I mean, my understanding about how the decision was come about in the first place to open up this spectrum was through some fairly extensive simulations based on assumptions of, you know, sort of millions of devices transmitting indoors, and certain power levels were decided sort of based on these simulations. But I'm not party to what those results were or what the simulations were themselves, but I believe that they did their due diligence before they made these decisions, at least. And then they've added this additional overlaying framework, which is, I mean, you could compare it, I guess, in some ways to the 5 gigahertz spectrum, where they're coexisting mostly with radars. So there's a coexistence mechanism at a very, very low level, which is called DFS, which is meant to be detecting radars, you know, airport radars, ship radars, anything that has to be a keep out. And if you ever detect one of those in 5 gigahertz, you just have to shut up, and that's it. You're out for an hour or something like that. And you can't go back in until you sense nothing. In the 6, they've come up with this, I guess you could call it an architecture, which is terribly named, as I said very briefly in my slides. It's called AFC, which everyone in the engineering world, at least to me, known as automatic frequency control. But no, this is automatic frequency coordination. Why they couldn't think of another name. It confuses everybody. And that is based on geography. So, for example, around your actual radio telescope, there will be an exclusion zone that's laid down. And no one can use that band in 6 gigahertz in that exclusion zone. Now, my concern around that is, as you say, who's going to monitor it? It's going to be you that's going to notice it and then going to have to report it, and the FCC was going to have to react on it.
Sure.
It's administered by commercial companies. So I believe at this stage, Facebook, Google, and a bunch of other companies have shown interest in running this AFC database, for which, by the way, they're allowed to charge, which is another kind of concern of mine, in that this is a way to squeeze the highway, if you like. You know, if you pay me more, I'll give you more potentially. But at least the principle is there, that the geography of exclusion can be applied and created. And there's been a test bed for this already. I don't know if you're aware of, there's a 3.4 gigahertz band or 3.2 gigahertz band called CBRS, Citizens Broadband Radio System.
Right.
That's the precursor to all of this, which also uses AFC. And you can argue whether it's been successful or not, but that was really the driving motivator behind doing the same in the 6 gigahertz.
Mm-hmm.
For the low power indoor, there is no need for AFC in the US. In the EU, country determination is still required, but it's not geography determination, it's only country determination. But the power levels there, I believe, are set such that they shouldn't leak out outdoors. And then the other part of the FCC ruling, which I'm not sure if you're aware of or not, but the client power levels are actually set 6 dB lower than the AP levels, meaning that it forces the clients to be in closer proximity to the AP than the AP can actually transmit out. So, it kind of prevents the clients from diverging too widely from the AP without completely losing communication. That was the intention of how they said it. Now, whether it works, I mean, that's I guess we're going to find out.
Yeah. Yeah, part of the difficulty, some of that is that the geographic protections that you're talking about, and Alex, I was watching the chat, and someone basically said, "Well, can't you have an antenna with very large side lobe suppression?" I use an antenna with a gain.
So just to repeat, one person I was saying, "Oh, this would be a great question," but yeah, exactly, somebody said, if you had directional filtering, wouldn't that help with bandwidth overlap and stuff? So yeah, and then they tagged you in that. So yeah.
Right, and so the answer is yes and no. Yes, in that yes, traditional radio astronomy predictions there's a 150 kilometer exclusion zone around this particular observatory in these particular frequency bands. Part of the problem is that the allowed emission levels and the size of that circle is set, often taking into account terrain protection. Again, if you have something at altitude that doesn't work any longer, I will not talk about Starlink here, but that's a major problem. And there's some dialogue going back and forth. But the second thing for this particular application, to be aware of, is that when you design a front end for something like a very sensitive passive measurement like radio astronomy, you kind of have a technical choice. You can design it for low noise, or you can design it for high dynamic range, but you cannot do both without an enormous amount of investment in technology. And so the difficulty is that there are many telescopes that were designed in quiet locations for the former, and those locations are no longer quiet. I can submit to you that Haystack Observatory on the east coast of Massachusetts is no longer a radio quiet place. So there is a catch up that we're having to play even in our community in the technological front, because out of band emitters, even though you knock them down quite a bit, that spike can be big enough to compress the front end of a very sensitive thing that is set to look at thermal noise levels. And so then even with directional protection, I have trouble. So that's but again, that's part of the dialogue, I think, that has to happen, right? This is our application. There's the commercial application. Can we find places where there's not a null set between these two? Can some cancellation techniques, depending again on the coherence of the particular signals involved, be applied? But I think the laissez-faire kind of thing just doesn't work anymore. And so I believe, Tim, what you're seeing is the FCC attempting to begin that kind of accommodation. But even in the order for the 6 gigahertz, you'll notice at the end that they say, by the way, there will be a further notice of proposed rulemaking to actually move some of those low power devices up in power and perhaps let some of them go outside. And then you would run into another round of consideration. People like the Committee on Radio Frequencies through the National Academy of Sciences, Medicine, and Engineering, they try to serve as a voice in the United States for scientific applications of the radio spectrum, but ultimately there is no government agency that dictates that. NSF, NASA, Air Force Office of Scientific Research all contribute to a committee where FCC and NTIA are right at the table. But that's a consensus committee. So but as you correctly pointed out, that's the United States. In the European Union, in the other IT regions, it's different. And as you know, these are diplomatic kinds of discussions too. They are literally treaties that countries sign to. So there's that whole bureaucracy at the top of it. It's very interesting.
So maybe Dola, like turning to you, like what are your thoughts on all of this? Like obviously, like because I think there are a lot of techniques, and I think also history, like like what is radio quiet is no longer radio quiet. What was, like, let's say, spectrum that was used for commercial applications now has kind of like like folks are looking at like 6G and pushing at like 160 gigahertz and in terms of carrier frequencies. Well, what are your thoughts?
One of the big issues, I think, is not only just to make it quiet, but how do you detect it, that this is a protected zone? Because we are not just talking about simple software-defined radios that can detect that noise level, because we are really talking about extremely low noise where the side channels or the leakage is happening. So not quite, if we try to measure it with a ton of random radios, those will look like quiet, which is not the case, which is definitely not quiet. And so it's not an easy problem to solve. I think it will require a lot of research money coming in to understand how we can define this, how we can understand this from both the communities, communication, as well as radio astronomy and remote sensing community coming together to really understand how we can exchange this information, this knowledge that about the communication into the other domains, so that then a better interference cancellation can be done. So yes, I think that's what needs to be done.
Cool, thank you. And just to let you all know, like all the discussions we're having here are like, I think the three of you are very well in sync with what's appearing in the Slack channel as well. So that's why I'm like saying, oh, the audience has a question. I'm like, nah, you already are answering it. You three are on top of it. I think honestly, like we'll probably have to conclude in a few seconds, but I just wanted to add that I think this is going to be much more of a growing, not a sort of a steady state or decreasing type of topic that's going to occur in the United States and around the world, right? I think as we become more connected, and I think the pandemic is kind of a sort of critical juncture in terms of our, like, highlighting the broadband dependence. I think like Tim's slide with a sort of close up of what a COVID virus looks like, I think is spot on. Like, if this was 10 years ago, people either be like out of work or would have to force to go to work. And I think now we've kind of like, this is kind of right time, right place, the wireless technology being able to enable us to telecommute, to do remote medicine, like, number of medical appointments my family has had, myself, my daughter, my wife. Like, I never had to set foot in a doctor's office. It's been great, or teaching and a lot of other things. But I think at the same time, there's more, there's so many wireless things out there, and we do need, and I think Dola's point about, like, how do we monitor this? And what Phil was mentioning, it's like, so we have these exclusion zones, we have sort of these sort of physical requirements of such, but I think this is going to be a very interesting, very multifaceted sort of research and development space. But I think you're, like, the three of you, thank you. Like, I think you've opened the Pandora's box of so many really cool topics, and hopefully energize the community. I know, like, there's like, questions percolating up in the Slack.
And I will try to go over and answer some of them too as we finish here.
Well, Tim, Phil, and Dola, thank you again so much for your time and joining us here for NEWSDR 2020. I really appreciate you, all three of you, taking the time for this fireside chat. Thank you so much.
Our pleasure.
Thank you. Take care. Thank you. So next up, we have Fireside Chat number 2. Fireside Chat number 2 is focused on a software-defined wireless communication network research infrastructure for Internet of Things. Wow. So another one really exciting topic that affects all of us around the world. and has a lot of connections with software-defined radio technology. So this is where I'm going to enjoy sitting back as I let my co-organizer, Yusuf Naderi, serve as the co-host, as the moderator for this panel discussion. So with that, Yusuf, take it away.
Thanks, Alex. Really excited to have a really super experienced people for this channel. I think the theme here is the next generation of IoT, and we are going to really look at it at a different perspective here. One is the infrastructure. So what we need to do for a software-defined infrastructure for next version, next generation of the IoT. That is one perspective. And then we are going to look at 5G and what the role 5G can play here in the next generation IoT. And the third perspective would be the security and reliability of the IoT, the long range communication needs and the security needs. And in the panel, we have Sung Han, who is an associate professor at University of Connecticut. And I think we'll have an excellent perspective on SDR integration with the industrial IoT from Sung's side. And we have Brian Kelly, he's an associate professor at University of Texas at San Antonio, and look forward to hear really diverse experience in the cellular network and the 5G integration with IoT. And also we have Matt Knight, a co-founder of the Agitator, which has, I think, well known for a community, and he has a world really class hands-on experience in LoRa and security aspect of the IoT communication, and also spectral coexistence. So by this introduction, so let me ask each of the member here to have a few minutes introduction, and we can focus in the vision and challenges and shortcoming in the existing infrastructure that we have toward the next generation IoT. And what's your vision, how you see the really main shortcoming and challenges? So shall we start with Son?
Sure. Can you hear me okay?
Good. Yes.
Okay, so thanks a lot for inviting me to be here. Okay, this is a great event. My name is Sung Han. I'm an associate professor in the computer science and engineering department at the University of Connecticut. As you also mentioned, okay, my main research interest is in the design and the development of industry IoT system. It's a part of the IoT scope. I mainly focus on communication protocol design, resource management problem in industry IoT systems, and also security and privacy issues in such systems. Currently, I have the honor to work with Alex at WPI, and also another faculty member in UTSA, working on a joint NSL planning project, to design and develop a software-defined industry IoT infrastructure to serve as a community research infrastructure to enable the access for a broad range of size researchers. Because my main research area is in the industry IoT, so I will just based on my limited knowledge, okay, to talk about my perspective regarding the major challenges in the design and deployment of next generation IoT system, or even like the current generation of the IoT systems. I think there are three major challenges. Okay, the first one is about the deployment environment, because for the industry IoT system, it's different from the the residential environment or the office environment. Industry environment is much harsher and noisier. So there are many different types of networks coexisting in the environment, right? Just as what we described in the last panel, talking about the coexistence problems. There are so many different types of networking technologies in the industry environment. And for example, the temperature, humidity in some of those areas of this environment is very high, okay? And also there could be many metal walls, doors, instruments, and moving objects like the human operators, like the robots, they are in the field. So when we are deploying the industry IoT solutions, okay, not only for the current one and also the future ones, all these factors, they have to be taken into consideration. So this is, in my opinion, the first challenge, okay, in the industry IoT system deployment. The second challenge actually is on the other side, okay, even because it's kind of a very noisy environment, but the performance requirement of the industry IoT system and applications, they are actually very, very high. because many of those applications, they are designed for mission critical and safety critical applications. For example, in process automation, factory automation industries, they have a stringent requirement on the timing, reliability, security. So for example, okay, for the high-speed motion control applications in industry, the latency requirement could be in the millisecond level or microsecond level. And the reliability requirement for the communication, they could be up to like 6.9 for the requirement, right? So basically, if we consider challenge 1 and challenge 2, okay, from both the environment and also the requirement, okay, this makes a design and a deployment of industry IoT system to be very challenging. And the last challenge in my mind is about the industry IoT system setup, because when we take a look at the industry IoT system, it's a quite a complex system. Actually, it's a system of systems. They have many different subsystems, they have different modules, and each of them, they are actually employing different type of networking technologies. So it's quite common for these different subsystems and modules. They are not only competing for the networking resources, okay, but also competing for the computing resources together. So, and also the situation could be even worse while we are considering, for example, the new subsystems are adding into this kind of industry systems, or some of the existing industry systems that they are going to change the configurations, change the specifications. So this makes this kind of the industry IoT system setup it's even become more challenging. So these are the 3 key challenges that in my mind, okay, that basically the roadblock, okay, for many of those kind of industry IoT system solution design and deployment. So when we take a look at the current industry IoT research, okay, I think the kind of major drawbacks in my mind is the first one is most of these researchers and also the test beds that we developed is mainly in the office environment or in the residential environment. So we cannot very carefully be able to capture those kind of characteristics of the real industry environment. So which will make those results not be very well justifiable. And the second drawbacks, okay, in existing research, in my opinion, is most of the people we are focused on, for example, one type of networking technologies, wireless technologies, but the coexistence problem, okay, in the industry domain actually it's very severe. And also, when we talk about the kind of resource management, we are not only talking about the wireless network resource management, but also a combination of both the networking resource and also the computing resource together, because nowadays for the industry applications, more of them are end-to-end systems. So they consider both the computing components and the network components to form this kind of end-to-end solutions. So I think both of the networking resource management and the computing resource management need to be considered together. So these are my perspective about the current challenges and some drawbacks of the existing research, especially in the academia.
Great, excellent. Thanks a lot. So we can go to Brian. So what's your shot here? What is a vision that you are seeing for next generation IoT and some of the major challenges that we have?
Yes, thank you for inviting me. And it's very hard to follow up on Dr. Han's presentation, but I will try. Let me just say first a little bit about myself. So I'm Dr. Brian Kelly. I'm an associate professor of electrical and computer engineering at the University of Texas at San Antonio. Before I joined the University of Texas at San Antonio, I came out of industry. So after I graduated from, I did my undergraduate at Cornell and graduate work at Georgia Tech, and then went into industry. So part of my background is informed by my industry experience. I filed a number of patents. I worked with Motorola while I was in industry. So I have a broad telecommunications background and did everything from designing communication system platforms, signal processing algorithms, to serving on the 3GPP standards body as well. And contributing to the RAND 4 standards. Since joining the University of Texas at San Antonio, I've taught courses on Internet of Things, software-defined radio, 4G communications, which is now 5G communications. And so I've got a lot of really interesting insights informed by my various experiences. One of the things that has occurred recently my team has been approached by the county, Bexar County in San Antonio, about the digital divide issue. So one very interesting phenomena is due to the virus, the students are returning to school. Many of them have to do so basically at home, and there's a divide between students who have significant access to communications and those that do not. So one of the things that we've been looking at, so we formed a team to address this, is basically setting up private networks, private 5G networks, private 4G networks, using citizen broadband radio services, which we think, it's got this 3-tiered structure associated with it. So it basically enables, private owners to access, the spectrum on a county by county basis, potentially. And with these kinds of technologies, we can potentially give access to students that wouldn't normally have access. So this is one of the areas that I'm focusing on. Another area, I'm on the 5G steering group of Joint Base San Antonio. And this, our particular group was received from Department of Defense funding to develop a 5G experimental network. And so I'm working with a large team of researchers to do just that. What we're looking at are 2 areas. One is 5G security, 5G network security, basically for military folks, as well as the support of 5G with telemedicine, enabling telemedicine to be performed at remote distances. But you can imagine if that's in a maybe an environment where you don't have easy access again, that's another area that I'm focused on. In terms of some of the sort of research challenges, one area that is always important, but becomes increasingly important with 5G and 6G, as these things get baked into our critical infrastructure, the security challenges are immense. So I foresee in the future just tremendous advances needed to secure the network, because let's just take the digital divide. Let's say 40% of students are learning in some kind of environment where they have network access. Well, if that network access goes down, it gets hijacked, or let's say all of their accounts get broken into, right? That's a tremendous travesty. Let's take telemedicine as another example. When you have electronic health records in telemedicine, those records have to be, encapsulated essentially for the life of the patients. So if we have health medical records and they get destroyed and we don't have backups, paper backups are one thing, right? But let's suppose we are trying to modernize and we don't have paper, right? So if the records of individuals, their whole health history gets destroyed, right? That's a tremendous travesty. So one area of research I've been focusing on is security. There are a number of different areas of security. One is that I've been looking at in particular is what's referred to as physical layer security, which tries to use some of the randomness of the over-the-air channel, and particularly in what's called in the time division duplex mode. We can use that, and we can actually generate some pretty good capabilities to secure our wireless communications. We submitted and presented a number of papers on that, some at MILCOM, some at System of System Engineering conferences.
Excellent.
Okay, so I'll stop there.
Yes, yes. We'll go to, I think, deeper the security aspect in the next questions. And thanks a lot. Matt, do you want to also have your perspective of how you see the next generation IoT? What are the main shortcomings and challenges according to your experience?
Yeah, sure thing. Thanks so much, Yusuf. It's great to be here. Just to introduce myself briefly, my name is Matt Knight. I'm here today in my agency as a co-founder of Agitator, which is a software wireless and security company. I was founded by myself and Mark Newland 2 years ago to enable us to compete in DARPA's Spectrum Collaboration Challenge. If any of you were following that event, we competed as Team Helmake Radio. So since the event, we've branched out into other domains and projects, largely at the security. So apart from having been an SC2 finalist, I'm also a security researcher and engineer. I really enjoy exploring everything from embedded systems and radio physical layers up through cloud security, so sort of the full spectrum. If you go back far enough, I started my career as an electrical engineer, got a BE from Dartmouth, and software radio was sort of my vector into security. I started playing with SDR as a hobby, and shortly thereafter discovered how many radio protocols are really built up on the principle of security through obscurity. FIs being proprietary meant that adversaries couldn't, it wasn't just as simple as sending an HTTP request to a service to get it to do something bad. You had to have a piece of hardware that let you interact with it. However, SDR has really shattered that threat model. So that was, pretty profound for me. And since then, I've been really focused on security, expanding up the proverbial tech stack from then. But I remain passionate about the intersection of wireless, physical layers, and security. So, I'll keep it brief because I know you have some questions for us. IoT, as we know, encompasses many sort of like different application modalities and deployment and security requirements. It's a broad field. I think there are applications of legacy, cellular and telecommunication protocols, but there are also areas where those fall short. We see a number of emerging technologies that are popping up to support those diverse use cases. And while those, bring with them opportunities to get, security right and to, improve on the state of the art, in many ways they have failed to deliver on that. But I'll pause there. It's great to be here. One other comment, I attended NEWSDR in 2014 and 2016 when I was living in Cambridge and really enjoyed the event and the community. So it's really good to be here today. So thanks.
Excellent. Thanks a lot for the comments. I think we can also, if audience have a question, please ask through the Slack channel, and we will try to ask those questions as much as possible. I think the next question for Song is what is the role of software-defined radios and networking in industrial IoT? What's your insight here? Yes, I think yes.
Okay. Yeah. I think it's it's just based on my limited knowledge. I think it's basically two sides. Okay, on one side, I think the software-defined radio or software-defined networking technology together, right? Because when we talk about the industry IoT systems, it's as we said, okay, it's more like it's a very complex system, including both the wired part and the wireless part. So if we talk about this kind of a software-defined infrastructure, then it should consist of like software-defined networking, like the software-defined switches working as the backbone system, and also the software-defined radio-based, the wireless devices working as those edge devices. So this is basically, in my opinion, this looks like this kind of hierarchical structure. So on one side, I think this is a brilliant future. It has brilliant future because it brings a huge amount of flexibility, like from all the layers of this kind of radio communication protocols, okay, in the backbone infrastructure, that to let the users, like the researchers, to be able to exploit all the possibilities, right? So I think this is great, okay, and actually we have already seen tremendous amount of effort, okay, from both the academia and industry, they are working on this kind of aspect, right? From security and privacy, from the communication protocol, from this resource management. Even now we see that, okay, they are not talking about only have this kind of a control plane, okay, for the software and network. They also have the PISA architecture. They can also support those kind of, data plane, those kind of a software-based data plane. So we can see that, okay, there's a huge amount of efforts, okay, looking into it. On the other side, okay, from the practitioner perspective, okay, because I'm working with many, industry partners, okay, because actually from myself, okay, I wanted to push this kind of a software and defined radio-based, like high-speed wireless communication protocols to the industry domain, especially for the process automation, like factory automation applications. But it seems that they are not still not very widely deployed, okay, in the current industry applications. I believe there are several reasons. Okay, the first one is those kind of industries, right? Process automation, factory automation, they are very conservative because they are safety critical, mission critical. So they wanted to make sure that, okay, all these kind of technologies, they are very, very validated, okay, or even certified, okay, before those kind of software and defined radio-based devices can be deployed in the field, right? So for example, as Brian and Matt mentioned, those kind of security issues, right? So if they don't get the 100% confidence, okay, they are recommended, okay, to be able to deploy those kind of technology in the industry field. The other one I can sense is about the cost. Because for those kind of industry automation systems, so they are trying to make those kind of devices to be as cheap as possible because they want to reduce the cost. Okay, but if we consider those kind of radio, they are relatively cheap. Okay, but compared with the software and radio platforms, I know, okay, the price currently is keep reducing, but still not yet at that level that they can be massively deployed in the industry field. Because in the industry IoT system, we are not talking about 2 devices, okay, 10 devices. We are talking about could be hundreds or thousands of devices, because in this kind of industry, they are talking about a pervasive sensing. They are deploying sensors everywhere. So, and the third, I think the potential barrier is about the energy consumption. Because for those kind of industry IoT systems, they want to make them extremely energy efficient. So compared with existing those kind of protocols or the hardware that they use from the commercial off-the-shelf solutions, the energy efficiency is very good. But for the software and radio platform, at least in our current stage, okay, the energy consumption. I mean, I know a lot of work talking about how to optimize energy consumption of software and radio platform, but I believe, okay, if they wanted to really be massively deployed in the industry IoT systems, still quite a lot of work. Okay, they are still necessary. Okay, so these are my perspective regarding the role of the software and radio, but only in the industry IoT systems.
Yes, great. Thank you very much. And a question for Brian, following up what is the conversation we had. So what are some ways that IoT can help to bridge the digital divide gap that you mentioned? We have shortened the time, so if we can have maybe a few minutes.
There are a number of different ways in which IoT can bridge the digital divide gap. I think one of the key things that it can do is basically create sort of this virtual presence, right? So we're talking about things like the tactile internet, trying to bring learning at a remote distance as if you're right there. To do that, one of the things that we need to do is focus, I think, a great deal on edge computing and the ability to really shorten that latency so that we can put robots and control them remotely and create environments that appear realistic. Other things that can help reduce the digital divide include things like the increasing use of artificial intelligence so that we can create learning environments that in some sense are sustaining and where people can have easy access to, let's say it's training, right? So you have the physical teacher, then you have the virtual teacher. The virtual teacher with AI is able to create certain environments, certain mentoring capability that will sort of multiply. Let's say there's a human in the loop, will multiply, certain human capabilities. So I think these are some of the things that can help improve the digital.
Great. Thank you very much. And I think the last question, and then we can conclude the meeting for Matt. You have worked in LoRa as an example. I think a lot of excellent works. How you see the role of the long-range communication along with the secure and reliable in the next generation of the IoT? Any insight would be really appreciated. Yes, I think you are mute. See, Matt.
Thanks. Yeah, Zoom didn't let me do it myself. Appreciate it.
I see.
Yeah. So I appreciate the question. Sure. So, IoT is a very broad term. It encompasses, many different modalities of communication. So, like IoT applications, we have like a CCTV camera, which is going to stream like H.264 video sort of on one end, but then we also have like, say, like an agricultural sensor that needs to send like an 8-bit moisture reading 4 times a day, just hypothetically, right? So we have very different application and deployment requirements for each. The CCTV camera might be stationary and powered. The agricultural sensor might be unpowered and needs to sit in the middle of the field for years on end. So right away we have like power constraints and endurance, is dimensions right away. Then depending on whether or not the link is simplex or duplex, that puts further constraints on the ciphers and the security architecture you can build within your application. And then you throw on top, like maybe there's no service where the sensor is being deployed. Verizon, AT&T maybe don't care about deploying in an area that's going to serve 10 farmers. Then maybe you run into a scenario where you want to run your own standalone network. And that also introduces the dimension of spectrum as well. So, there are all these different dimensions that go into sort of the viability of these different protocols. So to that end, we've seen a lot of innovation at the PHY layer. You mentioned LoRa. LoRa is an example of a very novel PHY that pushes the bounds of what was traditionally thought possible within an ISM band. Today it seems like pretty much everything is built up on like some sort of like OFDM or FSK, but LoRa is built on chirps. So it's got more in common with like radar systems than other traditional digital comms protocols. So because of this, it's really well suited for coexistence with other protocols. But it's really limited in terms of power and duty cycle. And I think the security dimension is more interesting if we look at LoRa's competitor Sigfox. Sigfox is even more power and duty cycle constrained. I think you're limited to like, I think it's something on the order of like 1,400 bits per day under like a Sigfox device license, and it's also, I believe, uplink only. So that puts some limitations on the type of security architecture you can deploy there. Just briefly, I think spectrum access is pretty defining here in terms of what some of the options are. DARPA's SC2 program did a nice job of sort of testing the range of applications that IoT and IoT-centric 5G applications are designed to support, from sort of the heavy-duty streaming use cases down to like small, lightweight packet radio. I would love to see more research done in these regimes because I think it's kind of unfortunate that so cellular security has been pretty widely reported on. I think it's kind of unfortunate that all of the commercial cellular and wide area network options are really bound by the same effective threat model. You really can't there's really not much to for a consumer to go and shop around if you're looking for a cellular type deployment, because Verizon, AT&T, and T-Mobile operators like that all are effectively the same and have the same limitations in that regard. So I think there's some technological research that underpins this. There's some policy as it intersects with licensing. I don't know what the future looks like, but I'm encouraged by the direction of research and the enthusiasm in the area.
Right, great. Thank you very much. I think we are really short in time, and we have a next fireside. We have some question in the chat, so we'll direct those questions to you. So I think we will probably continue answering those questions in the chat. So thank you, Son. Thank you, Brian. Thank you, Matt. I think it was excellent discussion, and I know this is a very wide topic, so we kind of just touch it, and hopefully that could be more deeper conversation in the next events. Thanks a lot. Yeah, Alex. Yes.
Thank you, Yusuf, and thank you, Brian, Son, and Matt. Very exciting IoT. Thank you again.
Thank you guys.
So now to the last of the 3 fireside chats. This one, this is going to be exciting because like I can imagine Slack kind of burning up with this one, is the topic of open source software and software-defined radio. And so here, the moderator of this session is going to be our own John Swoboda, and the panelists are Pau Closas. Oh, there's Pau. Hi, Pau.
Hey.
Frida Fund. There's Frida. Hello. And Juha Verinen. Where is Juha? Oh, there we go. And I will just turn everything over to John. So John and panelists, take it away.
All right, let's get crazy. So anyway, so we all know. I think software-defined radio has been greatly helped by the open source community, and also adding to the open source community has been just very helpful in general. And so we got 3 panelists today from SDR, the SDR world, who have been contributing to their own open source projects and other open source areas. So first, we'll start with let's do a quick little intro for each person. Pau Closas from Northeastern, who works in GNSS SDR.
Yeah, hi, John. So thanks for inviting. It's great to be back on NEWSDR again this year, even virtually. So I can give maybe 1 minute or background info from me. So I'm assistant professor in electrical engineering, Northeastern University. My background is on signal processing, machine learning, mostly applied to satellite-based navigation systems, so GPS, GNSS in general. And this is where I get connected to SDR. So as John was mentioning, 10 years ago, or maybe even more, we started an open source project called GNSS SDR, which basically by then it was a GPS, end-to-end GPS receiver. So during all these years, it kept growing. And now, well, it incorporates more signals and stuff, but basically we were following this open source philosophy that I think we're going to discuss today. Thanks, John.
All right. So next is Frida Fund from NYU, who is working very active on the Genie project and the wireless testbed at NYU. Frida, are you there?
Yeah, thanks. It wouldn't let me unmute myself. Hi, thanks for having me, even though you tried to keep me on mute. My interest in open source software and software-defined radio actually extends beyond software. So my background is in open access testbeds that any researcher or educator or student can use in the field of computer networks, but that includes wireless and software-defined radio. So I operate a wireless testbed at NYU that anybody can use over the internet, researchers, students, educators, and hopefully today I'll have a chance to tell you about a few other testbeds and how you can use them to encourage contributions to open source software.
All right, awesome. So next up is Juha Virnen, who is currently at the University of Tromsø, and he's worked in the past on a number of geophysics projects and developing radar, software-defined radar receivers and radio receivers for various remote sensing applications. Juha?
Thanks, John. You basically stole my introduction. Good evening. Yeah, I'm a professor at nowadays in Norway. Before this, I was at MIT, working with geophysical radar remote sensing, and that's still what I work with most of the time. I'd say my specialty is developing novel radar signal processing techniques for remote sensing the various geophysical targets. Most of the time I work with high power large aperture radars. There's an example of a high power large aperture radar on my wall here. Some of you might recognize that antenna, it's the Arecibo dish. Some of you might have seen something in the news about the Arecibo dish yesterday. Hopefully they'll get that fixed. So I use these types of large radars to develop new ways of sensing the Earth's ionized upper atmosphere. I've also dabbled a little bit with planetary radar. I've made a very long wavelength, 6-meter wavelength map of the moon using a high power large aperture radar. And I'm also involved a little bit with the European Space Agency space debris observations. And you know, I've benefited a lot from open source SDR software packages. I first stumbled on GNU Radio and open source and you know the EDIS research boxes in about 2006 when I was starting my PhD studies, and I quickly found that I can make a lot of things happen with not so many resources. Just as a lonely PhD student who has to do everything by himself. And since then, I've also contributed a little bit to and started some of my own open source projects as well. For example, the GNU Chirp Sounder, which is an open over-the-horizon radar receiver. I've got the GNU Ionizond, which we just published. I've developed an open source spread spectrum meteor radar, which is there's one deployed in Germany, one in Peru, one in Argentina, and they're building one now in Colorado in the US. You can see, if you were to visit these observatories, these high power large aperture radar observatories like Arecibo, you would see that inside there's a lot of open source software defined radio and also open source hardware. You know, the best plasma line receiver for the Arecibo 430 megahertz ionospheric radar is a USRP2 actually. All right, so that went a little bit long, so I'll hand it back to you, John.
All right. Yeah. So also, if you guys are ever in you know, Massachusetts in near Westford, feel free to stop by. You know, the what do you call it? The Millstone Hill in Haystack, where you'll see some of these open source radios actually, you know, taking data. You know, if we ever get out of the pandemic, that is. But let's not get into that just yet. I guess the main question I want to start with everyone, and I'll kind of just go in last name alphabetical order, I guess. You know, but what you guys, all of you have been you know, I think contributing to the open source software world. What do you think are some of the things that can be done to improve, you know, the open source software contribution, and also how the rate at which, you know, we can improve software within our community? Pal, I'm going to go with you first.
I think Pal's muted.
Yeah, you're
Excellent.
unmuted, Pal. Yeah.
Excellent, thank you. Yeah, so let me then get started stating the obvious, probably. On the bright side, I think that we have a really good, healthy ecosystem in the community of open source projects. So we have I mean, I think we are achieving a really professional coding standards. So I think really the ecosystem itself is very healthy. We have a bunch of people contributing, a lot of visibility in the projects. At least I can talk about the experience I had with our open source projects. So to me, everything seems to be running really good for the last years. Maybe because this is more about the challenges and the way forward. So maybe again, stating at the risk of stating the obvious, I would say that maybe one of the challenges that we have, or some things that we could see how to stimulate as a community, could be how to stimulate, again, this bidirectional code sharing. So let me explain that. So we see a lot of people contributing or benefiting from open source projects. And then they email you, yeah, this code is great, this project is fantastic, I've been able to do this and that. But we have a lot of people contributing back to the project, but some others that they are not really either sharing the code or maybe commenting it, some sort of bidirectional code sharing that will be, I think, terrific, or it's something more about up for discussion, I guess. But it's mostly, I think, in general, because we use this code, maybe we just use it, or maybe we do a small hack that serves for us, and then maybe we are lazy to document it properly or whatever, and then share it. It's not that we want to hide from anything, no. But I think, and I don't know, maybe that's something that we can discuss in this chat. So how could we do? How could we stimulate these contributions from everyone? Because everyone likes to go to the project and see new stuff, not only about the couple of guys that are developing it. So that's something I would maybe point as a kind of a challenge. Some other things that I was thinking about, maybe, okay, so here I am with this academic head, but maybe thinking about how industry contributes and benefits from open source projects. That's also something that I think it's moving a lot, recent startups, so that many people is benefiting from this. So I'll be curious, and I'll be happy to see which are business models that are built around open source projects. I mean, we know popular and well-known examples of this, but probably this is something that we as a community, or NEWSDR as a community, we could have some discussions around that, besides the obvious research and scientific oriented projects that we have been dealing with. So I guess I'll keep it short, so maybe we can do a couple of iterations on these ideas.
Yeah, I think that's good. I think, like you were saying, getting a good documentation procedure going, and then making sure industry is able to properly add to software-defined radio's open source network of tools would be very, I think, very helpful. The academics are already trying to put a lot of stuff out there. Freda, why don't you talk about how we can improve, our open source, contributing to open source software within our community, and feel free to jump into the aspect of the wireless test beds, because those are super interesting, and I think that'd be really great.
So I definitely have some thoughts. Now, Pal spoke about getting people to make these high quality contributions, better documentation, etc. I'm coming from a different perspective, because these days I don't actually use software radio much for my own research. I use it mainly for teaching. And I want to talk about how we could encourage contributions to open source from the other direction. So getting students used to working with open source software-defined radio software. And if it's okay, I'm going to share my screen because I want to show a few things. Is that okay? Can the host turn that on?
Yeah, just give me a second. I have to make you a, let me just, I gotta make you a co-host, I think. Let me just see. Do you have a thing to share or no?
Yeah, it said host disabled.
Oh, okay.
Okay, now
now you're co-host.
I just made it.
Perfect. Thanks a lot. Okay. So here's my recipe for encouraging contributions to open source in software-defined radio. The first step is I want to make sure that every ECE student, I'm in an ECE department, has a chance to touch a software radio sometime during their undergrad career. Now, what are the current barriers to doing that? We heard earlier this morning from the guys at MathWorks, Analog Devices. They have these curriculums, they have these lab exercises, but we don't have anywhere close to every ECE student touching an SDR. And the reason for that is also partly related to something that was brought up in chat earlier this morning, which is, if I can't get from 0 to a useful plot in 10 seconds, right, I'm done. Now, if this is true of researchers, it's even more so true of faculty members, instructors who are thinking about what kind of lab exercises to include in their course, right? If there's something that doesn't involve software radio that they can download and it runs and they don't have to learn a new platform and their students don't have to deal with installing complicated stuff, they're going to use that. So I think we need to make it much easier for faculty to incorporate software radio in the undergraduate curriculum. And I would like to see, these lab assignments with a lot more diversity in a lot of ways. So not only, lab curriculums and software-defined radio, because as much as we'd all like to teach intro to software-defined radio, we don't often get the opportunity. But I would like to see lab exercises involving software radio that, can just be used as a standalone one-off lab assignment in a digital communications, signal processing, even a computer networks course that's not a digital communications course. So I have an example, and I know this is something that students like because this is from the webmaster console for my blog. And this shows some of the top search queries that lead people to my blog, where I host many experiments on a range of topics in computer networks. And you see that I get lots of hits from students trying to understand how data rate is related to bandwidth, right? Now, what could we do to make it easy for every instructor out there to give a lab assignment involving software-defined radio when they teach this concept? Well, I have this lab assignment written up on my blog, and it describes basically how to run a Shiny SDR visualization, browser-based, and send some traffic over a network, over a software radio link. And you can see how the bandwidth changes, right, as you change the data rate. And this is something that students can actually run using test beds with no installation in the lab. They don't need access to a computer lab in school. I'm going to show you right now. It's so easy, so quick. I can do it right here in my browser. Just going to move this out of the way. Okay. So I'm going to run this on the Powder test bed at Utah right now. And I can set this up right in my browser. It took like 5 clicks to get to this, but because it takes 2 minutes to spin up, I didn't do it live. But I can just, click on a few things, get this thing. I can click on these nodes and get a shell. I already have a shell open. I can run my Shiny SDR right here. And I'm opening it in a browser. And now I can go back here, send some, dummy data with different data rates, different modulation and coding schemes. And I have a lab assignment that students can run in 10 minutes or less entirely in a browser. So that's ingredient number one. We want every student in their undergrad curriculum to be able to do something like this without this big barrier to entry. Ingredient number two is we want students to be able to keep playing with their software radios even when the class ends. So right now, if you teach software radio in a digital communications class, maybe you have a bunch of USRPs that your students can access in a lab in school, but once the class ends, they don't have it anymore. One of the big contributions of these open test beds is that if you use them for lab exercises, your students can keep working with them and playing with them when the course is over, even after they graduate. And I know I made it look like this was just a demo and you can't really do anything, but this is just a regular Ubuntu host. I have full root access on this. I can tinker with it. I can install other modules. While I was waiting for the session to start, I tried installing this Marmot E module that we were talking about earlier. So this is something that also makes it easier for people to play with SDR. So when you have these open test beds, anyone can get in and use them and have access to the real hardware. Once you have that, my hope is, smart people can do cool stuff and share it. And then you get to the other issue, which Mark's raised earlier this morning, which is a profit, but maybe someone else can address that.
Yeah, that's great, and I'm totally going to use those. What I think is really interesting for the test beds from the point of view of a current researcher who is often doing developing software for SDRs, having that in a CI type of environment where you're doing continuous integration could be very game changing, and for us especially, because thank you for putting that in the chat, because then I'm going to look into that. We're all going to look into that later and start messing around with that. I will say one thing we've been trying at Haystack. One thing I will say at Haystack, we've been trying to make it easier to get to the open source tools. We are using A couple of the researchers have packaged, GNU Radio into Anaconda, so you can get it through Anaconda downloads now. But I think your situation kind of deals at a much more universal level, as opposed to for us, we were just trying to get a workshop together. So I think this is really this kind of gets to that deeper problem. So that's good. And we probably will be using this if we're going to be testing our own stuff, I think, in the future. Okay, I'm going to move on to Juha. Juha, how do you think we can improve, open source software development and sharing, especially in the geophysics community, where you and me are?
Well, there were a lot of good points presented, but maybe I could tack on to the profit part that was left open. I mean, programmatically, I think when the government is providing funding for research, that should come with strong incentives to also not only publish the data openly, but also publish the software that was used to analyze that data. I think there should be more of that. I'm a scientist, and my currency is publications. How many publications have I written? How many citations do I have for publications? That does not incentivize me to maintain software long term. It incentivizes me to write a quick script that plots the data, allows me to write the paper, and then basically discard that script. And that script might have something useful. Many times people have asked me to release my software, but sometimes I do it, but I don't have time to comment it or release it properly. Some cases we have done that, but that requires a lot of time and engineering, which is not funded. So I think National Science Foundation, DARPA. I'm happy to see Tom Rondeau on DARPA, and he understands open source, and he's funding open source as well. And there are examples of that. For example, SRI has this resin project in our community where they provide Dockerized containers, which contain a lot of open source tools that we use in our community. MIT Haystack also has a very, very long track record of releasing open source tools for the community. But I think programmatic incentives, basically earmarking money for science funding also for long-term, long-term development efforts for software. I mean, I don't know why we have GNU Radio, but I think part of that is because there was a company that was supporting it for a long time and still is supporting it for a long time. We need some sort of base funding so we can maintain these awesome pieces of software. I mean, maybe I have a question for Paul, for example. How do you guys maintain, what's your base funding for long-term maintenance of the GNSS software?
Yeah, that's an excellent question. So we started, as many of us here, for fun, basically. Well, for fun, mostly because we were using this for our research. So at that time, there was no funding. Obviously, it was more internal funding, let's say, from the institutions we were working in. And then there is, I think, probably this happens in many other projects. There is a breakdown point where the project is mature enough so you can go and ask for funding relying on that project. So in our case, we were using it in the context of other projects that were using this GNSS receiver for other purposes. So then we were using this funding coming in, for instance, in Europe from the European Space Agency or Horizon 2020 to develop new features. So here in the US, the NSF also is supporting partially now the code where we are adding other features. But I think it's crucial to have this breakdown point for the project. So the benefit of using it in research is clear for funding agencies. That's something that I think, at least in our experience, maybe change for others.
There's a really interesting question that popped up in the chat. I think more or less the overall idea is the idea about bit rot of different projects. Well, I was going to go with the bit rot question. Sorry, Alex. But how do we prevent that? And there's a lot of things that come up in like people's PhD projects where they write maybe a piece of code and that looks pretty useful, and then it doesn't get kept up. And then we also have situations with companies as well. Freda, have you had experience with this? Have you tried to combat this in some way?
Yeah, I think that's a really good question. And testbeds can actually really help with that because, often when you have this kind of situation with like a PhD student project, it really only works on like a very specific installation with like a specific version of every, related software library, right? And as time goes on and those libraries are no longer the default, it becomes very hard to reproduce. What I really like about working with testbeds is that I didn't show you this feature of the testbed, but all of the testbeds I mentioned have the functionality where you can take a bit exact snapshot of the hard disk of the host you're running on and save it and kind of capture it in the metadata of your experiment. And you can share that experiment with other people so that when they spin it up, they have your exact working environment with your software and everything else you've prepared in it. So that really helps a lot because, it doesn't necessarily help you bring this code up to date so it works with current versions of libraries, but at least it means that you can always get, a working version up and running and work with that and maybe, kind of build on that incrementally. So I find that having testbeds that can capture the whole environment and not just, the code of module X really helps with that.
Okay, great. Let's go round robin with the bit rot question. Juha, how do you prevent bit rot?
I don't have a solution for that yet. Every now and then, for example, the GNU chirp sounder, I find that it doesn't work anymore with the latest versions of the software or the libraries. I just have to sit down and work on it. But unfortunately, it means that some of the software that I have released that will rot. I mean, some of the software that you guys maintain, for example, and have taken over, that I started contributing to a long time ago. That's kept alive because there is an investment into manpower to maintain that software. Haystack does a good job with that. Me as a associate professor, my task is to push master's thesis students and PhD students out the door. I'm trying to encourage them to use GitHub. I'm trying to encourage them to release their software as open source, and I review the code that my students write, and I try to make careful suggestions that this might be a better idea to do it this way with the higher quality code, and I also contribute to the software that my students develop. And one of my master's thesis students just developed an open source Amazon together with me. We programmed it together. It's now on GitHub, and it still works. I have one report of somebody who has managed to install it, and it relies on basically just Python and the UHD library.
Great. One last thing I want to get to Pal about. Again, Pal, ask your doctor about bit rot today. How do you deal with it? We're all doctors, so you know.
No, it's actually, this is a really good question. I was reading the Slack when I think it was Marcus Miller posting that. So the way we did that, so before we started the open source project, it actually happened what it was actually mentioning. So we all write our code, and then after we submit the paper, then the code never works. So in our case, we found that having this open source project running and having some ecosystem of people also checking the code, so it stimulates people also to make things or to code stuff that will run in the long run. And there's also a lot of people also checking that this is going to run and for a while, not for a couple of weeks until the deadline is over. So in our case, I think having open source projects and having PhD contributing to those projects benefits, and it's some way of addressing that. And I think it connects to what Frida was saying about the testbed. So it's kind of, you can think of an open source project as a software testbed if you want, right? So having some system, some ecosystem where you can keep contributing, making sure that code will run, is something that benefits for sure.
Mm-hmm. Yeah, no, I completely agree. I think that, you know, I've got code that I've got, you know, for my PhD that I'm like using it, but I'm using it like within Haystack, but then now I've got to like, but the other aspect is like sometimes the utility or the way I've adjusted it will only work in a certain way. And so I have to like work now to expand that usability beyond that. I wish we had some time to talk about, like, you know, trying to push open source stuff to the into corporate America and get them in terms of the two-way street. I think we might be out of time. Alex probably wants to, you know,
just a little bit. But I mean, the thing is, there's
Alex. Yeah, it's a great time for you to die.
There's always the Slack channel that we have.
Yeah, please continue this in Slack if Alex ever comes back. Even if Alex comes back, please continue this in Slack. And I think that would be really useful because, you know, this is a really interesting topic, and, you know, people have a lot of opinions about this. And, you know, we have our way of doing things, and you know, like from where I am at Haystack, we have our way of doing things, and I think we can. There's always ways to improve. Actually, if any,
like a lot of activity happening in the Slack channel.
All right. I did get one question that I want to throw this out before this, you know, so people can mess around with this in the Slack channel. But let's ask the community. So wants to ask. We're excited about open source tools for host-based DSPs, GNU Radio, Python, etc. But then we don't mind using proprietary tools for FPGA DSP development, Lovato or Quartus. So whoever wants to bring that out in the chat and start that, you know, fight, and start that. Or if anyone wants to comment really quickly about that.
Yeah, I think evolution also, you know, helps to remove software that is not so good and you know, maintains the code that is worth maintaining. You know, people using it will be annoyed if it doesn't work, and they will send you emails, and they'll send you more emails, and that's one incentive for me.
All right. Well, I think that concludes our fireside chat. You know, and
John,
hand this back over to Alex.
And I'm here. Did you or am I fading out again?
You're back. I think the wilds of you know, the wilds of West Boylan are taking their toll on the internet.
You know, Central Massachusetts and that network connections, right? All those deer eating the cables.
I don't know if that's deer, Alex.
But John, thank you for moderating, and Hao and Frida and Juha, thank you again for your time, especially Juha. Like, what time is it over there in Tromsø is Norway, right? So what time is it over there? And here, I'm going to unmute you because I have the power. Or trying to unmute. There we go.
2200.
Yeah, that's where I had to resort to Slack. 2200. But I'm a night owl. I tend to work late. Okay. Yeah, thanks for inviting me. I think I gave a talk, you know, maybe at one of the first NEWSDR conferences. I at least visited one of the first NEWSDR conferences. So thanks for organizing this.
Thank you. Thank you.
This live. Hopefully I'll participate again in years to come.
Awesome. Thank you. And Frida, thank you from NYU. You folks are doing a lot of SDR work there. So thank you again so much. Very insightful. And Pao,
thanks for
I think
having
we're
me. It's been
intersecting like a gajillion times or something like that. I don't know what's going on.
Thanks for inviting. This is great, guys.
Well, thank you. Thank you. So so with that, we're gonna close up the event before I fade out again because of like the reliable network connectivity that I have. So what I'm gonna do is, so first of all, again, you know, like this is a NEWSDR 2020, and the last thing, like, you know, it's over, but it's not over, right? And you might say, oh, hey, that sounds very like, you know, kind of like confusing, but it's not. What happens is from 5 to 7 p.m., both the MathWorks and NI EDIS Research both have short tutorials in the evening. Well, it depends on what time zone you're calling it from. So definitely check that out. And again, those links have been sent out to everybody who registered. So definitely check it out. See what there is to see. It's going to be really, really super duper exciting. Again, we really want to sincerely thank our sponsors for generously supporting this event. MathWorks, MediaTek, Link, Analog Devices, NI, EDIS, Verizon. Like, you know, again, their support is really generously acknowledged. Like it's just been fantastic having them support us all these years. Hopefully we'll see you all in NEWSDR 2021. It's been great. Again, like you know, even though the event's over, there's an online community that continues to communicate and such. Like I'm looking right now on the Slack channel, and it's just like I cannot sort of keep track of like 2 computers going on at the same time. So definitely check us out on Slack. We have a LinkedIn page as well. So that's if you want to like exchange resumes or say, hey, you graduated from that same school as I did? Oh, you know, sort of thing. So that's more like for like the working professional. But Slack is really where people can engage and connect and all that. Of course, our website, www.sdr-boston.org. So definitely check us out there. So with that, on behalf of all the NEWSDR 2020 co-organizers, so myself, Alex Wiglinski, Neil Pandia from NI EDIS Research, Mike Rame from UMass Boston, John Swoboda from MIT Haystack Observatory, and Yusuf Naderi from Northeastern. We want to thank you all for spending the day with us. And again, this link, the YouTube live stream, once it's compiled and stuff, I'm going to make it public. Like right now, it's unlisted, but I'm going to make it public. So if you want to watch this event over and over and over again, or maybe parts of the event and like different fireside chats or presentations you saw during the day, like definitely, you know, like I'll make that, I'll share that link available, like the public link available on the Slack channel, so that people can have access to that. And do spread the word. Let people know that there's this community of SDR folks who are really interested in this technology and its applications. And you know, like let's stick together, especially since what we're doing definitely has an impact on the world today, especially in this like COVID-19 pandemic scenario. So with that, thank you all for being with us today, and stay safe out there. And hopefully physically we'll be able to meet with each other soon in the next NEWSDR. So take care, everyone.